Oh, good.
It's on channel 12. Check. Check. Mic check. 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 Is that okay?
Check 1 2. Check 1 2. Check 1 2. Check 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 check. Yeah. Testing 1 2. Testing testing.
Good morning. Good morning, everyone. Good morning. Okay. Happy to see all of you here. We're going to start with talks very soon. Just an opening couple of remarks here before we get going. So yeah, you can grab some coffee. Who's working on the CTF? Who's in the lead? Yeah, you look up Daniel with how many points? Too many points. Fair enough. He has all the points. Why am I not surprised? Yeah, today we're going to close out and then I'm going to show the scoreboard again. Anyway, couple of things. So yeah, we made it all the way to Wednesday. So I'm glad to see people still around. I hope you had a good time so far. I really liked the talks yesterday. I also like the breakouts. And today we will not only have great talks, and not only have great talks, but also have the evening social, which I'll talk about in a sec. It says Tuesday, but it should say Wednesday. Whoopsie. Yeah. So the social event. So this is one of our highlights, of course. I mean, not like this isn't a social gathering all week, but tonight we'll go to Penn Social. It's close by 801 East Street. So you can just East Street. I mean, you can. I mean, it's close. You can take a electric scooter, or you can walk, whatever. It's not far. 10-minute walk across the mall, even better. Like, I mean, you can get some sights in as well. And apparently, some people want to do a skee ball competition. So if you're not good at the CTF, you might be good at skee ball, and then that's your chance. Anyway. Yeah, so please show up. Obviously, this is part of your, if you registered for the conference, you show up to that. It's part of your, it's part of the conference. And it's a really important one too. I'm looking forward to seeing you all there and having nice conversations. Also, I want to quickly plug our merchandise. So at the registration desk, we are selling these bottles and also these like GRCon 2022 shirts. So they will not be available. Like there's one batch. They can only increase in value. I don't know if that's true. But for $25, they're a steal anyway. So yeah, tickets on GNURadio.org/shop22. You point your phone there or your laptop. You buy it online, and then you basically take your receipt to the front desk, and they will hand you the shirt or the bottle. And we've never had bottles before too. And so again, all right. Yeah, schedule. Kind of the same as yesterday. We have talks, we have exhibits, but there will be the torchstick workshop, which was not entirely sure if that would actually happen, is happening in South America. And I think, Josh, are you doing the GR 4.0 thing? So Josh is not only talking about the project today, but also talking about GR 4.0. Exciting stuff. Capture the Flag still going on, and lightning talks. We do have one slot available. If you want to talk about something for 5 minutes, approach us. Otherwise, no big deal. I'm sorry? Yeah, one today, and I think one tomorrow. So something like that. I've talked about this. Join us on chat. It's good for back channel communication. It's better than actually talking in here while people on stage are giving a presentation. That's okay if you talk during the opening, but please don't talk during the presentations. And Wi-Fi, yeah. Amateur radio exams. I've had this up every morning so far, but you can still, and walk-ins are welcome. You can sign up now. Seriously, if you've never done this, just go for technician. There's a good chance you can do it. You want to join a CTF team? It's not too late. Go to the front desk. There's other people looking for teams as well. You can just gang up. And yeah, that's it. So with that, I'm going to hand it off to Steve, who will introduce our keynote speaker, and that'll kick off the talks for today. So yeah.
Thanks, Martin. So it's a great pleasure today to be able to introduce Dr. Tony Beasley, who is the director of the National Radio Astronomy Observatory. So NRAO is responsible for many of the radio telescopes in the US. I think probably the one that many of you are familiar with is the Very Large Array, the 27-element array in Socorro, New Mexico, that's appeared in many movies, but there's also many other facilities across the US, and the new NG-VLA, which is playing the next generation VLA, which really is sort of an evolution of what's gone on with the VLA to the next level, spread out across a much larger area of the southwestern US. I'm sure Tony's going to cover that a little bit this morning. Tony got his PhD in Sydney. He was then the project manager for the KAMA telescope, the Combined Array for Research in Millimeter Wave Astronomy, which was a telescope in the Owens, or just above the Owens Valley in California, that laid a lot of the groundwork for ALMA, the Atacama Large Millimeter Array in Chile, which Tony was also the project manager of. He's been the director of NRAO since 2012. He's also the vice president for astronomy operations at Associated Universities, Inc. So also under his remit comes things like the Green Bank Telescope. And he's been a big booster for SETI as well, which has been really encouraging for those of us working in that field. And he's going to tell us this morning about satellite constellations and astronomy. So thanks very much, Tony. I guess you have your... Yeah.
Okay, good morning. Can you hear me? Up the back? Yes? Thumbs up? You guys can, yeah, good. Okay. Thanks very much, Steve, for the introduction, and thank you to the conference organizers for inviting me. A little bit like yesterday, like Stephanie, we're kind of an end user for a lot of the technologies and techniques that you all develop. And so I'm going to talk about a specific problem, but along the way, I'm going to kind of give you some sense of why we need you and what we're looking for. So Steve mentioned I'm from the National Radio Astronomy Observatory. This is our mission statement. We provide world-leading telescopes, instrumentation, data, and expertise. We train the next generation of scientists and engineers. We try and improve the inclusion and diversity of the scientific endeavor. And we promote astronomy to foster a more scientifically literate society. So, perhaps a fundamental question that comes up a lot of the time is, why do we do astronomy? Why do governments around the world invest in astronomy? So there's a couple of standard answers. There's kind of the historical, cultural one. We all are trying to understand our place in the universe. And so throughout history, there have been sort of astronomical endeavors. Cosmic laboratory, when you look out into space, you see places that have gravity and magnetic fields and densities and temperatures and so on that are not possible to reproduce here on Earth. And so you can learn about physics by looking at these places in the universe. A big one is technology development. To make these sorts of observations, you've really got to produce equipment that's incredibly sensitive. And that's where we kind of push all of you in terms of digital signal processing and the other sorts of things that you're all involved in. We really very much are pushing the edge of technology. We used to push a lot harder in computing. The data that we were moving around was incredibly significant. That is still true in some ways, but a lot of it these days is digital engineering. We're actually just moving a lot of bits around and trying to process them. And so that's where I think some of the work and some of the things that I've seen here over the last few days is relevant. There is a huge difference in sensitivity. So if I was to take all of you now and transport you to the surface of Pluto, in the few remaining seconds of your life, while your cell phone was still working, your cell phone would be a very bright radio source to my radio telescopes. And the typical unit we use is 1 Jansky, which is 10 to the minus 26 watts per square meter per hertz. And so that is something to think about, particularly as I sort of move into RFI, that your cell phone, or typically 1 watt cell phone on Pluto from here looks like a very bright astronomical source. And so there's 100 people in the room here. You would be one of the brighter radio sources in the sky, briefly. And then STEM interest. Astronomy is a fascinating thing. It's a bit like dinosaurs for kids. It is a great way to get people kind of engaged in the scientific endeavor and just thinking about the world and so on. So this is why we do astronomy, and you'll notice that NRAO's mission statement kind of reflects off these topics in many ways. Talking about our instruments, this is the sort of the landmark instrument. This is the Jansky Very Large Array. This is 27 antennas on a Y-shaped track in New Mexico. This was built in the 1970s and the early 1980s, and it really is the premier radio telescope in the world today. It's incredibly flexible, and it has these long rails because we can move the antennas around. Kind of not going to explain that today, but just in general, the VLA you can see is on a lake bed essentially, and surrounded by mountains, and that's important, and we'll come back to that later in terms of why would you build a telescope in this kind of remote place with certain characteristics. This is the Very Long Baseline Array. This is 10 antennas distributed across the US, with an antenna in Hawaii and also an antenna on St. Croix in the Virgin Island. Fundamentally, the resolution of these instruments, the angular resolution on the sky, depends on the separation of the antennas. And so you can have all the antennas together, like at the VLA in New Mexico, and you just fiber the signals back. It was waveguide originally. If you want more resolution, you move the antennas further and further out. Eventually a river or a mountain or something gets in the way, and it's not simple. And certainly, 20 years ago, it was not simple to bring those signals back. So what we actually do is in each one of these antenna stations, we have a very high-speed digital recorder. Used to be tapes, now it's just disk. And to make sure that we can line up the astronomical signals to correlate them, we have an atomic clock at each one of these stations, and they write a very accurate timestamp into the data stream We bring all the discs or tapes back, we'll kind of line them up on the basis of the clock signals and then hit play. And then it looks like they're all coming out of a, a bank of fiber or something like that. So this is very long baseline interferometry. Interestingly, these days, we do fiber the data back. We can't fiber our full data rate back at the moment, too expensive. But, they are sort of connected element in that sense. But it doesn't work the other way. We can bring the digital data back, but I'm sending the signals back and forth on commercial networks. So I can't send that time standard out because you're passing through other people's oscillators in some sense. You can't line up the signals that way. So you have to have the atomic clocks out there. So we haven't removed that requirement. And that is actually very annoying. This is the Atacama Large Millimeter and Submillimeter Array. This is at 16,500 feet in the Andes Mountains of northern Chile. So, your cell phone is receiving at a few gigahertz or something like that. This telescope observes at a few hundred gigahertz. And so when you go up to those frequencies, water vapor and oxygen in the atmosphere absorb and distort the radio signals as they come down. So you've got to be somewhere that's high and dry. And so this site in northern Chile is pretty much the highest and driest place on Earth. The South Pole is actually probably higher and drier, but hard to work in. So this is a telescope that was built. This is the ALMA telescope. This was built in the 2000s and early last decade. And this is the Green Bank telescope. This is a 100-meter diameter telescope. It's a single pixel. Those other images, those other telescopes I showed you were interferometers. They build multi-pixel images of the sky. Green Bank is like having your cell phone camera is one pixel. It's a great pixel, but it is one pixel. And so you don't really image. It's much more about spectroscopy and detection and other things and so on. So this is about 2.5 hours drive from here. And you notice again, it's in a valley surrounded by mountains. That's the second clue. So what is in a radio telescope? Typically, there is some kind of antenna. This is one of the ALMA antennas. The radiation from the sky comes from the right, kind of bounces off the main dish. Can you see my mouse? Yes? Yeah. Bounces off this subreflector and then down through this hole in the surface of the dish. In there is a cryogenic system, a DOA. And so what we do is we cool our electronics down to 10 degrees above absolute zero and so on to improve their sensitivity. And we typically get a factor of two out of doing that. So it's an important thing. Although running these cryogenic systems in the desert on a mountain and so on is quite difficult. It uses a lot of power and it's a lot of complex electronics in the field. Inside that DOA is something that looks like this. These are the different receivers. And so you can kind of see these sort of circular cartridge-looking things here with little mirrors on top of them. Those are the actual receivers. And so what we do is, if you want to look at a certain frequency, you kind of point that receiver through the optics, and that's how we're receiving it from the sky. So as I said, you can see kind of the container this is in. That's the cryogenic DOA that we have the receiver in. After this, the signals are digitized and sent back to a correlator. So in the case of ALMA, for example, we have 66 antennas, and each of those antennas is producing about 120 gigabits per second. So we optically fiber that back. We have about 1,000 kilometers of fiber up on the ALMA site, which is only 10 kilometers wide, and we send it back to this correlator. So these correlators are supercomputers, maybe not in the sense that we kind of traditionally think about it. They do one thing, which is to cross-multiply the signals, the digital signals from the antennas and every baseline pair, basically. So, if you add it up, it was a 17 petaflop machine, and it was built, started building in 2004. So it doesn't really traditionally appear on any computing list, right? Because it doesn't, in practice, it can't be used to balance your checkbook or anything like that. But, it was quite impressive in its time. It still is. We're about to start building a second generation one. So it's inputting these 60, 64, 66, 100 gigabit per second links. This was all built with 2004 ASICs. It was about 150 million processors in this thing. So it sips up at the high side, and that's another problem. You've got this very high-speed digital computer up there that generates a lot of power, a lot of heat, and you're actually up at 16,000 feet, so you don't have a lot of molecules to bounce off it to cool it. And so these are the sorts of challenges. This is how our application tends to drive things along. And this is what we do. This is the radio sky. So it kind of looks like the night sky. You know, if you glanced at it, you'd say it's a night sky, but it's not. You know, when you look at the night sky, you're typically looking at stars that are within, you know, a few hundred light years of the Earth or something. Nearly everything you see in that diagram is a galaxy at a much greater distance. And so that's one of the big differences between optical and radio astronomy. We are typically looking at radio emission from galaxies, not from stars. And so all this sort of background star-like looking thing, these are all galaxies. Sometimes these galaxies are sort of interesting. They have these large lobes. And then there's kind of this pattern that runs left to right and up and down here. That's actually the plane of our galaxy that also gives off a lot of radio emission. And so, you know, this was the joy of radio astronomy as it was developed in the last century or so, is really kind of looking at the sky in a different way, and you're kind of looking at objects in different sort of energy regimes. And so there have been lots of great radio discoveries, the cosmic microwave background, quasars, gravitational lenses, masers, dark matter, et cetera, et cetera. And so, you know, the hopeful radio astronomy student can get a Nobel Prize. It's been very productive over the course of 90 years now. So just to give you some examples, this is the radio emission from the center of our galaxy. The galaxy is kind of tilted, you know, sort of top left to bottom right. What you're looking at here are supernova remnants. These are the radio, it's a radio emission given off by stars exploding. The bigger ones are older. In that sense, the shock wave is moving out further. There are these interesting structures you see here, sort of these linear structures. They're magnetic field bundles that are somehow or other moving through the disk of the galaxy. We can blow that up. We can increase the size of the array and drill in on some of these paths. If you do that and you continue to do that with a VLA increasing in frequency, eventually what you can get to is this white dot here. And, you know, so that white dot is right down in the middle of all of this, and eventually we can resolve it down to find that thing. And that white dot is the center of our galaxy. There is a supermassive black hole sitting there. There are stars falling into it. It gives off radio emission because of that. And so recent press releases you see where people have continued to use VLBI, long baseline, to really get in there and try and see the shadow of the black hole. You know, this is sort of the progression of radio astronomy in terms of technology over many years. This is a nice ALMA result. This is looking at a star about 140 parsecs away, so 300 light years away. What you're looking at here is sort of the dust that the dust and the gas that the star forms around. And so you can sort of see the star in the middle here, and then you see these channels around in the disk. This is where planets have formed, and they basically eat the dust as they start to orbit and gravitationally, you know, sort of attract all of the dust and the gas material. The interesting thing with this one is the scale is very different. This yellow dot in the center here is the size of our whole solar system. So this is much larger than our solar system. And so, you know, really what you're looking at is the birth. The star is probably not too different to the sun eventually, but you're looking at sort of activity on a much larger scale. And this is the famous black hole shadow in M87. This is looking at one of those radio sources in the background that I showed you. If you can get enough resolution on it and you look down in the core where the supermassive black hole is, you can actually see there's this disk of material. The theory here is the disk of material is sort of the orange stuff, and what you're seeing here is the material, basically the light that's been eaten by the black hole that sits in the center of that disk. Although the jury's not completely out on this, actually. So, you know, that's what we do. And, you know, those are sort of some of the typical results. As I mentioned, the technology is, you know, largely digital technology these days. And so we've had a long history over the course of the, you know, radio astronomy's progression since the 1930s of situating radio astronomy instruments in sort of remote or very highly controlled environments to sort of minimize their impact. As I said, if your 1-watt cell phone is a very bright radio source on our scale, then your refrigerator is much worse, and your television and all of that. So even by the 1950s, when the US was building a lot of telescopes, or starting to build more telescopes, it was already very apparent you had to be in quiet areas. And so there are areas like where Green Bank was, the National Radio Quiet Zone. When the VLA was to be built, they did a US survey to find a quiet place. And you really do want that kind of general idea of being distant, and you want to be kind of surrounded by mountains is good. But of course, you know, that's set against the change in all of us, the change in society in terms of interfering technology. Cell phones in the 90s, and now it's everything. Bluetooth, Internet of Things, and satellite constellations and so on. And it's a very complex problem. You know, it's very complex for the interferometers. It's not as simple as, you know, radio source, radio telescope, you can work out what the impact of A on B is. What you've got to deal with is the fact that the radio telescope is operating very complex. You know, it's looking in a certain direction. It has all kinds of natural oscillators in it and so on. So exactly how it will pick up and see this radio source is very complex. There's also bounces off other objects, there's multipath problems, all of that kind of thing. So in general, this is an area that we don't really deal with. The forward gain of the antennas is so strong, you know, 80 dB, I think it is for the GBT, that we are really looking in that direction. And a local bounce off something can impact us at some level, but we tend to try and work around it. You know, we have not got very aggressive about trying to deal with it. That's probably a mistake, actually. So this multi-dimensional problem in frequency and time and space and polarization and so on is a problem for our very highly sensitive radio astronomy receivers. We also, there's two types of observation we do. There's sort of what we call continuum, where we're looking at a slab of spectrum, trying to catch as much energy as we can. And so some of those images I showed you are continuum observations. You know, their sensitivity depends on how much clean bandwidth we were able to observe, versus spectral line, which is where, if you look at atoms and molecules, they emit at a very particular frequency. And so if GPS is sitting right on your frequency, you are screwed. There's nothing you can do. And so what we deal with is trying to find the balance between, you know, what we want to do scientifically and what people are doing in society. And so what happens, for example, with GPS, you know, the GPS bands, is that you just give them up. That we don't do certain types of observations in those bands anymore because, you know, the societal need is strong enough. And so, you know, there is this sort of general interplay that goes on between the science community and the people that are responsible for this, which is largely the ITU, the International Telecommunication Union. So, you know, I think all of you in the room, or many of you in the room, probably deal with this at some level. You know, the frequency space between sort of 0 and 270 gigahertz, I think it is at the moment, is allocated. There is an international agency that deals with it. There is the FCC and the NTIA in this country that deal with it, and allocations are made. And so deep down in this chart, you know, there are allocations to radio astronomy. But this is an imperfect system, right? Because technology changes. And so we're all kind of aware that there's a lot of interest in sort of gigahertz and hundreds of gigahertz transmissions and so on. Now, there's essentially very little regulation at that point. It was all kind of focused around a few gigahertz because that's where all the action was for so long. So this table is good in the sense that it's, you know, it is a way for us, the rules of the road, we can all operate on the road at the same time. It doesn't necessarily support scientific endeavor. So coming back to this point, if you have a radio telescope and some kind of transmitter, spectrum protection is critical if you're sort of relatively close. And so tens to hundreds of kilometers. I want to observe in this band, you guys are transmitting in some other band. As long as it's relatively clean and separated, we're probably okay. But that falls down when there are multiple applications and multiple users, multiple transmitters and so on. So as I said, typically what we have done is we seek geographic protection. We put our radio telescopes in remote areas surrounded by mountains because you get a lot of natural shielding that way. So that worked pretty well for a few decades, except that then satellites came along. And so then you're looking at a transmitting source that's anywhere between a couple of hundred kilometers and 37,000 kilometers above you for geostationary sources. And so that is a problem. And there are certainly applications like GPS where, you know, there's basically unusable band for us now. We can't really easily observe. But even then it was not so bad in the sense that, you know, a lot of the satellites are quite directional by design. And also, as I mentioned, if you're not looking at the satellite, if the satellite is over there and I'm over here looking over there, you know, the impacts might be quite tolerable in some ways. Well, of course, that's sort of blown out of the water by constellations. And so there is this amazing thing going on in the country well, not in the country, around the world, about building these satellite constellations. You know, and the goals initially were to sort of, you know, produce global internet, which is, you know, an amazing goal, really. More recently, it's now, they want to be able to use, they want to text, your phone will be able to text one of these satellites, very low bandwidth communications and so on. So that's all cool, but in some sense, each one of those steps represents a bit of a challenge for radio astronomy. And so, we've been sort of keeping an eye on this. This has not been a secret or anything. These companies have been coming at us, developing for decades, really. There have been some long-standing issues. Iridium was very exciting for us back at the turn of the century. GLONASS is the Russian GPS, the geostationary belt. We have observations which, we try to avoid the geostationary belt because it's got a lot of RFI in it at some spectrum. So we have kind of dealt with this. And, I think as a member of society, you've got to find balance. That it is not appropriate for radio astronomy to say that global internet is impossible, right? If you stand in front of that, they're just going to go over the top of you. You have to find a way to work, and you have to sort of technologically assess the challenges. These new systems that are being discussed, like Starlink and OneWeb, and Kuiper is the Amazon one, they are talking about more transmitting objects. The most amazing numbers are like, if I was standing at the VLA site, there would be 300 Starlink satellites above me. Most not looking at me, not transmitting in my direction, but that's quite amazing. So we kind of deal with that, but you have to sort of deal with it realistically. There is no business model on Earth that's going to support hundreds of thousands of satellites in the sky. I don't really believe that's possible. We'd all have to have our own satellite, basically. So, in some ways you have to sort of deal with the technological impacts of it, deal with the societal benefits of it, and the answers are technical. And so we continue to kind of look at that. In a lot of cases, these organizations are transmitting in their assigned bands. And so in some sense, why do they have to deal with this at all? Well, what it kind of comes down to is sort of the edge cases. So, there's one place in particular where we have a radio astronomy band right next to a satellite downlink band. And so if you can build a filter that looks like this, well, life is good. You're very clever. And we can build filters that look like this. They are wickedly expensive. And so that's what you kind of get into, is that in reality, they build filters that look like this. And so the very low out-of-band emission here, the roll in the filter here, puts just enough signal into our band that violates the ITU regulations. And so they then can't get an operating permit. And so they do analyses that look like this, where, given their transmitting characteristics, we look across the whole sky, and they kind of admit that, if you look down here, essentially at sort of the band of satellites, given the way their orbits run, there's a place where the observations are not going to work very well in their band adjacent to their transmit band. Most of the sky you see is sort of blue, and there's not really any data loss and so on. So we produce a lot of diagrams like this, and we analyze what the impacts are to the radio astronomy mission. And on the basis of this, we make decisions about what kind of permit and what kind of use of the system we're going to collaborate on. So the consequence of these analyses, for example, is that SpaceX and OneWeb agreed that they couldn't use their lowest channel of 250 megahertz. So that's difficult, right? We all know how much they're paying for that spectrum, and then they can't really use it because they're rolling slightly into our band. And so I think that, that presents a challenge for them, and I kind of look at it and I don't think it's particularly appropriate either. We're interfering with commerce for a band that honestly I don't think, we don't use in any particular way. And so this is, again, where this sort of collaboration between what do they want to do, what technologically is possible, what do we need scientifically, and so on. This is where we kind of entered into collaboration, in particular with SpaceX, to explore it. So we started doing tests. This is a SpaceX user terminal. This is the uplink in some ways. And so you can see the VLA in the background there. And so what we were doing were tests of, we would sort of set this user terminal down, Starlink would communicate with it. Their system's pretty impressive. You get 300 megabits per second to this antenna. Pretty impressive. But we would look at the interference associated with both the downlink signals to eat this guy, to feed this guy, and also the uplink signals, which are in a different part of the band, as it turns out. And so, we started doing experiments last year. We did the same thing. That's, if you can see the little white dot there, that's the 100-meter Green Bank telescope in the background here, and this is the user terminal, which is only that big, so this is not to scale. But what we were doing was moving these user terminals around with respect to our radio telescopes. We'd do some data transfer up and down in the Starlink system, and we'd see what the impact on our observations actually was. And so what does that look like? Here's two examples. These are two baselines. So this is two pairs of antennas on the VLA, frequency across the bottom and time running upwards. And so what you see, the little yellow sections there, that is the Starlink system trying to find someone to talk to on the ground. And so what we're actually seeing is, SpaceX's system trying to communicate with the user terminal on the ground. And we knew exactly where, and we knew exactly how long and so on. So it's pretty straightforward for us to go back into our signals, and we were sort of, I think, just observing a background source in a random piece of the sky. It's easy for us to go back and look in our data stream and see, could we actually detect the satellite? And to be honest, it was hard. We had to really know exactly where they were. And so we started doing these tests, and you sort of did different responses. One of the interesting things in this diagram is that, as I mentioned, this is essentially a triangle of antennas. And the one on the left is this baseline, and the one on the right is this baseline. And you notice they didn't see each other's signals. And that's sort of interesting. The antennas are looking in the same kind of general region of the sky. One pair of antennas saw a satellite over here. A different pair of antennas saw the satellite over here. And so what you're getting into is this complex interaction between the way we observe and how these guys transmit. And so eventually you get to this sort of situation where we can model what we should see. And the results are very consistent. So there were no particular surprises. And so up here, we're in Janskis here. So you see we're kind of getting up to about 10 Janskis here, which is still less than the signal that we all generated on Pluto together. And so it's significant. But it's very brief. These satellites pass across the antenna in sort of 90 seconds or something or other across the site. And so we did a lot of observations. The results were that the interference from the satellites was kind of predicted and seen. We could detect them. It's very different for something like Green Bank, which, as I mentioned, is a single pixel. It kind of eats everything. And so it is a much more sensitive radio detector that way. The downlinks were detected, but the system doesn't saturate. And that's one of the problems we have, is a very strong interfering signal kind of saturates the system. You lose the linearity in the system, and you can't do scientific observations. So the result here was that for the interferometers, for the VLA, there was complex interactions with no saturation. The user terminals, which are 3 watts, I think, are not much worse than your cell phone, 3 times your cell phone in that sense. And so they were not particularly problematic. Once they're actually not in the line of sight to the radio telescopes, it was okay. So just in general, these results were consistent with the models. We put together some fairly complex models to describe what we were getting, and it all kind of hung together. But, thinking about the future, if there are more satellites, there are different satellite systems, they're all transmitting on different things. This whole thing about connecting to cell phones, which kind of appeared, we started to think about, is it possible to actually really coordinate with these systems? So can we have sort of spatial and frequency sharing schemes? Can we actually connect the real-time system so that the real-time system that's driving our antennas actually knows what SpaceX is doing? And so if there are antennas flying, they're satellites flying over the site, and we're not observing at that frequency, do we care? So these are the sorts of ideas that have been floated around. And the goal here is really to preserve our protected bands. If we can control their interference on us better, we can do more science. But it also potentially opens up some lost frequency for us, and it opens up the bandwidth for them. It might be possible for them to get back into that lowest band that they had to not transmit into to meet the ITU regulation. So we've been underway with a research program with SpaceX, and we've got this kind of concept of radio zone multiplexing. So we essentially know what each other are doing, and we kind of avoid each other. So as the satellite kind of flies over the site within some radius, it goes into a different, the satellite goes into a different mode of transmission. It avoids certain channels, or it basically moves between set channels on a time grid that we know. And so we can then teach our correlator to know about that and blank all of the data when the satellite is on. So we actually did tests of this in the middle of last year, and it worked pretty well. So that's great. It works for SpaceX with 2,000 satellites. Will it work for 5 companies with 10,000 satellites? And I think that's kind of, the challenge ahead for us. And these are just sort of what the results look like, where this is sort of, again, frequency along the bottom and time up the left-hand side. And so you can kind of see on different baselines and in different channels, we made the prediction of what we should see, and we can extract their signals out of the data and so on. So this was very successful. And, we've had a very good collaboration, I would say, with SpaceX. By and large, in a corporate sense, they're sort of aware that they could cause a lot of trouble and we could kind of stop them in their tracks at some level. They don't want that. But I do think there's a genuine sense that they want to be kind of doing the right thing and they can get the job done. If we can work around each other, then we should certainly do that. So in terms of this sort of spectrum sharing, the negative impacts to radio astronomy are growing. There are more companies and more satellites and so on. We're trying to define this constellation standard interface and interaction that could be adopted by the satellite constellation industry as sort of a standard. And that would, I think the advantage is it gets us out of their hair, basically. If they adopt this kind of technique in above radio astronomy locations around the world, then they simply we will not be interfering with each other, and so that's a better place to be. The testing we've done so far in terms of their real-world impact to us, at least Starlink's real-world impact to us, is pretty consistent with our models. As I mentioned, the interferometers are less susceptible to satellite interference. In future, there's other mitigations that can be considered. As I mentioned, a dark secret of radio astronomy is we don't tend to deal with interference. We don't try and recover it. We don't try and do a lot. If it saturates the system, we have to put in a filter or something like that. But generally, we kind of work around it. And we are sort of approaching the point where that will not be possible. And so thinking about ways to design our systems in future is an important part of dealing with this problem. And so just in general, we think it's very important to explore the impacts. Part of what you all fund astronomy for is for us to solve problems. So just sitting there whining about it is not good enough. There are technical problems here to be solved. And so that's kind of the challenge that we're trying to rise to. We have plans for the future, and in potentially the impacts of these satellite constellations need to be noted on these plans. One is that some of those telescopes I showed you, we want to kind of combine those and essentially increase by a factor of 10 the number of antennas we have. So this is the next generation very large array where we would take the current VLA, which would be sort of on the scale of about this guy, build this 5-arm spiral, continue that spiral out into Mexico, Arizona, and Texas, and then combine it with the antennas on the VLBA. So this is, the VLA is 227 antennas. This is 263 antennas distributed essentially across our sector of the Northern Hemisphere. And this is the type of science you can do when you build an array like that. You can actually, I showed you that star forming region earlier where that yellow dot in the center was the size of our solar system. With the NGVLA, we can actually get down to terrestrial scales. And so what you're looking at here is the formation of planets on the scale of our solar system, on the scale of our planets. And with our telescopes in spectral line mode, we can actually look at molecules. We can look at the components of what's forming these planets. And so you can see water and you can see organic molecules and so on. So with these sorts of instruments, 15 years from now, we can actually watch planets forming around nearby stars, and we can measure the chemistry of the gas nebulae that are collapsing to form those planets. And it gives you a lot of information about the formation of life and what the opportunities are for life around some of these systems. So this is one of the science goals of NGVLA, and there are lots of others, but this is the cool one. Another thing we've been doing is getting into radar. We built a radar transmitter for the Green Bank telescope, and at the moment we're receiving it with the VLA and the VLBA. So this is a 700-watt system. I'm pretty sure there's more than 700 watts sitting on the table in front of me there right now. This was a pretty low power system, but we had a lot of collecting area to receive the system. And this was one of our first pilot observations. This is actually the Apollo 15 landing site. Some days we convince ourselves we can see the lander in this image. And so you can end up with like 1.5 meter resolution pixels from something like this. This was the Tycho crater. Again, this is 5-meter resolution and so on. So moving forward, both in terms of the environment we're seeing from industry, but also our own environment, it's more complex. We have plans to build essentially a space domain awareness system where we have a transmitter on the GBT. We transmit out of that guy probably 500 kilowatts or something like that. So we're transmitting 500 kilowatts out of the National Radio Quiet Zone. That's a thing. And then you bounce the signal off the target, and it can be a satellite, it can be an asteroid. You can do sort of solar system research this way. You collect the reflected signals in the sort of multi-static array configuration, and then you rebuild some image of the object, be it a satellite or an asteroid or something like that. So we are headed strongly in this direction. The design of that transmitter is underway, and hopefully one day, some years from now, we'll have this high-power transmitter at Green Bank and being received by the NGVLA. So just in general, I've sort of given you some sense of what we do and how we see the sky. And a lot of the time, the sky is like this. It's some antennas, and you're looking at a quiet sky, and we are really sort of fundamentally doing scientific research. And this is why we build these antennas, and this is why, there is international frequency regulation and so on. I noticed actually this morning, this one is not perfect. There is a plane or a satellite trail in the middle of it there. But a lot of our astronomy is still like this, and this is why we go to these remote sites and so on. But the future is changing, and we certainly need to be able to deal with things. So this is a video. What I'm about to show you is a video we took at the VLA site a couple of weeks ago, actually, and it was just kind of cool, but it kind of gives you a sense of what we actually deal with in the real world, right? There's lightning storms, and you see all these planes whizzing over, and then you see some satellites whizzing over, and amongst all of that, we are still doing our astronomy. And so in some sense, that's what the interference of these constellations is going to look like, that we are going to have to continue to develop technologies, develop ways of processing the data to be immune to the impacts of some of these other sorts of effects. And that's really where all of you come in, that the digital work that you're all doing and the types of technology you develop, ultimately, we are an incredibly interested customer and hope to work with you more in future. So thank you.
Sit on.
Testing. Yep. Testing.
Thank you. Are there any audience questions for Dr. Beasley? Are there any plans to do radio astronomy from space, so something like a James Webb, but instead of optical radio astronomy?
Sure. So, I mentioned this idea that we do interferometry, and the resolution of the image depends on the separation of the antennas. So we have built systems in the past where we had a radio antenna in orbit, and we, again, it has an atomic clock on the spacecraft. We capture the data and send it back down, and we've used that like a sort of moving, distant antenna. It's kind of hard to support in long term. Eventually you run out of propellant and so on. There are so we have done some of that. There have been 2 major experiments doing that, and then there's a lot of interest in the far side of the moon. And so if you kind of think about the Earth-Moon geometry, here's the Earth, and it's transmitting a lot of stuff, and here's the Moon. There's a sort of cone on the Moon where you can't see any of this Earth-generated interference. And so there's a lot of interest in doing work, in that region. That's hard, getting to the far side of the Moon, doing something, not polluting the environment, getting the signal back, all of that is hard. So there's some interest in it, and there are some scientific goals that might be better done in that environment. But our telescopes are heavy, and getting them into space would be bad. So yeah.
Yeah, good morning. You commented on trying to work out, I guess, a coordination arrangement with the NGSO or the LEO satellites. So for for the geostationary satellites, that they're using the same spectrum, or Starlink is using some of the same spectrum as and they also have rules about, especially when they're going around the equator, the LEOs are going over the equator, that they're supposed to turn off or not radiate certain bands because they could be in the line of sight of antennas or terminals that are talking to geos. Or have you consulted those rules, or?
No, it's the same, but it is the same general idea. That's right.
Right.
So obviously the geostationary ones don't move, so it's kind of a fixed problem. Once you get it kind of set up, you're kind of done. There are certainly already regulations on some of the orbiting satellites. Yeah, when they go over some part of Southern Africa, they do not transmit in some band because there is something receiving there or something like that.
Right.
Really what you're talking about though is kind of a change of scale. I mean, if you believe the models, and as I said, I don't really believe the models, but if you imagine you're standing at the VLA site and there are 300 SpaceX antennas above you, so we can coordinate with SpaceX and probably do something meaningful, and OneWeb, and Kuiper. And then, of course, the reality is the Chinese are going to build their own system as well, and they may or may not play, right? And so that's where you've got to kind of attack the problem from multiple things, try and coordinate with them, trying to find standards and so on. But then we need to build hardened systems. We need to be more robust to it.
Right. But I guess there's like a set of rules that are in place, kind of like a standard for NGSO and geosatellites. And it seems like that a lot of those could be applied. So that way you would.
Yeah, but the rules aren't great, right? In the sense that, if there is an ITU international rule.
Right.
And then the FCC and the NTIA produce their sort of local version of it. In reality, commercial companies have a lot more sway in that process than the scientists do.
I agree with that.
Yeah,
I agree with that. But it's like it's a basis, though. If you're trying to get a standard and trying to make it easy, then
and there is some interest in that. So I think we're trying to define a pragmatic standard, and then we will try and operate it through those channels. Yeah.
Thanks for the talk, Tony. Well, from the Hat Creek Radio Observatory. As we start putting cheaper and cheaper electronics into space, is there ways in terms of regulating the RF leakage of such electronics in space, or is there thoughts on doing that?
Well, if we go all the way back to the diagram, this is going to be slow. If we go back to the FCC diagram, I mean, there are already fixed, there are already fixed bands for the uplinks and the downlinks of space-based technology. So any of you that are involved in CubeSat experiments and so on, the hardware that you use is already coupled to some standard about what you can and can't transmit down in. So interestingly, it's not necessarily the job of the end user, the application developer to do that. I mean, if you have some idea, I believe, if you have some idea of something you want to do in a CubeSat, you're going to buy a standard CubeSat from someone who's going to have standard comms in it. Those standard comms are developed to be consistent with these rules and those standards. So unless whatever your application is, unless your experiment is producing radio signals for some reason or something like that, and that could be leaking over into one of our bands, generally, it's not so much of an issue. It is like in the constellations, it's just the volume, it's the number of them, and you're getting these complex signals coming into the side lobes of the telescope and so on. So I think if you, in general, for these applications, you're buying standard communication systems to go in your spacecraft and so on, usually it's okay. But then, as I mentioned, that by and large, over the course of 20, 30 years here, we've sort of got to the point where it's very hard for us, and we generally don't go hunting for signals around, downlink bands, because you're just going to get crushed. So this is a little bit of a problem for us in sort of that radio galaxy astronomy sense. It's a big problem for the SETI people, because they're trying to be somewhat agnostic to what we're actually looking at. And so if you're anywhere near 12 gigahertz these days, right, DirecTV is blasting you. So it's not a particularly productive place to go hunting for radio astronomy either. So just in general, I think, if you're using standard components and you have space applications, probably you're not part of the problem, certainly for one CubeSat or something like that. If you put up 10 million CubeSats, that might be more interesting for everyone. But if your application somehow has a non-standard transmitter on it because you're doing something, I don't know, Yeah, that'd be something we'd be interested in. But again, you ultimately have to have an FCC license for it. There is a well-defined review process. We would get to write a nasty letter about you, so it would be okay. That said, coming back to the previous question, our nasty letters are not that nasty, and in general, FCC perhaps doing the job that it should is trying to push commerce and move things through, and so we fight a lot more than we win. Yeah.
Got time for one more question.
Hello. So yesterday we had a talk with the director of DARPA, and she talked about their project Space Bacon, which is designing a reconfigurable terminal to allow the different constellations, LEO constellations, to communicate with each other. And I'm with Arizona State, and we're working on that project there. And I was wondering if you guys had thought about interacting with a project like that at all ever, where like you talked a lot about how you've worked with Starlink, but something like that could allow you to communicate with more, interact with like more different companies that have constellations out there.
Sure. So we've worked a lot with SpaceX, with Starlink. We've also interacted with OneWeb. We haven't done any testing of OneWeb yet, and Kuiper is further back on the track in some ways. And so, yeah, I was at Stephanie's talk yesterday, and I kind of looked at some of the things she was doing, and it's very difficult for me to assess the reality of it in some ways, right? And you know, you talk about building a network which is merging those other networks. So it has a cool name and there's a nice diagram, but actually what it means in terms of technology and what are they actually doing, I don't think it means anything in space. I think it's more about technology on the ground coordinating, you know, the transmissions from these constellations, or not, I don't know. So DARPA's hard, right? By definition, it's hard to sort of roll up to DARPA and say, you know, what are you up to? And get some answer out of it. So I did note the talk, and I noticed there was another thing on there where she mentioned correlator systems, and I was thinking, what is that? So I absolutely take your point. We probably should spend more time looking at exactly what technologies are being developed there and so on. But to the general point, and maybe kind of the broad takeaway here, is that once something like Starlink is permitted and is underway, we tend to try and just stay away from it. Right, or find some way to coordinate it with it largely. You know, one of the interesting things is that I guess it's a funding issue. There's an enormous difference in our development cycle time relative to DARPA. You know, you heard yesterday that like it's like 3 years and you're dead or done, right, or whatever it is. So we have National Science Foundation funding. Just in general, the development of one of these telescopes takes 25 years, typically speaking. And so there's a little bit of a timing problem there, is that we can sort of spot the environment, try and build something that deals with that. There'll be 8 cycles of development here. You know, SpaceX will be transmitting at 40 gigahertz by the time we're finishing. So that is a challenge, but point taken, we absolutely, I was intrigued by her talk and I should follow up on that, yeah. Okay.
Hello? Okay, so before we let you go from stage, so last Sunday, I learned what a challenge coin is. I assume you know what a challenge coin is, right?
A what?
A challenge coin?
A challenge point, no?
A coin? No? A challenge coin?
No.
I see. So you're not from the US like me. So I learned about these on Sunday. So I'll let someone else educate you, but they're basically tokens of appreciation in a sense. And we have a rare set of 3 challenge coins for our distinguished keynote speakers. We'd like to present you with one of those as thanks. And with that, I'd also like to ask for a big round of applause for Dr. Beasley. And if you have some clueless Europeans at your table, you can explain to them what those coins mean, like I learned on Sunday.
Is it a Bitcoin?
I think we have a break now. It's a break now, right?
And next we have the GNU Radio project talk by Josh Mormon.
All right. We got a mic? Good. All right, good morning, everyone. So this morning, I'm going to try my best to represent the state of code development across GNU Radio, all the amazing work that goes on across the community for more stable, maintainable, and feature-rich releases of GNU Radio throughout the year. And then also kind of a path forward, go through the state of GR 4.0. And we're also going to get an update on the Volk project from Johannes and Michael as well. So my name's Josh. I am a research scientist at Peraton Labs and one of the maintainers here at GNU Radio, and heavily involved in the 4.0 development, which we'll spend quite a bit of time looking into in this talk. All right, so it was a busy year for GNU Radio releases. We started off after last GRCon working towards GR 3.10. And 3.10 included the GR PDU module, which took a lot of out-of-tree work from Sandia and brought that in as an official in-tree module. GR IIO, which brought in support for IIO devices from analog devices. And we got a lot of support in upstreaming that from ADI. And it also brought in this custom buffers feature, which we've talked about a lot. This is a feature that streamlines the data movement in and out of accelerators and makes it much easier for GNU Radio to work in these heterogeneous environments. And another feature that really, this is the one that caused us to tick up the API revision, is the move from log for CPP as our underlying logging library to SPD log. And we have Marcus to thank for that work. So we were able, in 3.10, we were able to get this into the Ubuntu 22.04 distribution. So if you have Ubuntu 22 and you type in apt install GNU Radio, 3.10 is right there installed on your system. So that we have Maitland to thank for that, who is our Debian maintainer, who's right over here. So give Maitland a round of applause. So we'll talk a bit more about packaging in a few slides, but there's a lot of work from people behind the scenes that get things packaged in a way that just makes it so much easier. And then throughout the year, we had several maintenance releases, and we have Jeff Long to thank for this, who is not able to join us this year. But Jeff Long is our release manager, maintainer that gets things out on time and does a tremendous amount of work. So more recently, the new Sketch project, which we've talked quite a bit about in the last couple of years, moved into the main repo as the Dev 4.0 branch. So that is our path forward for development towards GNU Radio 4.0, which we'll spend more time talking about. And just before the conference, Jeff put out our 3.10.4 and 3.9.8, which are our latest releases, which you can grab and stay on top of things. So 3.10, already talked about a bit. It is a much smaller, what we call irritation factor. So 3.9 and 3.8 brought in some heavy changes to GNU Radio. We went from Python 2 to Python 3 in 3.8 and some other big CMake changes. And then from 3.8 to 3.9, we brought in PyBind 11 instead of Swig. So those changes, if you're an out-of-tree module maintainer, those caused you to have to do a very non-trivial amount of work to get up to date. The change to 3.10 was a much smaller step, so it's probably unlikely that specific change caused big problems within your out-of-tree modules, and that's our stance going forward. That's where we want to keep things, is make it less irritating to move GNU Radio forward. Only change things as necessary. Another thing I want to note here is for this 3.10 release, 92 unique contributors. So a lot of people contributing directly to the GNU Radio code base. So what is our current maintenance strategy? So Jeff Long, like I mentioned, keeps this running like a well-oiled machine. If you have PRs to submit, pull requests, the main branch is where they go. So everyone keeps things up to date on the main branch, and then Jeff picks off the things that are suitable to go into the maintenance branches and makes those releases. So maint 3.10 is where our 3.10 releases come from. Maint 3.9 is there's no more planned releases unless something serious comes up. But 3.9 is close enough to 3.10 that we don't feel like we need to maintain 3.9 any longer. And 3.8 is bug fix only. We realize that 3.8 exists in the ecosystem. There's some out-of-tree modules that are still 3.8, but we're also not maintaining that as well. 3.10 is the path forward. And then the other thing that we'll ask is if you want to propose or you have some kind of big pervasive changes, let's look forward to 4.0 to do those. Let's use those to accelerate the progress of 4.0. And then if something is safe enough really to get back into the main code branches, then we'll consider putting that back in main, and then it can roll into the maintenance releases. All right, so again, a lot of, probably not the exciting stuff here, but our strategy for these releases, we're trying to avoid breaks in the API at this point. We're really focusing on stability, reliability. And so the main branch, we allow for these API breaks, but code that gets pushed into main that breaks API might not make, well, it won't make it into the maintenance releases. It might just sit there for a while until we accumulate enough things that break API that we need to make a, say, 3.11 release. So what's an API break? It's something that's going to impact our out-of-tree module ecosystem. It's something that's going to break your stuff. And it might be minor, and we're hoping that anything we do would be very minor breakage, but it's something we're trying to avoid at this point. So there is no current plan for 3.11. We're just going to keep putting out 3.10 releases going forward, trying to make GNU Radio more stable, more maintainable, more feature-rich. So we're going to keep this at 3.10 for the foreseeable future. Okay, so just another summary of these maintenance releases. These happen because of the aggressive backporting that Jeff does. And they are, our policy is we are doing these minor changes and keeping these rolled out on a continuous basis, on a quarterly basis. So Jeff puts out these releases once every quarter. Last one just came out. We should expect another one probably in January sometime. So just to reiterate, again, our commitment to stability as the maintainers is we want to avoid as long as possible the frustration that came with 3.8 and 3.9. Now we recognize that that frustration was necessary. We needed to modernize the code base in these ways. A lot of times you get a dependency that just becomes unmaintainable in modern distributions. It becomes, the dependency becomes unmaintained. It's hard to install across a lot of distributions. So we took care of a lot of that in 3.8, 3.9. 3.10 and going forward, we want to just take smaller steps in terms of these pervasive changes and reserve 4.0 for the big aggressive changes. So as a community, we should be very proud of the state that GNU Radio is in. We are able to make these continuous releases and keep things rolling out into the community. So just one thing to remember here is that there's a lot of people involved in the maintenance of the GNU Radio code base. There's a lot of PRs that get submitted, and the best way that we can ensure the stability of the code base is if there's people to get in and review those PRs. I would say that's our biggest bottleneck to getting features in GNU Radio is PRs sit there, and there's one or two of us that look at it. If you're in the GitHub and you see something that someone submitted, take a look at it, try it out. That's a great way to help the development going forward. Especially if it's a part of the code that you understand, you're familiar with. If it's say it's in the GR digital module and you're very well familiar with that code, jump in there and take a look at the code and provide your comments. That helps us out tremendously. So if you submit a PR, go in and review some other ones too. That's a great way to help out. If you're submitting PRs, try to keep them moving. If it's a draft, if it's not completed, if you're just putting out an idea there, try to clean those up and get your draft PRs out of there as soon as possible. And then when submitting your PRs, we have a set of guidelines about keeping the commit log clean. So just a lot of business here that helps us out big time. So one thing we want to do is we want to highlight a lot of the exciting work that's gone on in the community. And first I want to give a shout out to Clayton, who's here. Clayton did a tremendous amount of work in two particular areas in these 3.10 releases in the last year. The first was removing a lot of our dependence on Boost. So Boost has provided a lot of advanced features for C++ language, but it's a big dependency. And it also can be challenging to maintain across a lot of distributions. So the less we rely on Boost, the easier it is for us to support our releases. So Clayton got in and removed a lot of that dependence just by updating to standard C++ and a lot of other changes. And the other thing that's exciting from a maintenance perspective, Clayton got in there and fixed our intermittently failing CI tests. So we had some CI tests that would, 8 out of 10 times it passes fine, and then those other times we'd have to go in and say, oh, why'd the CI fail? Well, that test just fails sometimes. Merge, and that's not a great place to be. So now we have much more solid CI thanks to Clayton. So Clayton's here today, so let's give him a round of applause. All right, so another shout out is Bjorn Curler. So I haven't met Bjorn personally, I don't believe he's here, but took it upon himself to update out-of-tree modules across the entire ecosystem. Now, I don't know what the final number was, but I know it's dozens, perhaps hundreds of out-of-tree modules, just going to, creating forks of these, updating them, submitting PRs back to the main branches. And since 3.10 is going to be around for a long time, this is a great help to the community. So if you're a maintainer of an out-of-tree module and you got a PR from Bjorn, take a look at it. If you're able to upstream that, that's great, because we maintain CGRAN. Is it cgran.org? cgran.org, which is it's a non-curated list of out-of-tree modules in the ecosystem. And so the more of those that show up as 3.10, that's more code that people are able to use the current GNU Radio with. So let's give a round of applause to Bjorn. All right. So as far as packaging goes, there's a lot of work behind the scenes that our packaging maintainers do, so that from your distribution, you can just go in and apt install, yum install, whatever it is, GNU Radio, and it just installs. And if you look on our GitHub, there's a little badge right here. It says in repositories, and this brings up a whole list of the repositories that GNU Radio is in, the distributions. So a lot of the newer ones are updated with our latest release. And so we have our packagers to thank for that. So this is definitely the preferred way at the moment to install GNU Radio, if you can just use your distribution's package manager for Linux, right, if you're on Linux. We also, thanks to Ryan Volz, have a Conda ecosystem for GNU Radio. So especially if you're on Windows and Mac, this is the only robust way that we know of to get GNU Radio up and running on Windows and Mac. And also, he's done a lot of work in our CI to tie this in so that we can see when changes in the GNU Radio code base are going to affect building on Windows and Mac as well. So take a look at this if you're not familiar with the Conda install. If you're using Windows, or even if you're using Linux and you like Conda, take a look at it. It's another very solid way of installing GNU Radio. So it's on our wiki. For Ubuntu users, we also maintain a PPA, not as heavily maintained as it should be, but it's currently up to the latest release. And so if you add this repository, if you add the PPA, then you can install GNU Radio on Ubuntu 20 and Ubuntu 22 and you can get the actual latest version, not just what originally came with the distribution. But there is some help wanted here. This is something that if someone is really interested or involved in the Ubuntu community, not only would we like help managing the PPA, automating that, if someone's tied into that Ubuntu community, it would be nice to get these maintenance releases flowing through the actual Ubuntu main repos, if somebody has connections or knows how to do that. So Maitland keeps Debian very up to date, and the Ubuntu packaging just derives from Debian. There's a few extra steps with their tooling, but if someone knows that ecosystem well, this would be a great help to us as a community. And then, of course, there's installing from source. When do you want to install from source? Obviously, if you have to modify the code yourself, if you need multiple versions concurrently, so you want to have your own prefixes, or if you want to operate or need some features on the main branch specifically. PyBombs has gone very lightly maintained. So I know for many years we recommended just use PyBombs, and it will grab the latest, all the dependencies, manage all that. That's a very hard problem for a project of this size to manage on our own. So that's why we have really moved towards package distribution as the way to do this rather than our own managed thing. So PyBombs, use at your own risk. It is not something that you'll probably get a lot of support for when it doesn't work. So a couple of things that Derek mentioned in his talk yesterday. We are looking for help, and some of this very well could be funded by the grants that we've received and grants that we're going for. We are looking for better GNU Radio binary installers, so you can just double-click install GNU Radio on Windows. That would be great, something that would really help us in the educational communities, and also Mac OS and packaging of outer tree modules. So if you didn't get a chance to hear Derek's talk, please go back and take a listen. It's on YouTube. Also, ongoing and maintenance support. This is something, like I mentioned before, with helping out with the PRs, reviewing things. We have an issue queue. A lot of these are feature requests. It'd be great if GNU Radio did this. But there's a lot of them that are marked as good first issue. So if you're interested in making your first contribution into the GNU Radio code base, take a look and grab one of those issues, see if you can fix it. A lot of them are just very small, manageable things. So that can be helpful. And as a task, we are looking for people to step up. I think Derek said to email jobs@gnuradio.org if you're interested in taking a bigger role here. All right, and with that, I'd like to introduce Johannes and Michael, who are the maintainers of Volk, and they're going to give an update on the status of the Volk project.
Hey, good morning, everyone. I hope you can hear me. So a quick project update about Volk. Where are we currently? Well, first off, what's Volk again? It's a SIMD optimized functions with a hardware agnostic API. So you want to do complex multiplications, you want to have SIMD support, but you want to have different hardware. Well, that's where you want to use Volk. For the last year or so, we were working on relicensing Volk under LGPL, so it should be usable for more people. And we actually completed that effort lately. That's one of the reasons why we put out our latest release, Volk 2.5.2, where we already prepared a lot of things to then go to our next major release. That's what we are currently working on, the 3.0 Volk release. We decided it would be a good idea to have a major release because we changed the license. It's not a change in the sense of it's not technically breaking the API, but it's in a legal sense breaking the API. So we think it's a good way forward. But it should be easy for all of you to update because, well, the technical API doesn't change. And we will have a 3.0 release soon. Well, and then where do we want to go from there? So where to go, Volk? One of the things that bugs us is our tests should get an update, as well as our benchmarks to figure out which special implementation works best on your computer. Here we want to have more flexibility. Also, we want to have more standardized tools, and then we want to customize tests, because right now we have a one-size-fits-all solution, and it doesn't fit all cases. So we're thinking about going towards benchmark, like Google benchmark for benchmarks, and G-tests to write tests, actually. And then even further into the future, we actually want to fix our complex type API. For historical reasons, that's a mix between C and C++, and some of you might know that's one of the rare cases where C and C++ are actually incompatible. And well, that's a very unfortunate situation. It works on x86, it works on ARM, but we've received reports from other platforms where it just breaks. Well, we want to fix that, obviously. But, you know, we have to come up with a good solution. We have to implement that solution, so that will be far into the future. And, well, by the time we fix that, we will have a 4.0 release where we won't depend on undefined behavior anymore, where we will support more hardware, but as I said, that's further into the future. If you have any ideas to how to do that, if you have ideas how to, well, improve Volk in any certain direction, let us know, talk to us. You see our faces now, and that's it. Thank you.
Thanks, Johannes, Michael. All right, so want to give an update on GNU Radio 4.0, kind of where we're at. We're at a bit of an inflection point. We want to take GNU Radio forward, do things that you might not have ever been able to do with GNU Radio, but you wanted to. So why GNU Radio 4.0? You know, we love GNU Radio. That's why we're here. We're very interested in it. But it's great. It's great for prototyping, quickly getting things running on, you know, a subset of hardware that supports it. But there's some limitations, really, that we can only overcome with this big overhaul. And that's what we're targeting, is a big overhaul. And some of those things that we've talked about year after year is scheduling, support for heterogeneous architectures, ability to do distributed computing, and just the general ease of development. So then a step back one layer, why GNU Radio at all? So if we're looking at changing such major things, you know, why didn't we just team up with some other framework out there? You know, GNU Radio is not the only solution for moving samples around and doing signal processing. But GNU Radio is fully open source, actively maintained, and we have a vibrant community. And that sets us apart as a project that puts value into doing something that a lot of the other frameworks might not be able to do with the support and the broad community that we have. You know, there is no one person, there's no one organization that is holding the keys to this project. So it's a community. We have, as Martin laid out and Derek has laid out, we have an organization in place that keeps things moving in a very democratic and organized way. So there's a community, there's an ecosystem. There's a lot of things that have been invested over time into the GNU Radio block library. And so keeping that and moving that forward as GNU Radio set of blocks is very valuable. So I want to lay out some kind of pie in the sky things as to, you know, what I think GNU Radio could be in the long term. And I want to get your feedback on this. So at the end of this talk, there's a link to a survey. So really want to interact as a community as to where you think the next iteration of GNU Radio should be going. So just a few things here. One, the ability to rapidly deploy onto a large range of hardware platforms. Number two, and I'm not going to go into these in detail. Number two, a user-friendly development methodology so that someone that doesn't necessarily know anything about GNU Radio can get something deployed in just minutes, right? It's very easy to learn. 3, a large active user base. So the more people that are using it, the more people contributing, the more it benefits everyone. 4, pervasive footprint in academic courses, university labs, so we can get people kind of hooked on GNU Radio at an early stage so that they, as a tool to be able to teach signal processing and develop actual real-world signal processing frameworks. And then the last one, set things up in a way that it's supportable and more people are able to get involved and support the development of GNU Radio. So these are just some things, and I want to get feedback on what's important to you. So one thing, and this has come up in some of the talks this week, is we usually see GNU Radio as sitting in this proof of concept stage. Some people are sending GNU Radio out in deployments, and some people are using it for early simulation, but I would say the bulk of use cases are typically in this, I want to do a proof of concept with some actual hardware, do some signal processing on these blocks on my machine. So we're hoping through the 4.0 architecture, we can push the bounds of feasible usage of GNU Radio. And we can get it to where, by, say, supporting heterogeneous architectures, you can get this out on more performant platforms. And then also by reorganization of the block library, you can use the same signal processing with the blocks, you can use it in more simulation type of environments. So this slide, we've presented several times. Bastian and I laid out this vision a couple of years ago. So these are kind of the main focuses for GNU Radio 4.0 development. The first is improvements to the scheduler, but not just improvements, modularity. We don't want to try to solve the problem for everyone as to how you want to schedule your signal processing tasks. We can have a scheduler, the GNU Radio scheduler, that does it in a way that hits 80–90% of use cases and make improvements there. But for specific applications, specific platforms, there might be different ways of doing that scheduling. Heterogeneous architectures. So we've talked a lot about the custom buffers feature. We want to be able to have streamlined data movement between accelerators. And then the one that we haven't talked too much about is this distributed DSP. We want to be able to, say, instantiate a flow graph, but be able at runtime to define the resources or have it intelligently choose the resources that it's going to run on, be able to scale up in cloud architectures. And do all of this, this is almost like the fourth point, do all of this in a straightforward implementation to where the ease of development is there. It's not, each one of these things you're not having to go through weeks of training to learn how to do. So now let's take a look at kind of the current state of where the GNU Radio 4.0 dev branch is at. And then at the end, again, there's a survey link where I'd like to get some feedback, if possible, if you're willing to. So highlights, improved support for hardware accelerators. We have modular components, the scheduler. We have an in-tree scheduler, which gets over this thread per block limitation. We're able to do multiple blocks in one thread, but also modular, which is much more than that. But we also have a modular runtime and buffers, and we have some of the hooks in for distributed flow graph support. And I think there's a lot of places that can go in the future. And then we'll spend a little time looking at this streamlined development methodology, which this part excites me a lot, taking out some of the frustration of all the different boilerplate things you have to do to make GNU Radio blocks. So hardware accelerators. So 3.10 brought in this custom buffers feature, and that allows, when you hit the work function in your block, the buffer abstraction says that the data is already where you want it to be when it's in the work function. You don't have to do data movement in the work function. One thing that we were unable to do in GNU Radio 3.0 for the custom buffers was have any insight into other parameters about the buffer, because the 3.10 API, it passes in raw pointers without any information. You just get a pointer to some data, and it says put it here. With the 4.0 block API, we have an object which, if you drill down, there's a reference to your buffer object in there. So if you have an actual custom buffer, you can get information about that buffer from that buffer object. And just a quick example, I think it was OpenCL. We couldn't do the custom buffers feature in 3.10 with OpenCL because there was more information needed about the buffer. I think it was offsets. Things weren't exactly where you could represent it with just a raw pointer. So there's probably a little much detail for here, but that's kind of the motivation here. And then also, we've set things up in a way that there's multiple implementations per block. So you have one representation, this is my block, but I'm going to have the CPU version, the CUDA version, I might have a OpenCL version, I might have a Xilinx runtime version, all within one abstraction of the block. In terms of modular components, this is an old result. We've presented this several times. And Bastian, in I think it was 2019, did a very comprehensive paper on the limitations of the thread per block scheduler. There's a lot of scheduler overhead if you have more threads than CPU cores on your machine. So even just by lumping together the blocks within one thread, we're able to greatly get rid of a lot of that overhead. So that's been done. That's the current state of the entry scheduler for GR 4.0. But there's a lot more we can do with modular scheduling. It's kind of like bring your own scheduler. We don't know what your application is, but the normal GNU Radio scheduler, it'll probably do okay with your application. But if you're doing something such as, you're doing a lot of parallel packet processing, you might want a thread pool scheduler. You have a hardware platform that has a huge bank of GPUs. There might be some other parallelization that we're just not going to handle in the main GNU Radio scheduler. So, bring your own scheduler, contribute back a scheduler implementation for that. Now, distributed flow graph support. So imagine a situation where you have a rack of servers, a bunch of edge devices. Our goal is that the blocks, the flow graph that you set up, can be distributed seamlessly to these compute nodes. And under the hood, we can handle all the serialization, communication, synchronization between all the nodes that a single flow graph is going to span. That we can distribute, we can scale up. So we haven't. There was an early proof of concept of this, but there's a lot more to do here. But we have some of the hooks in place, the enabling features such as runtime modularity, reflection. There's a concept of parameters. So if I have, say a constructor parameter on my block, that's a thing that can get moved around and reflected and serialized. So there's a lot more, and we'll talk about our architecture working group, but I think this is a very interesting topic for conversation going forward. I'll skip that. And then the last point here in terms of the current state of GR 4.0 is a streamlined development methodology. So we want to make it as easy and accessible for users to do the signal processing part of a block. We don't want everyone that wants to write a signal processing algorithm to have to go through 50 steps to get it wrapped into GNU Radio. We want to get straight to that work method, and that helps. It should help bring more people contributing things into the GNU Radio ecosystem and also make blocks more maintainable. So by reducing the boilerplate through automatic code generation, we can get for free all of these kind of annoyances in GNU Radio, such as doing the Python bindings, the GRC bindings, managing all of your constructor arguments, all of the build system scripts, the setters and getters, all of those things that you end up doing over and over. Let's get that automated. So I'm gonna show a little demo of the current state of this automation. Just a couple of minutes. Let's see how much time I got. Yep. So here is I'm going to create an out-of-tree module for GNU Radio 4.0. So just a script it's kind of like a poor man's mod tool. So I've created my module. I'm going to create a block. It's just going to take a float in and multiply by a number of k. So let's pull up the code here. So the entry point for a block is this YAML file. So everything that describes this block should be defined at this top-level YAML file. So how is this going to show up in GRC? I have my parameters, which parameters are like the constructor arguments, but it's more than that. It's something that's represented in the block that can be changed in a thread-safe way. So let's set this up as a float. So I have this value k that's a float, and then I'm going to have an input port, floating point, and we're using kind of SIGMF notation for the types here. Try to make that consistent. So I have an input port and an output port. And then we're only going to define a CPU implementation for this block at this point. All right, so I'm going to set up the build script. We're using Meson, which is it's like CMake, but a much more Python interface, Python-like interface. And so that when I run Ninja, it's going to generate a whole bunch of code that you don't have to touch, you shouldn't touch. And we're going to jump right to our work function. So first thing we have to deal with is, instead of the raw pointers coming in, we have this work IO struct. So now let's grab the raw pointers out of that work IO struct. Okay, we'll grab the input pointer. We'll grab the output pointer. And then let's grab the number of items that we want to operate on. Okay, so all we're going to do in this block, stupid simple, we're just going to make a for loop, and we're going to iterate, we're going to iterate over the for loop, multiply by k. So I'm going to skip ahead a little of the coding here. Okay, actually not too much. Okay, so in the for loop, we're going to multiply by k, but what is k? K we said is a parameter that we defined in the YAML. So jump back to the YAML, there's k. So this is a thing. So let's grab the current value of that thing. And we have a little work to do on the syntax here, but this is using the new PMTF library that John Saleh talked about. And so we're going to grab the value of that, multiply. We're going to inform the scheduler how many items we produced. And that's it. We're done. We finished our work function. We're going to compile and install. And pop up GNU Radio Companion. Let's see what we've got. All right, so there's our block. So we didn't have to do any of the GRC work. That was all automated. Let's give it an input and an output. I will jump ahead a few seconds here while it does the... So I have some, just a placeholder visualization block. You can ignore this part. But we have, here we go. So I multiplied by the value 3, and there's our input signal multiplied by the value 3. So that whole thing, creating a block from scratch, took 4 minutes. So that's kind of the direction for the streamlined development methodology. The less steps you have to do, the better. The easier it is, the more people can get involved and do that. All right, so one other thing I want to bring up about 4.0 is the kernel library. So this is a little reorganization of the code. The concept is there in 3.10 in some of the modules. So like the filters, resamplers, they have this kernel namespace. What's a kernel? A kernel is inside of a block, another object like a filter that can be represented not as a block. It's just a filter object. And so we want to pull these out into their own library so that we don't have all the inter-module dependencies. And then we can wrap these in a way that they're used independently because they're just generally useful. So before we had a setup like this where, these are the entry GNU Radio modules, and then this is the runtime, and then a few of these modules have kernel namespaces, and because, say, the FFT library, GRFFT, has this kernel, filter module depends on the FFT module, and then the QT GUI depends on the FFT module. And there's a lot, we're just trying to keep things more modular, should help with packaging, things like that. So now we have the kernel library, and our in-tree modules should be fairly independent and only depend on this kernel library and the runtime. So if you have a few minutes today, please take a look at this survey. I want to get your feedback on where we're going with 4.0, what you think about it, what you would like to see, and especially that vision that was laid out, what your thoughts are on that, what's important to you. So anything related. There's some free form answers, so let us have it. So one thing that's really exciting for us as developers on GR4, there is a group that has, we've developed a close engagement with Ralph Steinhagen at the Facility for Antiproton and Ion Research, which is a particle accelerator in outside of Frankfurt, Germany. And what Ralph is doing here is they have a measurement system in this particle accelerator that's using GNU Radio across hundreds, maybe thousands of nodes. I forget the exact number. And they were interested in some features for GNU Radio that we don't have. The ability to, in a distributed way, configure flow graphs and reflection was kind of the key missing feature there. And this engagement started by Ralph informing us, hey, do you guys think that GNU Radio could do this? And that kicked off the conversation with a lot of the developers in the community, and we developed this engagement. So Ralph has his own middleware system, which is very impressive. GNU Radio is one component in this system. So the digitizer component is a bunch of different nodes, hardware nodes, that are digitizing these measurements, processing across the entire particle accelerator. And so I apologize, I'm not able to represent this project very well. Hopefully we will, next GRCon, get a presentation about this and learn all the successes and interesting feedback. But this is an ongoing thing, and it's something that GNU Radio 4.0 is helping to enable the integration of GNU Radio as a component in this overall system. So if you are interested in this project, take a look at their GitHub or reach out to Dr. Steinhagen as he is looking for folks to join this effort at the lab there. So if you'd like to get involved in GNU Radio 4.0 development or just learning more about it, join the workshop this afternoon. I believe it's at like 3:30. We're going to go deeper into that block development methodology. We're going to show some other things that we can do with the YAML file. We're going to learn how to easily make CUDA blocks, Python blocks. We're just going to go dive as deep as we can in the time we have. We also have an architecture working group. So it's all the people that are interested in discussing the next phases of GNU Radio development and features that are on the horizon. And then on Friday, if you're sticking around Friday, one thing that we would like to do is start porting some more blocks over to GNU Radio 4.0. The more blocks that we port, the more we learn about, are we going in the right direction? Do we need to change things about the runtime, things like that? So if you're around, I'll be around on Friday. I'm sure a bunch of others will be around on Friday, and would love to work on this stuff. And then if you want to install and try out GNU Radio 4.0, there's instructions on the wiki. So if you just go to wiki.gnuradio.org, search GR4 or search 4.0, it'll pop right up. So again, our architecture working group is it's a group that meets periodically. Probably don't meet as much as we should, but in the last year, we've discussed a lot of interesting features, and these discussions turn into action and turn into PRs, reviews. The custom buffer feature that was done by Blacklinks on the DARPA SDR 4.0 project, we were able to do some really in-depth review on that and get it into the 3.10 release through this architecture working group. We've talked about ways of measuring latency. So Bastian presented his approach there. We did a lot of reviews of the new sketch code base. We've had conversations about distributed operation, and there's a lot more that we need to have there. FPGA integration, PMT, PDU, John's baby there, and reflection was the latest topic about how we can better support this application at the particle accelerator. So our next call is in about 2 weeks, October 13th. We usually do it around noon Eastern time. And if you join the chat room architecture, we post the call details in there. So we'd love to see more people join in there and jump in on these calls. So just to give an idea of some of the things that, that we've been chatting about, things that we could use more info. Oh, actually, before I do that, so if you have ideas, ideas that people have lead to very interesting engagements. Chat's a great place to start, to bounce around ideas, solidify things, and that can turn into a GitHub issue, which we can expand and have a more in-depth discussion on GitHub than perhaps on chat. But once something turns into something we really think we want to do, and it's a broader change to GNU Radio, we have the GREP process, GNU Radio Enhancement Proposal. It's GNU Radio's version of the PEP that Python has. And so if the GNU Radio greps, you Google it, it's on GitHub. So these are more, it starts as a proposal for an idea, and it gets developed more into a design proposal. Once we accept it and there's a champion, and then it turns into something that we can bring in as code changes. Some things that, we're looking for input always on these forward-looking ideas. This one, which was submitted by Ralph Steinhagen, how do you make the input ports and output ports of blocks handle things that are not specific types? How do you have custom types? Like his example is they want to carry around a floating point value and a confidence interval between blocks. And we might have a block that doesn't support the confidence interval. So how do you have a data conversion that drops that or adds in a zero value for confidence interval? So we want to solve this in a very generic way. How in GNU Radio 4.0, how do we handle the lack of a forecast function and converging between stream blocks, PDU blocks? From a packaging installation standpoint, how can we have 3.x and 4.0 exist parallel? So you don't have to install both of these from source. And then there's a bunch of other things. They're all tagged 4.0 in the GitHub. Documentation, now that we have this top-level YAML, there's a good place to put documentation at the top, and now we have new options for how we can display our documentation in a versioned way. So, like we mentioned, Hackfest Friday, want to kick around 4.0. Let's start kicking the tires and porting as much as we can. And if you don't want to jump into 4.0, and if you're around Friday, let's start hitting the issue tracker. Let's try to knock out some of these issues. So really hands-on day on Friday. Anything you want to do, stick around to help out with the project is awesome. And I believe that's all that I have. So thanks everyone for listening. Any questions?
Before we get to questions, Ralph's in chat right now, and he said 200 to 300 nodes.
200 to 300. All right. That's a lot of nodes.
Yes, quite a few. Questions for Josh?
So I was wondering if I could get a little bit more clarification on what the situation was with pi bombs. It sounded like it was sort of going by the way of the dodo, if you will. But personally, I'm a big fan of pi bombs, so I'm sad to see it go. I guess my 2 cents that I was encouraged to input here is that for me, it was the thing that made GNU Radio go from completely unattainable mess to install to actually pretty consistently installable. I mean, I just reinstalled it again yesterday from source. So, I mean, I believe that there's going to be better tools eventually, but yeah.
Yeah, no, that's a great question. So pi bombs is still there. it is still maintained, but it's, I don't know, Clayton, you would say it's lightly maintained, right? Yeah, so I think it's that it works under a subset of distributions. It's not going to work necessarily on everything going forward, or new things being thrown at it might not work. So if it works on your setup, that's great. But someone tries it on some other distribution, something comes out. I don't know if all of the recipes are being kept up to date to the extent to support a broad range of distributions, or yeah, it's just that we're not investing effort necessarily into PyBombs and maintaining that because there's so many other people, there's so many other solutions for package management that as a pretty small medium-sized project, it's hard to manage that solution across such a broad ecosystem.
Hi, I'm Maitland. I package for Debian. The PyBombs issue is a kind of a precursor to packaging things in a distribution. Everyone on GitHub, you've got your projects. Yeah, make sure you're clear on the licensing so that we can share the code with each other. Secondly, make a version tag. Third, communicate what versions your project on GitHub works with on GNU Radio. That way, the PyBombs recipes can be maintained. Things can go into distributions. So my call to everyone is release early, release often, and communicate what versions work.
Got time for a few more questions before the morning break.
Hey, I don't know what it takes to do this, but I know that I've downloaded virtual machines before that come like preloaded with certain types of software. Have you guys ever considered doing something like that? Is that something that you could do?
Yeah, I believe Derek this week was putting together a virtual machine. We had it at last GRCon. The latest release is all packaged together on a virtual machine. So it's something we've done in the past, and I think that's in the works. So maybe Derek can comment on chat as to what the current status of that is, but it was definitely something going on. But thanks for bringing that up. That is a good method for distributing a quick solution. Yeah.
One more.
Hello? Oh, there we go.
There we are.
Just quick follow-up question to what I asked earlier. So if PyBombs is being phased out, what's the recommended tool for installing from source, including out of tree modules and the like?
Mm-hmm. The recommended approach. Are you saying from source? Yeah. So I would say from source, the recommended is you basically do what PyBombs does, but don't rely on PyBombs necessarily to do all of your dependency management. So it's that first piece that PyBombs does, setting up your prefix, that takes care of most of what you need PyBombs to do besides the dependency and the outer tree modules. So I don't really have a great answer there, but yeah. I would say, yeah, from source is just you manage the prefix yourself and download the code for all of your outer tree modules and install them to the prefix yourself. Sorry, Jacob. Thank you. All right. Cool. Thanks, everyone.
We have a morning break here until 11, but before that, just a quick announcement. If anyone would like to give a lightning talk, go see Samantha. We have another slot this morning. 5-minute talk on anything interesting. Other than that, we'll reconvene here at about 11.
Thanks again. What happens about this? I just looked it up actually. Apparently it's sort of something with a military tradition that shows that you're a member of a particular group and you can be challenged in a bar, and if you don't produce your point then you have to buy a round or something. So
Wait.
I think you just pocket it.
It'll work a little bit.
It's probably a funny handshake.
All right, well, cool. Catch up with you later. Thank you. Sorry, there's your.
Thank you. Thank you so much.
Thank you. The from source question?
Yeah.
Well, I think the only thing we're missing, the little piece that sets up the prefix, everything else we have a tutorial for, like here's the steps to install from source, which is CMake,
Yeah.
like app install CMake.
I have a.
So if there was like a little script that came with the video that's set up, that's all we would need, and then you can totally kill Python.
I literally use Python.
Yeah,
It works.
it makes the setup and the setup E and B or whatever, and the extra directories, but that's all you would need. It's very simple script if you. No, we need it to kill Python. Oh.
Exactly. That's exactly. So it's just like, if you're going to go from source, go from there. That's really the only way.
Whatever. Test.
Yeah, I mean, we went like. Hey, Hack On, if you could come up to the stage.
Check, check. Hello. All right, we're going to get started again. First we're going to talk about the state of GRC QT with Håkon.
My name is Håkon. I'm the newly appointed GRC team lead for GNU Radio, and I'm going to be talking about the GRC QT port, which I've been focusing more or less exclusively on recently. So to begin with, I'm going to keep this talk quite short because we had a breakout session yesterday with quite a few attendees, and I expect there will be some questions and concerns at the end here today. There's probably some opinions and ideas hidden here in the audience. All right, so first I will talk about the what and the why of the QT port. Then I will give a brief update on the state of it and what features are missing and what features are not missing. Then I will talk about the frameworks that are used in the QT port and also how one might help the effort. And finally, I will speak loosely about the new features that, well, some of them are already in the port and some are perhaps coming.
So the QT port is simply just a PyQt port of the GTK version of GRC, the GNU Radio Companion. It's intended to be a drop-in replacement, so no breaking changes, some additions and new features, but no breaking changes. It resides on the upstream GNU Radio repo on the feature GRC QT branch, and you can all try it out right now by cloning that branch and running the python-m grc-qt command. And this does not require you to rebuild. You just need to check out the branch and then run the command. So we've tried to keep the Qt code decoupled from the core. GRC is already decoupled in a way that the core code and what's being run by both GRC and GRCC is living in its own space, and the GUI components that make up GRC are separated from all that. And the Qt code is separated from all that as well in a new folder called the GRC /GUI QT folder. So the Qt port effort was started by Sebastian Kozlowski and Seth Heitfield some years ago, and it's been picked up and rebooted quite recently, a few years ago. So the reasoning for making a Qt port of GRC is that GTK version has some problems with other platforms. Well, we're trying to make it a more consistent and stable experience on other platforms like Mac and Windows. I believe actually the Qt version of GRC might be working even better than the GTK version of GRC on Mac right now, allegedly. But it also gives GRC a more consistent look and user experience, and some things are abstracted away from the GRC code, which makes it easier for the developer. So the state, most of the core features are done. Some of them are halfway done. Some of them have been too daunting for me to attempt yet, and some are kind of on the fringe, so I haven't looked at them yet. The core features that don't work might be because they are almost working. They were working recently, but I probably introduced some new bugs as well. And as of now, it's not as nice to work with as the GTK version, so it's quite stubborn in some places. That's why I say it has attitude. And I've added something that the GTK version didn't have, which is GUI testing. I realized that there are a lot of things that are features in GRC and a lot of things that aren't quite features, but they are still things that need to work. And it's quite hard to get a mental map of all these tiny features without bringing testing into the picture. So the most important missing features are the undo-redo framework. This is a bit easier in Qt since Qt has inbuilt support for this. Most of it is done. When it comes to block movement and rotation and all that, it's done, but the parameter changes isn't done yet. Another thing is the copy-paste framework. This is a kind of a big task, I would say. So I haven't looked at it yet, but it shouldn't be too hard. And the good thing about porting GRC is that a lot of the code is already there. It just needs to either be copied as is or edited slightly. Another thing is the variable editor and some other widgets, like, for example, the about windows and things like that. Also the bus ports. I haven't touched the bus ports yet because it might be in need of some deeper rewriting, not just on the GUI side, but on the core side as well. And some other missing minor features like multiple block rotation. I'm not sure how often that is used, but it doesn't work yet anyways. So we're using the PyQt5 framework and the graphics view framework. I know Qt has several ways of doing things. You may have heard of Qt Quick. We're not using that. We're using the graphics view framework. And that works in a way such that every block, every connection, every parameter is a subclass of the core elements. So if you see an actual block in GRC QT, then that's a subclass of a core block. And the graphics view is the window into the graphics scene or the canvas. And that's how the graphics view framework works with the scene and all the items, like all the elements of the canvas are graphics items. We're not using QML so far. Maybe we should. I'm not sure yet, but we haven't started using QML yet anyways. Yep. So before I talk about the new features, I should probably say that the best way of contributing to the Qt port is probably by like opening a window of GRC GTK and GRC QT and look at what's different. Probably there are dozens probably things I could write down as issues and mark them as good first issue on GitHub, but it would be a lot of work to just mention them. And a lot of these things are really low-hanging fruit, like connecting signals and opening windows and things like that. So new features. One thing I've added is parameter units. So some of the parameters have units like hertz or symbols per second, and they aren't necessarily written anywhere in the documentation. But it would be nice to have the units on the side so you see what kind of parameter you're editing. Also, better documentation or wiki integration. Right now, there's a documentation tab where if you click a block, then the documentation from the YAML file will show up on the right side of the window. And maybe that should be a Qt web view of the wiki instead. That may be. We're also looking to have a preferences window. Some preferences right now are hidden in different parts of the title bar. And also theming. Dark mode is definitely going to be a thing in GRC QT. And there are other features that might make it. I know the out of tree manager is, as far as I can remember, a part of the usability enhancement grant, and also running GRC on the web in a browser could be one way to do it. Also, remote operation could be interesting to play with. So yeah, a lot of things that would be nice to have. So that's my talk. I'm not going to show any demos. I'm more interested in your questions or ideas. So if you have any ideas afterwards, come talk to me or send an email either to the grc@GNURadio.org mail or open an issue on GitHub, or yeah, try it out anyways. Thank you.
Okay, any questions? I have a question. Do you have an idea about the path, like timeline for getting this integrated into GNU Radio? I don't know if Josh is here either, or if there's a path forward for that.
So the question was the path for including the QT port in GNU Radio.
Upstreaming all of this work.
Upstreaming
Yeah.
it. Yeah. I'm not sure about that. I guess it would be a decision involving more people than just me as well, of course. But my personal goal is to make it as good as the GTK version by New Year and irresistible by the summer.
Excellent. Okay, last chance for questions. All right, well, thank you. All right, next we have Travis from Analog Devices here. They are a platinum sponsor this year and have been a longtime supporter of the conference. So get you switched over and.
Good morning, everyone. My name is Travis Collins. I'm an engineer with Analog Devices. I work in the Aerospace and Defense Group, which is a little bit different than where I was last time when I was here at GRCon. Today I'm going to be talking a little bit about ADI and go into some parts that you probably, we don't really talk about at GRCon. We'll start off a little bit about the company, but then kind of get into some more interesting technical things. So just some background on me. I've been using GR for, I don't know, 10 plus years now. Back in my master's days, myself and a colleague of mine are the original authors of like GRDOA. And right now I help maintain GRIO with a number of others. So, you know, any complaints about Pluto or some of the other IO devices, please let me know. We're happy to add more features if you're using some of the I/O blocks now. Now, just a little bit of background on ADI. So ADI is really foundational in the converter space, data converters, microwave, sensor, all kinds of different devices. We've been around since 1965, excuse me. But our portfolio has pretty heavily grown through just naturally through development, but also through different acquisitions over the years. With companies like Hittite, which really increased our high frequency business, with Linear Technology, which gave us more ADCs and DACs, and a lot of power components, and more recently with Maxim Integrated, which really gave us a boost to our kind of commercial space as well. So right now we make around 45,000 different SKUs, so lots and lots of parts over many different industries, from like RF to sensors to precision. Audio is a big market for us, and we're all over the world. So we have design centers all over the globe, and we have, which makes, I would say, design reviews really fun. So usually we're in a call with guys from India, from Wilmington in Massachusetts, Limerick, Romania, which is where some of my team works. But it's really a global company. But ADI, I would say we really do two things really well. We do integration, so we'll take a bunch of components and put them into monolithic ASICs or SIPs or MIMICs, things like that. or we add new features and enable different applications. So that's really what I want to just go into a little bit. So if we go back, say, circa 2012, and if you walked into a LTE base station, you would see a radio head that looked like this, where we have this board on the left here, where we have really discrete sections of the radio, where we have a discrete RX1 section, RX2, ORX or observation side, as well as transmitters on the bottom. So this is kind of typical what you would see in 2012, where we have really discrete components put on a single PCB, and this would be your common radio head. Then if we kind of go up just 1 year to 2013, all those components really got smashed into a single 10 by 10 millimeter package. So this is really the birth of like 9361 and a lot of the generation of modern transceivers that we've seen from ADI over the years. So the chip is on the left, which is like a monolithic ASIC that includes most of the circuitry we saw on those PCBs. And in the middle is kind of a diagram of, it's a really simplified diagram of what goes on inside the transceiver. And on the right is a metal layer, which is a really interesting article from Zepto Bars that goes into 9361, some of the details on the chip. Some of the math isn't really right in the article about kind of the business cases behind it, but it's a really interesting read. One thing you'll kind of notice about the die shot here is this kind of like dense portion on the right. Whenever you see that on a chip, this is the digital sections. And if you look at the generations that come after 9361, this gets bigger and bigger and bigger. So at about now, we're like, that's over half of the dies. So we're adding more and more digital into the components that are coming out. But this is a great example of the level of integration that we do. We take like discrete mixers, discrete LNAs, and then smash them into a single ASIC, and you get massive swap advantages by doing that. And by putting things on a single process node, we can get a lot more advantages, control things, get much more performance by doing that, start introducing algorithms into the design, things that you can't really do or are really challenging to do with discretes. So that's part of our integration business. And the second is more adding features into hardware that enables different applications. So I just want to talk a little bit about our beamformers, which is a new area that ADI has been kind of getting into for the last few years. If you're not familiar with beamformers, I'm primarily talking about analog beamformers here. They work, we look at the diagram on the left, by taking different feeds on transmitters or receivers and applying gain and phase adjustments to them to build beams or gain in certain directions and nulls in other directions. Now, so you do this by having individual controls on the gain and excuse me, phase of those individual channels. Typically, this is done digitally because it's much simpler to do that than to build essentially hardware that does this for you. But having a single ADC, single DAC on every channel can be very expensive and have a lot more power requirements around it. So recently, about 2-3 years ago, we introduced the ADAR 1000 beamforming chip, which is this diagram on the right here. Now, how this chip works, it's designed for around 10 gigahertz X-band. We have individual controls, so there are 4 receive paths that come in, which are these kind of red lines here, which will sum together to a single output, or we can have a single feed that goes into the chip, and that will go out to the individual transmitters. And we can individually change their phase and gain to form beams. And this is what the eval board looks like if you want to buy the device today. But how would you really use this in practice? What does the system look like with a ADAR on board? So here's a really good example. We have a kit called the Stingray, which is our X-band development kit. And this comes with everything from the antennas to the ADARs to the up-down converters to get you to 10 gig, as well as the digitizers on the back end. So on the left here, we have just an image of the front end where we have our antennas that are spaced for 10 gig frequency, and they're set up in these kind of quadrants here, where on the back of that, that antenna face, we'll have the beamformer in red here. And the individual chips that are feeding the antennas are called TR modules. If you're not familiar with TR modules, they're essentially a switch and amplifiers that we use. So each of those panels can, or each of the antennas can operate in transmit or receive mode, and we can control them individually at the 8R level. Now, you might ask, well, how do I control these things? It's, if you're familiar with Pluto or devices from ADI, we provide kernel drivers for them. So we can individually control gain and phase, as well as other things. So if you look at the driver today, you'll see lots and lots of attributes that allow you to digitally adjust the phase and gain of each channel, of each ADAR. You can stack multiple of them together and adjust them kind of sequentially together as well. And these chips are a little bit more complex than just phase and gain. There are state machines inside of them, so we can do things like beam sweeps and beam adjustment. We can control amplifiers that sit on the front through bias controls and other state machines that exist inside the device. But again, since this is all driven through I/O at the bottom of the stack, we can just use our traditional GRIO blocks, and we get something like this on the right, and we get individual phases, and we can, as well as gains and other settings, and we can control these beamformers and easily bring up our system and control it as we would expect from a flow graph. So if we kind of look at this holistically, where we have our traditional kind of layout of our system with something like Python or GNU Radio, starting on the right, where we'll have our PC that's attached to a FPGA or similar device, and then our data converter, like a transceiver, high-speed device, something like that. We have more control today, where we're extending further out into this microwave domain. And we're adding more and more control into these more traditional kind of like fixed function analog components that you'd see. And the beamformers are a great example of these. So, the Stingray kit that I showed first, that's an interesting device, but it's very, I would say, like purpose-built for one function. We have been working with X Microwave. X Microwave makes this system for RF prototyping. You can think of it as like Lego blocks for RF devices, where you get this grid, the steel grid, stainless steel grid, and you can put down these little tiles and build up your RF system. Now, we worked closely with them to build a daughter board or a bridge board that connects to this kit, so we can individually control these components like beamformers, like mixers, like gain stages, and get them back into our drivers and control them as we would any other device. So, you can think, I have a beamformer out front. How do I control that? I have a mixer out front. You hook this up, you get the I/O driver, you use GRIO, and you're good to go. Here's just another example where we're showing off more explicitly this card in red here. So this is kind of a standard kit that you would see from analog devices, where we have these FMC cards, which will have data converters or transceivers on them, which are hooked up to a standard kit from Xilinx or Intel that have these FMC connectors. So the additional piece here is that we have a controller board that will bolt up to that X Microwave kit to give you access to these analog parts out front. And we develop drivers so you control them in a single holistic way, from Python, from MATLAB, or GNU Radio. It doesn't really matter. So this is kind of like the final hardware that I'll show, but similar to the big Stingray kit, we have a smaller, more education-focused device called the 80ALM phaser board. This is using the same parts, up converters. It's receive only. It doesn't do transmit from the beamformers. There's an up converter for just a single transmit that comes out. But essentially, it's 8 Rs on a single board. Then we have a Pi that's mounted on the front for control and data streaming. And then we have the digitizer, which we're just using a Pluto on the back. And this is just a self-contained kit that's great for learning about beamforming, understanding beamforming, and then you can kind of update to or upgrade to the bigger systems when you need more channels, when you don't want to do more, I'd say, unique arrays if you have a different geometry. And ADAR 1000 is really the first generation of beamformers, and we're on the 4000 series now. So depending on the frequency band that you want to operate in, we usually have things that fit into those applications. Now, if you found this interesting, we have lots and lots of openings, ADI, for software people, for HDL people, for hardware folks. We try to do things in a holistic way so that you can have a single consistent environment. You know, everything is software driven now, software controlled. So it's more adopting the beliefs that we have in software-defined radio and extending that further out to different components into different industries. You know, it's not just radio, it's sensors, it's audio. We're doing things all over the map. And you know, GNU Radio is a great platform for that, and we're building our software and our HDL in a way that cooperates with GNU Radio. But yeah, so as I mentioned, you know, we are in a lot of different industries. So if RF isn't your thing, if you like automotive, if you like 5G or smart systems, digital healthcare, we are doing similar work in these industries. A lot of it is just signal processing at the end of the day. So we use the same tools. It's just you have a different device hanging off the front. So thank you for your time. If you want to learn more about these devices, please come by our booth. We have the phaser, we have the X microwave kits, and we're glad to talk with you and discuss more about our devices. Thank you very much.
Thank you, Travis. Any questions? Well, yeah, check out that stuff in the expo hall next door. It's open now. We're a little ahead of schedule, so we have some lightning talks coming up. May end up a little early, but expo hall's open if you have a few minutes before lunch. Thanks again. So Dan, or actually, who's the first lightning talk? Someone from Aldec? Louis? Are they here in the room? We're a few minutes early, so let me hunt down our next presenter. Louis from Aldec, if you're in the room, you're up.
We're a bit early, so maybe if Dan Romanchuk, if you're able to start early. I don't know. Yeah, let's we'll shuffle things. Start with Dan from ARDC. Thank you.
So hello, my name's Dan Romanchuk. My call sign is KB6NU, and I'm here to talk a little bit about amateur radio digital communications, or ARDC. And we were mentioned yesterday here, if you were in the room, we gave we're a private foundation, and we give grants to organizations that deal with digital communications, communication science, and amateur radio. But let me back up a little bit and tell you the story of how we got started, because it's really an amazing story. Every time I tell the story, I'm amazed by it. So back in 1981, the internet was just getting founded, right? And one of the fellows, KA6M, Hank Magnuski, got the idea that, ham radio should have some IP addresses. So he asked the John Postel of MIT, not MIT, I think USC, who was doling out the addresses, to give ham radio some IP addresses. And if you look at the map of the internet at the time, there was like AT&T and Northern Telecom, and I think IBM had some assigned to them. And he gave ham radio, he assigned ham radio a Class A block of 16 million IP addresses, IPv4 addresses. And there was an ad hoc group of ham radio operators who administered those IP addresses for a long time. And they were used in different experiments. Some folks did packet radio over radio, AX.25 stuff. And, it was used, but we never really used all 16 million addresses. So anyway, along about 2011, so it was just this ad hoc group administering these addresses. Around about 2011, the Internet Authority said, well, you guys probably want to get a little bit more formal about this. So they formed a nonprofit corporation called Amateur Radio Digital Communications. This was 2011. And this went on for a while, several years. And in 2019, the board said, well, you know what? We're never really going to use all these addresses, and some of these are kind of valuable. So why don't we sell some and then start giving out grants? So they made a deal with a large internet retailer who I can't name, and sold them a quarter of the addresses, 4 million addresses, for a large sum of money, which I can't mention either. Although this is all on the internet if you want to figure this out. And we formed a private foundation. We're a private foundation now, and we give out grants to groups like GNU Radio and NRAO. In fact, we just gave a big grant of about $300,000 to NRAO to start an educational program. They're calling it Exploring the Electromagnetic Spectrum, and they're going to work with kids to teach them about ham radio and the electromagnetic spectrum. So anyway, we've got this pot of money, and in 2021 we gave out $9 million. In 2022 we're going to give out $6 million, and the difference there is that in 2020 we didn't give out all the money we needed to give out. As a private foundation, you have to give out 5% of your net assets every year to keep this tax-exempt status. So anyway, one of the reasons I'm talking here is that we have money. We have money available for projects. And if one of you have an interesting idea to do something, we'd love to hear about it. There's some caveats. First off, it has to be a nonprofit kind of thing. So we can't give out money to, like analog devices, for example. We can't give it to educational institutions. One of the grants we gave out recently was to a group of senior students at Bradley University who developed it was some kind of digital communication system using LoRa technology. It wasn't really using a GNU Radio, but if you had some project using GNU Radio, that would even be cooler. One of the grants we gave out recently was to a project called the M17 project, and they're developing totally open. And that's the other sort of caveat too here. Anything you develop has to be open source, and I think I'm preaching to the choir here on that. But we gave money to what's called the M17 project, and they're developing a totally amateur radio-based digital communication system to be used on amateur radio. And when I say totally amateur radio-based, you know, currently in ham radio, we have things like DMR and Yaesu Fusion and D-Star. And these are all usable, but they're just sort of amateur radio use of commercial technology. With the M17 project, what's so exciting about that is that it's totally done by amateurs for amateurs. And we think this is going to be a big thing in amateur radio. And M17, or GNU Radio, supports M17. Somebody's working on a project to do M17 using GNU Radio. So anyway, I mean, that's really the basis of my talk here. Like I say, we have to give out the $6 million in 2022. The deadline for getting any money in 2022 is kind of over because we're sort of near the end of the year. But we expect to give out an equal amount of money in 2023. And if you have any ideas about how you might use that money, please talk to us. Our website is ampr.org, ampr.org. And you can email giving@ardc.net. We have sort of two different domain names. And that's really it. If you're interested in ham radio in any way, I'm going to be doing a review session tomorrow, and of course, then there will be a test session in the afternoon. So if you're interested in doing that at all, you can see me. We're going to be. I've written a study guide for the amateur radio test, and it's a free download. You can go to my website, kb6nu.com, and get that study guide. But I'll be in, I don't really know, I forget what room I'm in, but I'll be in the room from 9 till about 1:30, and then the test session begins about that time. Or 9 to 3, I guess. The test session actually begins at 1:30. But that's it. Any questions? Yeah, so it's ampr.org. M as in Mike. You can get there by going to ardc.net too. It just redirects.
Okay. What's the selection criteria for the grants like? Are there any particular areas you guys are focused? Anything that interested parties should be looking for?
Can you repeat that question? I didn't quite get it.
Sorry. What's the selection process for the grants? Are there any particular areas or that you guys are focused, or anything for interested parties that they should be looking into?
Well, again, if you go to ardc.net, you'll see what kind of categories we look for, and some of the things we look for in a proposal. But the way the proposals work is we accept proposals any time of the year. We begin a review process 4 times a year. And the next one is actually starting October 1st. So that's why I say it's probably kind of late to get into the 2022 cycle. But the next cycle will begin in February 2023. And what we do is we bundle up all the proposals we've received to that date. It goes to our grants advisory committee, and then it goes to the board. The grants advisory committee kind of weeds out some of the ones that, like we get some proposals that really aren't germane to what we do. So we weed those out, and then the board approves any proposals that the grants advisory committee passes on to them. Does that answer the question?
Oh yeah, thanks.
There's kind of an echo in here, so it makes it hard to hear on the podium here.
That was good. Thanks. All right, thank you, Dan. Next up, we have Louis, who's going to give a lightning talk here from Aldec.
That's it. Okay, yeah, thanks for having me. My name is Louis DeLuna with Aldec. So we are a company who provides FPGA simulation and verification solutions. It's our first year exhibiting here at GNU Radio. What we built is a co-simulation interface with GNU Radio. So if you are starting to use FPGAs, we see a lot of markets everywhere, many different applications using FPGAs now. So if you are starting to use FPGAs to achieve higher performance, now you have a co-simulation environment with GNU Radio. So your GNU Radio flow graphs, you can have a custom component, for example, a DMA component proxy, which you can basically implement in the FPGA so that your core that you want to implement in the FPGA, for example, a VHDL core or a Verilog core, you can now co-simulate that within Riviera Pro and GNU Radio. The advantage, of course, is a very simplified tool flow if you're going to simulate FPGAs. In addition to that, you have advanced debugging environment. You can view waveforms in the digital side. You can employ advanced verification solutions, for example, code coverage, breakpoints, assertions, viewer, memory visualization. Okay. So after you've done co-simulation with GNU Radio and Riviera Pro, you can then re-implement that in one of our FPGA development boards. So we actually have a couple here in this example. One development board is with Xilinx ultra-scale Zinc chip. So that chipset actually has a ARM core within it. So you can run the GNU Radio on that ARM core and the FPGA logic running on the FPGA side of that chip. So that's one example. The second example of development board that we have is with this new chipset from Microchip PolarFire. So this company has a PolarFire SoC. Instead of an ARM core, they have a RISC-V quad core. So it's, RISC-V, as you know, is another open source project. So if you're interested to use a RISC-V core, which is an open source, you can also use that. These boards have different interfaces and also have FMC dual cards. So you can connect various types of interfaces. For example, if you want to run or use a QSFP Plus, you can actually connect a card with that. So we have a demo in our booth. Please come see us. We'd like to talk to you and learn more about your use cases with FPGAs. We've been a company for about 35 plus years now. So we have a lot of experts in FPGA design and verification. So come talk to us. We're very interested to know the use cases that you guys want to do with FPGAs. In many markets, in the ML market, the automotive market, we've been in those markets. The typical use for FPGAs is they want to achieve higher performance. So instead of running them on, for example, on ARM Core x86 GPU, they want to use FPGAs because it's flexible, it's reprogrammable, and it can achieve high performance and low power. Okay, so that's it. Thank you.
Thank you. Any questions? All right, we have one more lightning talk before lunch, which looks like it's getting started. But one more 5-minute lightning talk. Pete from Plane Networks has some slides and is going to tell us about internet on airplanes.
should say GNU something back there. There's a, oh. What's this one? Is that it? That's it. And this is on. Do I can forward them here? Is that but oh. Yeah. There's a good morning, good afternoon. Anyway, I've been spending a few years looking at delivering decent internet into planes, and the idea would be everybody that would sit on a plane could get Netflix. So if you were on a Delta, United, et cetera flight, you'd be able to get Amazon, Hulu, Netflix, TikTok, whatever. So my background is satellite engineering, and this is right now generally done by satellite. So I was trying to understand what kind of satellite designs would do it cost effectively, so that it cost about $5 a seat for each passenger. So to start it, you got to kind of understand, well, what kind of data rates do you need? And so I spent a weekend, this was a couple of years ago, just streaming different programs with different streaming services and measuring the required data rate. And for the most part, it's about 1 megabit per second. So if you had 150 people on a plane and everybody was streaming Netflix, then that plane would have to get about 150 megabits per second. And if there were two planes flying next to each other, you'd need to deliver about 300 megabits per second, and so forth, so on. So anyway, what I ended up doing was looking at a system that would do that. So and this kind of gives you a picture of what the system might look like. So you probably heard of companies like Viasat or HNS and Inmarsat. And right now they do a satellite-based system, and their satellite generates a bunch of spot beams. Okay, and then the planes flying through the spot beams would get the content. So the content would originate on the ground. It would be delivered to a gateway, which would uplink the signal to the satellite, and then down from the satellite would, in all these different spot beams, content would be delivered. And the problem is kind of simple if it's just a handful of planes, but you can see that over the United States, there's some regions that are going to have lots of planes, right, where there's lots of flights, especially around airports. And then in some regions, like Wyoming or Montana, where, yeah, you have planes, you have to provide coverage, but probably not a whole lot of coverage. So to do it cost efficiently, you need to understand how much resources you need in the congested areas, how much resources you need in the somewhat congested areas, and then how many satellite resources you need in less traveled areas. So anyway, I built a pretty detailed traffic model using a couple years of data, and just imposing them on this spot beam satellite, or maybe a couple spot beam satellites. So the number of beams start here in the upper left-hand corner is 0, and in the lower right-hand corner down here, 236. And if you see two numbers in the beams. You see a number in red and a number in blue. So the number in red represents the number of satellites you would need, or number of satellite beams that you would need from a power point of view. And then the number in blue would represent the number of satellites you would need from a bandwidth point of view. So in a lot of cases, these numbers match pretty closely, but not all the time. Yeah, like for instance, in beam 22, from a power point of view, you would need 1 satellite, but from a bandwidth point of view, you would need 2 satellite beams. So this model was done assuming that every person sitting on the plane would be trying to get 1 megabit per second because they'd be interested in getting Netflix. So you can see over regions like LA and Atlanta, somewhere down here, you'd need lots and lots of satellites. And in regions, again, like Montana, Wyoming, you don't need very many. So this would be done, this basically represents what would be done from a geostationary satellite. And then I looked at it from the point of view of LEO satellites. So this represents an older constellation, OneWeb. A constellation like Starlink would be the answer would be different, but the methodology would be the same. So these systems, the satellites travel in orbits. So in orbit 1, you have a string of satellites, probably about 20. In orbit 2, you have another string of satellites, also probably about 20, and so forth. So to cover the U.S., we need about 7 orbits for this particular constellation. Okay, and then what I did is I froze the constellation at a particular instance in time, and these were the satellites were at that instance in time, and then tried to figure out, well, how much capacity which of these satellites have to provide so that, again, everybody on every plane, that's Delta, United, JetBlue, Frontier, Spirit, et cetera, everybody on all the planes would be able to get Netflix. It just gives you an idea of the amount of capacity that you would need in each of the regions. So in the northeast part of the U.S., makes sense. You need a lot of capacity, more than 35 gigabits. Then like over northern plain states, you need a lot less capacity. So the whole idea of this analysis was to get a sense of what a smart infrastructure would have to be. So that's an infrastructure that would provide lots of capacity where you have lots of users and minimal capacity where you don't have many users. And what I'm not showing here is that there would be a terrestrial component to the system, and that would be that would be used to beef up capacity requirements around airports where the planes are fairly densely packed. That's pretty much it. Any questions?
Thank you.
Yeah.
I was just curious if you used any modeling tools to characterize the
I developed my own modeling tools. It's coded in C++. So I developed models for the beam sizes, and then I had inputs from a company called ADSB Exchange on where planes were every minute of every day over like a year and a half, and then just ran an analysis minute by minute over there, over that period, and then looked at the amount of power and the amount of bandwidth that would be required for each plane at each instance in the analysis, and then racked it up here. So you're not seeing, you're just seeing like the top of it.
Well, I mean, so it was a custom modeling tool that you built yourself?
Yeah.
Oh, is it open source?
I beg your pardon?
Is it open source?
No.
Anyone else?
So how'd you say you arrived at these data rates? Was it through testing, like the mobile data rates?
Oh, so yeah, that was done. Yeah, I spent like a weekend just looking at different programs. You can see them here, and then just streaming them and just looking at my router and looking at my Mac and just measuring how much data was required over a given period of time.
Okay. Yeah, I have to say I'm genuinely surprised how low it is for the mobile devices. I would think it would be like 2, 3, 5 times as much.
That's what when I went in, I didn't know, but that this is what came out. But for like an HD signal into your TV with I think the latest standard, I think data rates less than 4 megabits per second are required. I'm talking about your 55-inch TV. So for ultra high def, it's I think around 9 or so megabits per second. So, with a very small screen, you don't need as much resolution. And I believe that these organizations are trying to figure out how to compress their data, given the screen size that the file or the image would show up on. So these companies are spending a lot of money there, trying to definitely drive data rate down, because a lot of times people handling these devices are doing it over like an LTE network where bandwidth is constrained.
Thank you.
Yep.
All right. Thanks. As a frequent traveler, someone who travels a lot, I appreciate you working to upgrade my in-flight entertainment experience. Okay, lunch is being served in the expo hall. the afternoon session will start at 1, but the hall's open. The sponsor tables are out there.
Yeah, there are little animations and stuff. Something that wouldn't show up in a. Oop, that's my life.
Test, test.
All right, okay.
Hi. All right, everyone. Welcome back. Right now, we're going to have a quick announcement. And so I just hand it over to you, and then I'll tell you more.
Okay, perfect. Thank you. So I'm Dave Twitchell, work for Shift 5, and I was going to give a talk on my research on the positive train control system. Fortunately, you might have heard that I said was, so I unfortunately will no longer be able to do that. Due to some recent events, and recent as in 8 a.m. this morning, I'm not going to be giving the talk anymore, and unfortunately I'm not going to be releasing the code anymore either. So my company has given me a statement to give, so I'll go ahead and read that. Due to rapidly unfolding events and an abundance of caution for the critical safety implications associated with PTC systems, Shift 5 regrets to cancel the presentation. Please stay tuned for updates on the Shift 5 blog as we continue to conduct research and to work with manufacturers, integrators, and operators to ensure the security of our national railroad system. So, unfortunately, this is not going to be a press conference where I'm going to answer any questions about that. And especially since I'm an engineer and this is kind of straying into territory that's not something that I can talk about. But really, I want to apologize. This is obviously not something that we expected. I really was looking forward to giving this presentation, but we'll see where we go moving forward. Sorry. Thanks, guys.
All right. So what we're going to do now is we extend the lunch break until our next talk starts at 1:30. So take some time to look at the booth and yeah, continue your conversations, and we'll see each other at 1:30. Thanks.
I would also put a reminder for those that are doing CTF, you know, this is a great time. What does the Fox say? Good time. I've seen some people wandering around some nice antennas. You may want to ask if you can borrow some equipment. So thanks.
All right. See you.
Test.
All right. Yeah, and if it just press. All right. Yeah, that's exactly what I saw previously, and I wondered how to get that back. Great.
Yeah, so just press the button.
Yeah.
I think if you press it longer, it starts off. But just press it.
Oh.
Man sagen mal, bevor es losgeht. Weißt du, wo unser erster Presenter ist?
Ja.
Ah, okay. Also bevor du ihn einleitest, lass mich kurz noch was sagen. Hello. Hello, everyone. We're going to start our talks very soon for the afternoon. A quick announcement. So we were asked how to bring a +1 to the social, and we forgot to sell +1 tickets for the social. Sorry about that. It's not a problem. Just go to tickets.gnuradio.org, buy a virtual participant ticket for $25, and that'll get your +1 into the social. No problem. We're looking forward to we're looking forward to you guys. Like, don't leave your +1s at home just because we forgot to do that. $25 virtual participant ticket is all you need. And we have a number of drink vouchers. They are for badge holders, so not for virtual participants. But it's just a regular pay at the bar kind of thing after you've used up your ticket. So $25 plus whatever you pay at the bar. That's what. Sorry. Oh yeah, I'm sorry. You need to bring so the way you get the drink vouchers is you show the badge. Like that's how you. Exactly. Your +1 doesn't have a badge, so they'll have to pay their own drinks. But sorry, that's how that works. If you think it would be more useful to increase the price for the +1 ticket and then also include vouchers like for next year, that would be interesting feedback for us. But we thought this was just like the least hassle. So thanks for that, and I think I'm gonna hand it off to our MC for the afternoon.
All right. So welcome back from our extended lunch break, and we're gonna start with our first presenter for this afternoon. So, Sage Trudeau. Stage is yours.
Testing. Cool. All right. Good afternoon, everyone. My name is Sage Trudeau. I am an assistant staff member at MIT Lincoln Laboratory. I work in the cyber physical systems group, where we study various kind of ins and outs of cyber physical systems. Today I'm going to be presenting a little bit of work that myself and Hope Hong, another staff member, did last year, where we had some systems that were already out in the field that had some software-defined radios already in them, and we attempted to implement a TDOA geolocation solution on them, and I wanted to share some of the lessons learned that we kind of did there and walk through some of the exciting stuff. Okay. So a little bit of background. What we were trying to do here is basically locate unexpected emitters in a base encampment scenario. I won't go too far into this, but it helps frame the problem of why we were interested in this to the get-go. And currently, it's kind of a long process where they wander around. And so what we wanted to do here is be able to automate this process a little bit. Obviously, geolocation, not a new kind of concept. But we did have some interesting constraints of wanting to be extremely wideband. We wanted to remain signal agnostic. We wanted to be near real time. So in our case, within a couple of seconds. And we wanted a receive-only system because it was important to not be additionally polluting the EM spectrum in the areas of interest that we wanted to work with. So based on these constraints, we decided that a geolocation solution that we were going to pursue was going to be a time difference arrival-based technique. There are many other techniques out there, but this is the one that we decided to go with. So for those of you that are not as familiar with TDOA, I'll take a quick moment to kind of introduce it. Hopefully you've sort of heard of this before. But basically, it's a technique used to be able to calculate the location of a transmitter by using the difference in arrival time between 3 or more receivers. And so by calculating the difference in arrival time, you can then figure out kind of all possible locations that that signal could have come from to explain that time difference. And then you are able to, through the different pairs, kind of estimate an actual geolocation estimation. So our pipeline and kind of the 4 major steps that are involved with this is you need to get your receivers time synchronized. So that's the most important first step. You then have to get all of your data to a central node to be able to calculate a time delay estimation. And then you calculate these hyperbolas from that time delay estimation, and you then turn it into a map pin by the intersection of all 4 of the hyperbolas, or 3 in this case. So on that first step here, basically what we wanted to do is be able to use the EDIS X310s that we already had available in the pod. And so thankfully through UHD, we're able to utilize time commands to be able to make this happen, along with the GPSDO. They have some great documentation out there. I've also included it in my references if any of you are interested in doing this. You essentially calculate a new clock baseline, you set a command time, and then you set that receive command to happen in n seconds, and you end up being accurate, well, depending on what clocks you have in there, about plus or minus 50 nanoseconds. And for our case, that was going to be a great place to start. And you can utilize that to be able to have non-co-located receivers all capture essentially the same instantaneous moment in time. We then perform the time delay estimation step utilizing cross-correlation. So there are a few different ways that you can do this. If you know more about the signal, you are welcome to utilize kind of a match filter or maybe some kind of more advanced pulse technique or something like that. But if you want to remain, extremely signal agnostic and work right over kind of a lot of different signals, one common method is to utilize cross-correlation. And so we do a simple time domain cross-correlation on the raw IQ samples. And kind of the only downside of that is that you have to have all 4 data streams back at a central node before you're able to perform this step. And you can see this here that basically, it causes a nice little spike in the cross-correlation when you kind of guarantee that you have the same signal at all 4 of your receivers, and then you can move along to calculating your hyperbolas. So for hyperbola calculation, there are a few different ways to do this. We prefer to do the actual derivation of the equation. So we utilize the equation of a hyperbola and then know basically that through the speed of light and by setting up relative coordinate frames between all of our receivers, we can figure out what that a squared and b squared should be. And then that lets us kind of have the general equation at our particular instantaneous time delay. So in a perfect case, if the time delay is 0, then you don't have to worry about this. It's just kind of a straight line. But as that time delay changes, it describes the closeness that the transmitter was basically to one of your receivers rather than the other. And then you can calculate the hyperbola of all possible points that describe where that transmitter could have come from. And between multiple sets of receivers, you then are able to kind of create this, this plot on the right where you get an intersection of these hyperbolas. And you use kind of, well, for the developers out there that are interested, this is how kind of the equation of the hyperbola actually applies. In the essence of time, I'll skip over the math a little bit here. This geolocation result then creates a polygon. In a perfect world, these would all intersect on the same point. Unfortunately, that's not how this works at all. And so you end up with varying degrees of intersection, some of good. We just use a simple approach to then determine the centroid of that polygon and use that as our estimation. There's multiple kind of ways here that you can also do better guessing. So this is another area where there's opportunities for improvement. And it is worth noting that if that polygon's unbounded, kind of a side effect of the way that TDOA is calculated is that it does just kind of degrade to direction finding, which can actually be quite useful depending on what situation you're in. All right, so into the meat of it. Now that we've kind of described a little bit about TDOA just to get everybody up to speed. So what I'm going to talk about here today is three major kind of phases that we set up, along with the challenges that were associated with them. And my hope is that by sharing these challenges, you guys, if you guys are setting up something on your own, will able to avoid some of these pitfalls and also be able to better understand how this technique is used actually in the field in real world situations. So the first phase was to be able to set up all of our equipment, shake out any of the bugs. We were really just concerned with getting our receivers time aligned. The second phase, we wanted to understand better the importance of geometry, and we wanted to utilize a couple of techniques using a known transmitter in the area to be able to improve our time alignment from the first phase. And then in the third phase, we were worried about trying to actually send this out as something that could be a useful capability. And so there are data backhaul concerns associated with that, and there's a large amount of trade space that you have to play in there to be able to have this actually be a near real-time system and be operational. So the phase one setup is a roughly 15-mile square area located around Boston. Fortunately, we had some team members that were very happy to generously donate their backyards. And so we set up kind of these ruggedized Pelican cases that are essentially just a server blade and some X310s in people's backyards strapped to antenna masts. And we started doing this technique. And basically, we just wanted to shake out our time alignment problems. And so we were looking to be in a very wide area and to look at very high power transmitters. So we started by looking at HDTV and FM stations that were in the area. And what we quickly found was that there's actually a pretty striking difference in accuracy between the two, even though they're similarly high-powered transmitters, and we expected kind of great SNR in both cases. And what we ended up looking into is that accuracy is largely due to the difference in bandwidth between the two transmissions. And so to highlight that a little bit better, we dug into that bandwidth estimation problem. And what happens is that as that signal is more narrow band, if you're using simple cross correlation, that cross correlation peak flattens. And as it flattens out, the odds basically that kind of noise or any kind of problem with your receive chain, they cause that spike to be not as perfect. And then essentially if you have the wrong spike, that ends up to an improper sample, which is an improper time estimate, which down the line becomes an error in your location accuracy. And you can see here, these are kind of three major examples. The third, the LTE station, is from a different phase of experimentation, but it helps illustrate this point nicely. And here are some actual results. So as you're interpreting these, the red X is the known transmitter actual location, and the black star is the estimate of our geolocation estimate of that transmitter. And these are two just kind of random examples from our phase one testing, and they help illustrate how much worse this actually is, right? So in the case of the HDTV station, which has about a 6 or 8 megahertz wide, I forget off the top of my head, we get a pretty good estimate, right? Where we have a 15-mile square radius here, and we're able to find it within about 71 meters of the actual tower. With our coordinate errors and everything else, that's reasonably solid. And then in the case of the FM station, it's not always this bad, but in this particular capture, we're quite far off. And it's purely just kind of due to the two signals being very different bandwidths. So that's a common problem that you'll run into. We figured that we were continuously running into this, that it was probably worth it to model it out and make sure that we had experimental results and see if those were actually matching what we were hypothesizing what was the source of this error. And so here are kind of some major data points over the course of all of our experimentation. As you can see, the actual results, the green, they match the trend quite nicely, with the plus up being because the real world is not nearly ideal. And so you end up with all of your various timing errors, which just add to your location degradation. Cool. So moving along here to the second phase. In the second phase, we wanted to be able to detect lower power transmitters. And so what we're prominently looking for is LTE stations in this phase, or the potential for some handheld devices. And what we saw initially is we set this up around Hanscom Air Force Base, which is a standard kind of small Air Force Base establishment. And what we noticed was that although our cross correlations were looking really, really good, we were getting those great peaks as seen in the previous charts, we were still ending up with some bad location estimates, especially to the north. And we found this to be curious. And what we ultimately discovered is that what we initially thought was not going to be that big of a problem. We had read that geometry mattered a lot for TDOA techniques, but it ended up being quite a big of an issue here. And so we decided that we would take this opportunity to investigate the importance of receiver geometry and model that a little bit better. So this is a little bit of a lot going on in a plot. But what you're seeing here is a GIF of us modeling that scenario. And so the red dot that is moving is that third receiver. We're modeling moving it from an ideal location to the kind of junky location that it actually was in. And as we do that, we calculate a TDOA estimate for each of those pixel locations. And so then we then map the color map. Basically yellow are very poor estimates, and blue are very good. And this is without any RF involved, right? So we're just doing it based on the speed of light timing in between those points to use as the time delay estimation. And it shows how much the receiver geometry really matters, right? So you end up with, before you're even worried about the RF signal, if you've poorly set up your geometry of your receivers, you end up with these large areas of yellow where you're not going to have good results no matter how well time synchronized your receivers might be. So for what it's worth, the general rule here, the best case is a regular polygon of whatever number of receivers you have. So whether that's an equilateral triangle or a square or whatever you get to, and the worst case is a line. So just kind of avoid hiding them in each other's shadow and try and encompass as much area as possible. You'll end up with great results on the inside of your perimeter and then slowly kind of degrading results as you leave that perimeter all the way down to where it then degrades to just a direction finding estimate. In addition to kind of the geometry problem in phase 2, we had also read that there were some great ideas for additionally time synchronizing your receiver in the case that you had a known transmitter in the area. And so this is often the case. There are kind of great high power transmitters out there, whether you're using one of those HDTV stations or anything of interest, an LTE tower or whatnot. You can utilize that to better synchronize your receivers before you actually go to do your stairs that matter, that are going to be looking for unknown transmitters. And this is an old idea that's kind of prominently been used in the past for fixing bad, cheap clocks in various military systems and stuff like that. And I did want to give a quick shout out to Stefan Scholl. He has a very clean explanation of this in his 2017 SDR Academy presentation, and it was very helpful for me in implementing this technique. And the way this works is essentially Because of the way that software-defined radios work, specifically the ARDC X310s, as well as a lot of others, you can switch the center frequency that you're interested in without dropping any samples. And so it lets you do calibration steps on the first part of this kind of three-part capture that are then valid for the middle section. So the way you do this is you first stare at, say, 750 megahertz where your known LTE station is. You then calculate your geolocation estimate, and then knowing the true location of that transmitter, you can then correct for whatever your errors were. And then when you look at the middle part, which is staring at, say, an 850 station of an unknown signal, that same correction still holds true. And so you're able to gain some optimization here, and it actually helps out greatly. So I highly recommend this technique if you're trying to do any sort of time synchronization between multiple non-co-located receivers in general. And so here are some results. What you can see here is that this is quite useful. We were initially about 213 meters away from the transmitter with our first guess. And then with the correction, we're able to fix our time sync by about 550 nanoseconds, which gets us down to about a 50 meter away location error. In this case, we actually know where the true location is of the transmitter, but we're treating the red one as unknown to be able to determine how well this technique works. All right, that arrow ended up in a weird spot. So moving on to the phase 3. Our third phase is very similar setup to phase 2, but we've adjusted the receiver geometry according to our lessons learned here. And our primary goal was to be able to try and improve the data backhaul associated with this problem. And we wanted to do that in order to be able to meet our real-time requirement. So what kind of, to frame this better, what I'm describing here is that the initial part in the top left is that the time synchronized capture happens at the edge. And then we have to send that capture back to the central node where we can then perform the cross correlation to then do all the rest of the pipeline. What we found through just kind of some experimental results on our cross correlation size, we found that about 2 megasamples seemed to work well for us for kind of a bunch of different signals. And the issue was that over our kind of LTE backhaul link, we're experiencing 2 to 3 minutes of delay for each of those captures. And so that's far too slow, and that's never going to be useful for our use case. And so we wanted to try and improve that. And one thing that we kind of had as an advantage is that we already had some machine learning classifiers that were out at the edge. And so I will admit this is a bit of an over-engineered solution to this problem. You can do a lot of gains here with just filtering and doing signal detection in general. But since I already had the classifier at the edge, I figured I would play around with it. And some of the results are fun, and so I brought them here today to share with you all. So what I'm proposing here is essentially inserting the green, which is additional filtering. And so I'm going to do this in 2 parts. The first part was the classifier. We have a few there, but for this presentation now, we're utilizing OmniSig. It outputs a nice data product that tells you, exactly where a particular signal of interest is in time and frequency. And so we can use that as a pre-filter to just slice out that signal and send only that bit back instead of worrying about sending back the whole chunk or the whole file. And this actually results in, kind of some nice gains. So that was our first thought, is just to simplify this whole pipeline. We utilize OmniSig here, we slice this out, and then we can send it back, and we perform then the same cross-correlation step, just with a lot less data. And this technique, actually, it works great. It depends kind of how dense your signal environment is, but you can get a lot of backhaul kind of improvements by just pre-filtering your data, which should not be a big surprise to many of you all. We verify that this still works, right? So we want to make sure that kind of pre and not filtered data provide the same result. And as you can see here, we're able to kind of use this in phase 3 to be able to pick out what OmniSig thought was an LTE uplink. I'm not sure whether that's correct or not, but it was very likely, some kind of transmission coming from one of our cell phones that happened to be in this area. So, all right. Basically, pre-filtering data is not anything new, right? And so we wanted to push that a little bit further and see if we could kind of change the model of our pipeline by knowing that we had access to this classifier at the edge. And so what I'm proposing here is taking that time delay estimation step and migrating that out to the edge compute. That slide really died on the on the arrows there. Anyway, I'm not sure why that didn't make it through, but basically we slice out that signal of interest and then we use a preamble lookup to be able to do our time delay estimation in another fashion. And really, what I'm offering then is because of the machine learning classifier that's out there, I can create this idea of a lookup table, say for Wi-Fi or something like that, where I have known signals of interest. And so I can use the preamble of Wi-Fi to be able to look up the sync sequence against it and determine my time delay estimation off of that. And then I never even have to send any of that data back to my central node. I can just send the time delay estimation, and the central node just has to calculate the hyperbola and pop a pin on the map. And so to test this, we did this in lab. And so we utilized Wi-Fi for our purposes because 802.11, not 1, is a very well-known spec. It was easy to build a match filter against this, and so we used short and long training sequences to then match up, and we can get subsample estimation, which is then our time delay estimation, and this works really quite well. And so I want to kind of expand this work in the future and try and be able to build out a larger signal lookup table. So in the case then where you have a known signal of interest, you can use this to your advantage and get an even better result in a fraction of the time, and then in the general case you can still operate depending. So in summary, TDOA is very possible to be implemented on these EDIS hardware. There are some kind of common pitfalls, but hopefully I've outlined a few of them in this presentation, and you guys can avoid them in the future. And there's some exciting possibilities here as these machine learning classifiers become a little bit more prolific and are available at the edge compute. There's some heavy optimizations that can be done by utilizing them. So then the next steps that I have envisioned, thank you, as I'm wrapping up here, is basically to expand that idea with the classifier, to do some quality of life improvements on some automation of the filtering, and to do some optimization of better picking my reference receiver depending on SNR and geometry from the lessons that I've learned throughout this. All right, and so finally, in conclusion, I'd like to thank all of you for your outstanding work in the open source community. I do work for a defense contractor, and so I am fiercely aware that there are many times where kind of this interaction can feel like a one-directional street, where information comes to us and it never really leaves. And I am strongly trying to fix this. And so at Lincoln, I am working really hard to try and be able to help open source a lot of our own projects that we've been working on. And I have that working through the pipeline right now. That is a long process, unfortunately, but I have discovered a fun little workaround, and so I wanted to include it in this presentation. Essentially, I'm not allowed to share the code, but as many of you know, a lot of this is purely just researching, and so I went and found this code from open source areas already. And so there are no real rules about me sending up a very well-defined appendix. And so I've included a whole bunch of slides here where if you're a developer, these kind of go through and have screenshots of all of my resources and include some information, some helpful tips for you to be able to set this up on your own. And so hopefully this will kind of help tide over before I'm able to release the code. So thank you all very much for listening. Thank you, GNU Radio, for hosting this conference, and thank you to Hope Hong, who it was a pleasure to work with her on this work.
All right, I think we have time for like 1 or 2 questions. Okay.
Yeah, thanks for the presentation. Also, thanks for using USRPs. That was pretty cool. One thing I was surprised by, so you talked about sort of the correlation and classification for improvement, but I don't know, maybe I missed it. I don't think you mentioned like errors from multipath propagation in sort of TDOA. Like, have you looked at that? And also, there's like, you know, some algorithms like Kalman filters and scented and unscented Kalman filters for like tracking, you know, movement of like the, you know, the identified targets. Have you looked into any of that?
Yeah, we have looked into some of that. A lot of that is additional work that, so I guess the underlying portion that isn't really shown in this presentation is this is one TDOA estimation for a single data point, you know, moment in time. And you can keep doing this over and over on, you know, whatever that transmitter is that you're trying to track. And that's where something like a Kalman filter can come in and have very good results because, you know, you get the average of a whole bunch of results. And then in reference to multipath, we admittedly have kind of ignored that a little bit in this research, mostly because we just wanted to try and set that up. There are, you know, a whole bunch of resources out there on being able to find multipath, especially with the cross-correlation technique. You do end up with multiple spikes in different areas, which often is due to a multipath. And sometimes you can throw out or figure out clever ways for, you know, determining which one is the valid solution. Any other questions?
All right. Yeah, any other questions? I don't see any hand. Oh.
Have you looked into incorporating frequency difference of arrival into your TDOA estimates?
Yeah, so I actually think I might have cut that out, but I haven't. We did look into, we're in the process of looking into other kind of, I would bundle that into the time delay estimation techniques, right? And that is one of them that is on the list. Phase difference arrival, frequency difference arrival, as well as kind of like Hilbert transforms and a few other things.
All right, thank you. So let's move on to the next speaker and give Sage another round of applause.
Is it up on one? Sorry, this one, it's unplugged, but I don't know. You see yours here?
All right. So welcome, Paul. He's going to talk about LibIO. So the stage is yours.
Yeah, thanks. Hello everybody. My name is Paul Saccueil. I work for Analog Devices. I'm a software engineer, and today I'm going to present you LibIO version 1. So before I can talk about LibIO, I need to talk about IO. IO stands for Industrial Input-Output Framework, and basically it's the subsystem of the Linux kernel in which you will find all the input-output devices that we couldn't fit somewhere else. So everything that doesn't fit into the hardware monitoring or audio input subsystems goes to the input-output framework. LibIO was the project I started when I joined ADI in 2014. Since then, it's seen 56 different contributors as of today. The latest version is version 0.34, and that will be hopefully the last version 0.x, because we are shifting the development to a new improved 1.x version. The goals of the library is to allow your application to interface with the I/O subsystem of the Linux kernel, abstract away all the low-level details of the interface, and give your application high-level representation of all the I/O objects and concepts. It's written in portable C99s, modular, thread-safe, runs on Linux, Windows, etc. It's LGPL as well. LibIO has the concept of backend, so your application uses the high-level API, and then you have backends, for instance, the local backend to talk directly to I/O devices connected, I/O devices like local with the kernel, talking directly to the kernel. You have backends, for instance, to talk over the network to IOD server instance running on the board, for instance. You have a backend to talk over USB, over UART. And all of this is transparent to the application. The API is the exact same. So one application, you can even compile it and interchange the backends. If you design your application to run with over the network, and then you can run it over USB, it totally works. It also allows us to run applications on non-Linux systems. So let's take Pluto, for instance. Pluto SDR has a LibIO stack with the IOD server. And we can develop applications on Windows talking to the Pluto SDR this way. So why the need for a new version? Well, in 8 years of existence, LibIO never actually broke the API or ABI, which means that the sources written and the binaries compiled back in 2014 for LibIO version 0.1 still run fine today with the version 0.24. It also means that crust accumulated over the years. There's some cleanups to do. But more importantly, some changes were just impossible to implement without breaking everything. Hence the need for library version 2, and by version 2 I mean version 1, because the version 1 was actually version 0. LibIO version 1 is developed in the dev branch in the repository. There is no estimated time for the release. It's ready when it's ready. The API right now is pretty much stable, has been pretty stable for months. But it's not fixed in stone, so if we need to change something, we won't hesitate to remove functions or something like that. The major changes include support for multi-buffer hardware. It has a new low-level samples transfer mechanism. It has modular backends. It has a new asynchronous protocol between LibIO and the IOD server. And there's a new interface between the user space and kernel space. Modular backends is interesting for, notably for distributions. If you compile LibIO for Debian, for instance, then you're going to have lots of dependencies that you may not be interested into. So now with LibIO version 1, all the backends can be dynamically loaded. They are installed at their own shared libraries. And you could, for instance, just install the backends that you're interested into. It also means that third-party backends can be written. There is a backends API that you can use and to create your own backend. All the backends in LibIO, the network backend, the USB backend, UART, etc., they only use exclusively the backends API and the regular application API. So they don't try to tamper with internal functions and structures. A bit about data streaming. So the old version 0 LibIO API, the data streaming API was a bit too high level. It didn't give much control to the applications. And as such, it was just impossible to support some use cases like multi-buffer devices. So if you are familiar with LibIO, the IO buffer object does not stream data anymore. The IO buffer refill, IO buffer push functions are gone. And IO buffer now is just takes an index of the hardware buffer that you're interested to for the multi-buffer devices, and the data transfer is handled by something else. The data transfer is actually handled by IO block objects. So the concept of a block or IO block in LibIO is basically it represents a chunk of samples in the system memory. So your application is now responsible for allocating and managing its own IO block objects. And the block can be in two states, dequeued or unqueued. Dequeued means your application owns the block and can read, write the data. And unqueued means it's owned by LibIO or the kernel, and then you should not manipulate it until it's dequeued again. So the process for streaming data, you enable the channels that you're interested in using IO channel enable. You create an IO buffer like before. You create a pool of blocks, the number that you want, specifying the size of each block. If you're transmitting, then you fill them with data. You just enqueue them, so you give them to LibIO and the kernel. You then enable the buffer to start the streaming process. And then in a loop, you can dequeue one block, read the data or write the data, enqueue it back, and in a loop like that. So if you think that this is a complicated API, there is a simpler one, which is higher level. It's IO stream object. It basically just gives you basically have two functions. IO buffer create stream to create the IO stream object. And IO stream get next block, which will always return the next dequeued block to which you can write samples or read samples from, and again, call the function to get the next dequeued block, etc. It's actually implemented on top of the low-level interface, so you could totally do that with the low-level interface as well. The major change, though, with LibIO version 1 is the asynchronous protocol between the IOD server and LibIO in the version 0.24 and older. The protocol was synchronous and ASCII-based. So ASCII-based means that there was quite a lot of data that was transferred that was not samples, just command names and things like that. And it was also complex because it required a semantic parser. It was also synchronous, which means that you couldn't send a new command to the IOD server before reading the response of the previous command. So at any time, any moment in a full duplex link, like a network cable or USB, you only had one transfer direction busy at the same time. So either you were sending a command or reading a response, but never at the same time. So that's something that changed in the LibIO version 1 with help of worker threads. So now your IOD client, for instance, the network backend of the library is going to register a command to the worker, get an ID that it can use to identify the response. And that allows the transfer to go both ways. If we focus just on the local backend and the interface between the user space and kernel space, the interface that is upstream in the Linux kernel is pretty slow. It's based on file descriptors that you read and write. And reading and writing file descriptors means copying data with the CPU, so it's pretty slow. So I was working on a new interface using DMA-buff objects, which is basically a buffer object in the Linux kernel. And instead of copying data, you just get a handle of these buffers, so there's no copy. And it also opens some gates. For instance, we could, for instance, get a DMA buff object from a receiver and queue it to a transmitter without copying the data. And it can go ever further because you could DQ one DMA buff from an I/O receiver, from an I/O device, and enqueue it to the network stack or the USB stack and get the data sent over the network or USB without copying the data again. It was refused upstream, sadly. It's still working on it, and hopefully it can be merged sometime. A bit about compatibility. So if we consider the communication between LibIO and the IRD server, basically now everybody can talk to everybody, so version 0 to version 1, version 1 to version 0, and obviously version 1 to version 1. There's also a compatibility layer that is a separate library. It replaces the old library and allows to run old application compiled with LibIO version 0 on top of LibIO version 1 and get the benefits of the new library. A quick slide, something we've been working on is the timestamp API. It's not implemented yet. Basically, it would allow to schedule transfers. For instance, we could say, let's transfer this block of samples in exactly 300 cycles from now. It will also allow to detect from the application underruns and overruns, because right now with LibIO, that's not something that can be done. A bit about performance. So I did some tests with Z-board with a gigabit Ethernet and AD9361 and 32K samples blocks. With the old library, I was getting over the network 43 megabytes per second. With the new library, 64 megabytes per second. So that's a good 50% increase, thanks to the asynchronous protocol. And then I did the same experience with the Pluto SDR. And as you can see, the speed is the exact same, 24 megabytes per second. The reason for that is the Pluto SDR is bottlenecked by the CPU and not by the USB link. So yeah, the asynchronous protocol just helps a lot when the link is the bottleneck. So yeah, all my talk was about LibIO version 1, but why should you care? Well, the whole stack below GRIIO, if you guys use GRIIO, is LibIO, be it on the GNU Radio side to talk to the board, and also on the board in the firmware. So GRIIO will have to be updated when LibIO version 1 is released to add support for the new shiny stuff like multi-buffer I/O devices, to reduce the overhead thanks to the asynchronous protocol. And that's about it, because the blocks are not going to change that much. They will still be pretty much the same. In the meantime, the GRIIO blocks will just work fine with the compatibility layer. So even when LibIO version 1 comes, GRIIO can still work fine with the compatibility layer. So there's no rush to update it. And thank you for listening. If you have any questions, we'll be happy to answer.
So,
all right, there's a question over there.
Thanks. I got a question regarding the timestamp support. So you mentioned it specifically for the 1.0 branch. Are there any plans to also add it for the 0.2 branch?
No, so the version 0 branch is basically dead now. We only merged bug fixes, and all the development is done on the dev branch. Yeah.
Okay, that's clear. Thanks.
All right, more questions. I can't look at the moment, but are there any online questions? No. Well, if there are no more questions,
thank you.
Let's thank the speaker again. Has some time to prepare.
speakers, Sebastian and Luigi. So the stage is yours.
Thank you. Yeah, let me begin with thanking for the opportunity to talk about the Allen Telescope Array and how you can access data collected with the ATA on GNU Radio. I will begin this presentation with giving an update what's been happening at the ATA in the last couple of years and how the ATA can already be used with GNU Radio, and then later Luigi will present our newly developed module, which supports the data produced by the new backend on GNU Radio. The idea for this block basically originated as a side project of my bachelor thesis. I developed an LTE detection pipeline, which will be used in the future with lunar LTE downlink detection once NASA puts their LTE base station up there. And I encountered the challenge to convert the ATA's output to standard IQ samples, which could be processed by the rest of my pipeline. So, and then Luigi came up with the idea to make this a GNU Radio block, and that's basically how we ended up here. Okay, the Head Creek Radio Observatory, which is home to the Allen Telescope Array, is situated in Northern California, about 4 to 5 hours from the Bay Area, or 1 to 1.5 hours from Redding. Basically, in the middle of nowhere, we need to be in a rural area to be protected from RFI transmission, which would interfere with our observations. The Head Creek Radio Observatory has actually quite a rich history. It has been home to multiple different radio telescopes, and the most recent one, the Allen Telescope Array, was constructed from 2002 to 2007, and currently is undergoing a refurbishment program that aims to refurbish the feeds and also our digital signal processing backend. We have many different use cases, science cases that we can investigate. We primarily focus on pulsars, fast radio bursts, and prosody research. Pulsars are spinning neutron stars that we can only see when their emission beam points towards the observer. So the result of that is a pulse signal with a very uniform interval between the pulses. Fast radio bursts are rather short, broadband, and bright pulses. And the interesting part about them is that we don't really know where they're coming from. There are multiple theories, but as far as I'm concerned, none of them could be proven this far. So that's very exciting research. And then lastly, the SETI research. The ATA is owned and run by the SETI Institute, so that's basically our bread and butter research. Steve talked about this yesterday already. We do not search for extraterrestrials per se, but we look for traces they might leave, as in transmitters in the radio frequency spectrum. So our collaborator and funder, Franklin Antonio, who recently passed away, unfortunately, oftentimes said that SETI research is not actually an astronomical problem, but a problem from communication engineering. So I think this is a good platform to talk about this. Yeah, the Allen Telescope Array has 42 dishes. They have a diameter of 6.1 meter and are of an offset Gregorian design. The log periodic feeds that are used in the antennas have a log periodic structure, meaning they have this Christmas tree structure, and different parts of this tree, so different leaves of this tree, are sensitive to different frequencies. So when we want to observe at a certain frequency, we can physically move the feed into the part of the feed into the focal point of the optics to be sensitive at this frequency. But yeah, once the data is collected by the feeds, they are sent to a central signal processing room using an analog RF over fiber link, which limits our bandwidth to, or upper frequency limit to 11.2 gigahertz. In the signal processing room, we have 4 independent local oscillators, which supplies with 4 different tunings, each of them having 700 megahertz. These IF signals can then be fed into one of our 3 signal processing backends. We have the SNAPs, GNU Radio, use RPs, which I will talk about on the next slide, and then lastly the RF SoC boards, which are currently our main backend. So how can GNU Radio be used at the ATA today already? First of all, there is a GNU Radio module called GRATA, which enables an observer to use or to interface the observatory in GNU Radio Companion, meaning we can steer the antennas, tune local oscillators, and so on, basically conduct observations. Data can then be collected using our 2 USRPs. We have a N320 and an N321, which supplies with 200 megahertz of bandwidth for both polarizations for 2 antennas. And then lastly, the GNU Radio 1 server that can be used to process this collected data. Yeah. Just let me give a brief summary of the refurbishments. Currently, we have 25 operational antennas. 21 of them are new refurbished design and cryogenically cooled. That's why the feeds are placed under a glass dome. The glass dome maintains a vacuum which enables cooling. Their temperature is about 70 Kelvin. And we still have 4 old non-cryogenically cooled feeds. We are planning to have 30 feeds operational by the end of this year, and Alexander Pollack and Sarah Schultz, who are at the observatory right now, are probably building and installing feeds right now as we speak. Yeah, this is a slide that is mandatory to show when people are talking about the refurbishment program. On the left-hand side, we have our signal processing room before the refurbishment, and as you can see, it was wild. And on the right-hand side, we have a very neat, tidy, and operational computation room. Yeah. As I said, the refurbishment also involved a refurbishment of our DSP backend and the employment of our RF SoC digitizers. They are used, as I said, for digitizing the signal, applying delays for beamforming, and they also apply a polyphase filter bank. Operations that are currently supported by our backend is correlator mode baseband capture, which basically writes raw voltages to disk, and then lastly beamforming. Yeah, let me begin by talking about the correlator. We have 20 antennas connected to this backend, which means we have 210 baselines, which we can cross-correlate, and this forms an image of the sky. Integration lengths of 8 milliseconds to open-end are supported. The backend is XGPU based, and yeah, we can see a picture of our correlator in action on the right-hand side. Another very useful use case for the correlator mode is the calibration of the antennas, which is required for beamforming. Yeah, and that's basically how the calibration looks like. On the left-hand side, we have cross-correlations of multiple antennas as a function of frequency. And as you can see, those are squiggly lines. An offset from 0 means a phase difference between the antennas, and a slope means a delay in time. So we have to compensate for the phase offset and the slope to calibrate and synchronize the antennas, and then afterwards we can add up the samples to beamform. This is a simulation of the beam pattern of the beamformer for the Allen telescope array. Yeah, the beamformer is in use since December 2021. It is performed by Blade. Blade stands for Breakthrough Listen Accelerated DSP Engine, which uses NVIDIA GPUs and with CUDA. And it was actually developed by this gentleman, Luigi. we can currently synchronize 8 beams in real time, and the data product, or the data that is produced by the beamformer, is a modified GAPT format, which our newly developed GNU Radio module aims to convert into IQ samples. Okay, let me go over a couple of achievements that we have reached using the beamformer. Firstly, we were able to see a couple of Mars orbiters during a 60-second observation. We saw Mars Odyssey, the Tianwen-1 orbiter, Mars Express, Maven, and this, of course, is a very nice way to show the capabilities of the ATA, because after all, that's what we are looking for at SETI research, but of course we're hoping to see something that humans did not build. And another observation that has actually gotten a little bit of media attention is our observation of Voyager 1, which is, of course, the furthest away human-made object from the Earth. We were able to detect that on July the 9th, 2022, during a 900-second observation. And again, this shows the capabilities of the Allen Telescope Array to detect technosignatures. If you're interested in that story, I can recommend you to check out Wael's GitHub to give it a little bit more attention. Yeah, that's it from my part. Let me hand over to Luigi to talk about how the beamformer data can now be used in GNU Radio in the future.
Thanks, Sebastian. As you can see, the ATA is basically a very large SDR with some software trickery. We can possibly use all the output from our infrastructure with software developed for SDRs like GNU Radio and others. So thinking about that, we said, how can we facilitate this for the user? Because most users don't know how radio observatories like the ATA or others work, so they use some shady files to communicate with each other that are not compatible with the current tools. So we saw an opportunity to develop something and improve the community. This is some examples of data produced by the ATA. This is the JPAS, the new generation NOAA sun synchronous satellite, weather satellite. So it will circumnavigate the Earth every 88 minutes, and will scan the surface in multiple spectral bands and transmit that data back to Earth using an X-band data link called HRD. That is 30 megahertz bandwidth, because it needs the bandwidth to beam the data back to Earth fast. It is interesting to us this because I wrote the modulator and decoder for the satellite. So in the future, we are aiming to decode this file and produce images with the ATA. If you want to learn more about that, a DEF CON talk in 2018, I guess. Another example is this time using the beamformer. We even though we are in a valley with lots of mountains, we still can see some LTE basebands from nearby towns. So Sebastian, after arduous amount of work, found some of these signals, and we could point all the dishes. I think this was a 20 antennas observation. We pointed all to the source, and we received this with the beamformer. It's a 20 megahertz LTE downlink of LTE band 2 and 1900 megahertz roughly, and you can see nicely all the blocks of the downlink being presented here. And this is the ATA tracking 20 times speed of the JPAS-1 telescope. So you can see multiple antennas moving. Just the one in the center is doing other things. Yeah. So now talking about more technical stuff. So the file produced by the telescope is a GUPI file. It is basically a raw file with some MIME field with headers. So you have your header that is basically ESC2 text data, and followed by the actual data, metadata, the header, and then the data after the header. So to decode this, you basically read the standard amount of header bytes from the file, and then you parse. We can discover here the number of time samples, number of frequency channels, because this is a mixed domain file. So we have pre-channelized data. So instead of a time string, a single time string with time domain data, we have channels, frequency channels with some time data on it. So it's not, this is not what most GNU Radio blocks expect. They expect purely time domain data or frequency domain data. So that's an incompatibility that we found and we are aiming to solve here. Here's a diagram of how it works. So interleaved complex samples with time and frequency also interleaved. Basically a NumPy array, if you're used to that. And they can be represented as floats or integers, depending on what you are trying to record. So here we wrote GR telescope, a new out of 3 module that can read these GOP files. So telescope, you can do an observation that is saved to disk, and after it's saved, you can easily open that with our block, and the block will internally read this header, metadata header. It will parse the data, it will get the data from the file, and also do DSP to convert the mixed domain data into a time string domain that the GNU Radio is expecting to. So this is a sample flow graph. You can add more plots like Costas loop or phase recovery, so you can demodulate some telescopes like NOAA or any PSK or any other modulations, basically SDR. So, and current implementation is CPU based and is getting 96 megahertz, 16 bits floating point with half real time. The bottleneck here is the conversion from 16 bits to 32 bits, actually, not the other DSP things. Yeah. So the block is very simple to use. We are abstracting away all the complexity of reading the file away from the user, because we can't expect you to know this file very well. So here you can choose the type, the output type, and everything will be cast automatically. The file name, where the file is located. The repeat, like very similar from the file reader of GNU Radio. And also now the differences, the polarizations, you can choose X polarization, Y polarization, or both polarizations, X, Y, as an output. And also the number of aspects. Number of aspects can be number of antennas or number of beams, because sometimes a GUPI file has multiple antennas or multiple generated beams. So you can choose which one you want to output with this block. And lastly, you can choose the channel binning. So the file data is already pre-channelized, and sometimes we have a large frequency bandwidth. So instead of just doing computation just to filter their data afterwards, we gave the user a possibility to lower to specify which channels they are interested in. Here, we can also synthesize circular polarizations from the XY polarization by summing it. This is currently not available with the ATA because we need some calibration of our backends to calibrate the both polarizations before this actually working. We have some development code that can do this with a field filter to make things calibrated, but we are planning to add this capability to the ATA, so both polarizations are indeed calibrated with each other, and you can synthesize right-hand circular polarization or left-hand, so this can be useful to decode other satellites. So here is an example of the frequency binning. Here we are choosing half of the data, so 48, channel 48 to channel 144. That is basically from 192 blocks. So basically the half. And here you can see visualization. So in the left, we have LT channel in the middle in 96 megahertz bandwidth. And the right one, we have 48 megahertz with the LT channel in the middle and larger at this time. And lastly, we have the aspect. If you have, for example, this recording has multiple antennas, so we can choose antenna number 1, and we just pass 1, and it will just give the data from aspect 1, that is antenna 1 in this case. So this is it. You can download the module now from GR Telescope. We are also making available some ATA recordings. If you have something interesting that you think could be a nice experiment, you can come talk with us and we can see what we can do, right?
Thank you. So I think we have time for a question or two. Are there any?
So the before-after picture, you had the, first off, excellent cabling job. Love the before-after picture with the before and after. Where you go down to your back end, the data server, where you had all the RF socks. Can you tell me how was that actually cabled up to the antennas? Do you have any more information on that?
Sorry, could you maybe repeat that?
So there was a slide near the beginning where you had like a before and after with like the wild cabling and all that. Yeah. So if you go to the next, so how do you guys actually get it connected up to your up to the antennas then from the data center?
Oh, you mean on the right-hand side?
Yeah.
Yeah. This picture is deception. It's not in this picture actually. There are basically the same racks in the background on the right-hand side of this picture. So well spotted. They should obviously be connected to something. No. So the things that you can see on the left-hand side here are amplifiers which condition the signal to be digitized, and in these missing spots, that's where the RF sock board enclosures go, which well are our digitizers. Yeah, thank you.
All right. So thanks to speakers once again. And now we have 3 lightning talks. And the first one will be by Keith. You've seen him last year, maybe? So stage is yours.
Slides are already up. I like it. How y'all doing? Good afternoon. Ooh, that's coming out good. My name is Keith. As previously mentioned, I'm the CTO and co-founder of Rampart Communications. We're a company, here we go, advance the slide. We're a company that's innovating at the intersection of privacy and InfoSec, at digital signals processing, and at cryptography. All of those sort of very fundamental sciences. We're an early stage and growing company in that sort of unique intersection. I've got one central message today. So if you hear nothing else, hear this. We're hiring, come build with us. All right. So if you are a mathematician or a physicist or a EE and you want to work on fundamental advances in information theory, come build with us. If you are an embedded developer or an FPGA developer, I know you're out there, or a security researcher in general, and you want to build the most performant and secure radios on the planet, come build with us. If you're a tech writer or an ethicist or a leader of people, and you want to build a diverse culture and an engine that rivals that of Bell Labs in its heyday, come build with us. It's a rare opportunity to find something like uniquely technical and broadly applicable and impactful in privacy and security, and that's where Rampart sits. We're building things for abundance, not for scarcity, right? It's borne out in our T-shirts too. It's a pithy restatement of the capacity theorem, bits per second per hertz per watt per error, right? It's the fundamental constraint of all digital communications. It's the figure of merit that we are chasing after. All right, so that's my central message. You've heard that. To give you a peek at what we're building, last year, if you saw my talk, if not, still up on YouTube, I think. We introduced UBDM, a technology that is baseband encryption directly on the symbols of your signal, physical layer encryption. It's both purely cryptography, it's a block cipher, as well as being purely lossless from a DSP sense. So 256 bits of security, while having zero impact on any metric that you'd care about in the DSP world, SNR, occupied bandwidth, cluster variance, anything. And we have a demo out back if you haven't seen it. We had the demo last year as well. We've made a few updates. It's a pretty cool thing. If you're building networks like continent spanning or world spanning satellite networks, Starlink or Kuiper or Viasat or what have you, you need protection for both your user data and your control plane, the heartbeat of your network. That's what physical layer encryption can provide. If you're building medical IoT devices and lives are on the line and you need a way of communicating into and out of a device in a way that enhances privacy and is fundamentally secure, this is physical layer encryption. We argue that there's no better defense. There's nothing more fundamental than the PHY layer, the physical layer. And that's what we're building, and that's just UBDM. UBDM is a world first, but it's not the only product we have. It's, to borrow a phrase, we are, at Rampart, we turn a lot of things from impossible into late, right? So UBDM, not thought possible before. We also do interesting physical layer key exchanges and quantum-proof key exchanges that are performant and secure as well. A couple of the many things that we're building. All right. So last year, I briefed this, and again, the slides are available on our website. I'm happy to announce that we felt like we left out all the remote attendees. So for you this year, you can now use UBDM as a service. So you can go to this URL, I'll share it in the chat afterwards, upload your own signal, encrypt it, we encrypt it for you. You can download it, apply channel impairments or mess with the crypt if you really want to. And then upload for decryption and compare A to B. We're scientists. We show, don't tell, right? You can validate using the service. So this is free and open to use. So please have at it. And RIP to my cloud bill, I guess. I think that's all I have to say. I just want to say thank you to the organizer of the conference and especially to the contributors to the project. It's one that we're very proud to support at Rampart. And yeah, we'd love to talk to you. So see you at the booth, see you online, see you in the chat room. Thanks.
Thank you. So I guess we can just continue with the next lightning talk speaker. Is this you? So, Neil. Yeah. All right. So next speaker is Hollis Neil, and the stage is yours.
Yes, they should have been emailed, but I can just ramble as well.
Well, if the third lightning talk speaker would come up right now so we can prepare things in the background, that would be helpful.
I don't, but that's okay. Yeah. Minimize. We'll just leave that there. Awesome. So I'm Hollis Neal. I'm from the Oak Ridge National Laboratory, and in particular, I'm in the Resilient Communications Group. And so I was kind of hoping to talk about two separate things here. So one was kind of what do we do at a national lab, and in particular, what are my group's contributions to that? So if you look around the conference, you'll find a bunch of us walking around and playing capture the flag and such stuff like that. But the first thing I want to talk about is one technology that we're working on at Oak Ridge is satellite downlink. It's a very simple, just X310 powered ground station that's specifically meant to be an interface between kind of resilient communications research, so for long distance communications, and then also for integration with other groups in our at Oak Ridge that are the remote sensing group, and in particular that's for disaster relief applications. So it's when we have a hurricane or something roll through and there needs to be rapid response to an area, and particularly for efficient distribution of resources. What we're hoping to do there is to have a very low kind of latency downlink directly at the lab that goes directly to the analysts that are looking at when the power lines are going down and stuff like that. And specifically, we'll send where the power, or where people where things are most needed. So that's kind of a use case there. We have pictures and stuff of that if you want to come by our booth and see and learn more about it. And then in addition to that, so our group in particular, we like to focus on really the intersection between machine learning, artificial intelligence, and communications. So we do a lot of work in that area. We do a lot of work with protocol development. So whenever new standards come out, we like to kick the tires on them and see how they are. We have a very strong high performance computing, a very strong cybersecurity presence, and a just really it's a very wide array of backgrounds. So we have many projects, a lot of really interesting projects, particularly in the national security sciences kind of world. So if anybody wants to get involved with any of those projects, just come and talk to us. And with that, I'm going to go ahead and be done. I know I probably went way too fast, but yeah, so thank you.
Well, in that case, there's time for a question. Anyone? No? Well, in that case, we can go on with the third lightning talk speaker and speech. Where is he or she? Okay, I tried to pronounce it correctly. Javad Karabi. Oh, that's you? All right. So. And so that's our third lightning talk today by Javad.
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 Javad. All right. So the stage is yours.
Okay, cool. Thanks. All right, so this isn't as like advanced and stuff that like all of y'all got going on over here, but I got into radio like a year ago. I discovered my love for it whenever I joined Fathom 5. So I just want to talk about like something cool that I do with it. Okay, so Fathom 5 is a company that we're at the intersection of AI and Greece. So we like to we do like security for things that control physical things like pumps, motors, whatnot, PLCs. So one of the radio protocols that we work with a lot is AIS, which is a protocol that ships will use to inform each other every few seconds about, sorry, I like ran here from my hotel, about like their position, direction, and all that other stuff. So here, this is the AIS. The center right here is 162 or I think megahertz or something like that. But then minus 0.25 is one channel, and then plus 0.25 megahertz is another channel. One of them is, I believe, specifically for ship-to-ship, and the other one is ship-to-shore. So what I'm going to show also, FYI, is taking an AIS data and then split automatically in real time, taking each message and then putting it into its own file. That way you can open, like in URH or something, you can open per message, you automatically have the file separated. Okay, so yeah, we have our, I had a pre-recording, so that's a file source. Then we just, oh yeah, there's a frequency translate because of the DC spike thing, so I offset and bring it back down. Okay, so right here, what's going on is you can see on the left AIS1, AIS2, and on the bottom left and bottom right, you have where I'm. So what I do is I squelch. I squelch and I squelch like whenever the power is not at a certain level, then I don't have it trying to demod it. And so what you see here is just an output of the squelching, and this is the graph that does it. So at the top, we take our AIS center feed, then we do a frequency translate minus 0.25 to bring it down to AIS channel 1. So now we have AIS channel 1. Then bandpass for just to get rid of some of the stuff that's left and right outside of it. Then this is where we do our squelch. And then it goes to that sync AIS channel 1 squelched. This is channel 1 squelched right here. And what's going on here is the formula for the squelching is complex and mag squared, then a single pole IIR filter. So what's nice is that I pretty much just like from the docs, they say, oh, that's how it's done. So that way I can go here and I can look at, because this has two inputs, one's the raw feed and the other one's the squelched. This lets me compare, okay, am I squelching too much? Or is my ramp too much or too little or whatever, the alpha and all that stuff? And I can look here and I can say, okay, I'm gonna adjust this, and I can watch it in real time as it does that, all that stuff. So, okay, so now we have that, and then we take that squelched, and AIS is GMSK, so we do GMSK demod, then it's NRZI decode, then we flip it, add, like, because it's NRZI, it's going to be inverted, and I like to see the 0 be, at 0. So what we have to do is, first we flip it, then we bring it up 1, and then we turn it into a character, and then we can do the correlate access code tag because AIS has a known preamble in the front, and we put all 3 into the time sync so we can see. So right here, I have the GMSK demod and NRZI decode stages turned off in this example, but the actual final output you can see in the front. There's the AIS preamble right there, and then there's a payload following. Oh, okay, yeah. And so, okay, so, and then what I also do is I save, I add 48 to the 1s and 0s. That way they turn into ASCII 1s and 0s, and I save it to a file. So now I can see a file with 1s and 0s in it. These zeros, there's a ton of zeros that shouldn't be in there because the squelching should have gated it or something. But and then the part that is, I think, the coolest is we take the squelched, then we put it, we trigger based on if there's like data, well, we save it into a file. And then now in real time, each of these is a unique AIS message. And so you can see these are examples of unique AIS messages. So the squelching begins the saving to a file, and then the end of that file is whenever the squelch, or whenever the power level goes below the squelch level. And so now each of these in real time, I just have like hundreds of AIS messages that are just being saved into their individual files. And yeah, the reason I did this is because previously I would record it, then I would by hand go and cut it apart and stuff. And this is useful for us because now we can test AIS sensors and stuff that we have with real data that from Galveston is where this is from. So, cool.
All right, thank you. We have a quick break right now, so if you have questions, the last speaker is still there. Besides, we will be back at 3:20 for the next session with more speakers. So, see you soon. So, welcome back from our little break. I hope all of you found a new cup of coffee or whatever you needed. We start with the next session today, and now we have Jean. Okay, I will try and learn, but still, the stage is yours.
Many thanks. First of all, I know it must be a cliche, but I have to say how happy I am to be here attending the GRCon. After being using GNU Radio for so many years, since I was like doing bachelor's. And today I'm going to talk to you about a little bit about what we're doing using GNU Radio to do experiments in the millimeter wave range, more specifically in the initial access. If not familiar with all this millimeter wave jargon, don't worry, I'm going to walk through all of this during the presentation. My name is João Santos. I'm a postdoctoral researcher with the Commonwealth Cyber Initiative. We are a research institute associated with Virginia Tech in Northern Virginia, just across the Potomac. Here you go. In a nutshell, what we did with this work, right, was to enable to expose the control over different millimeter wave frontends in GNU Radio that use the GPIO interface, allowing them to be controlled on the fly inside of your flow graphs. Beyond that, once we're able to control the radios in the millimeter wave, we also did a complete initial access control loop, allowing them to do two different frontends to be able to locate each other and find the best beam direction to communicate. And with that, right, we enable a bunch of different high-level experiments where you can play around, you can point your beams to different regions, to different points of time, and you can also test around design trade-offs in your initial access procedure, tailoring that to suit your needs. First of all, why should you care, right? We're going to go a little bit about our motivation, then our implementation in GNU Radio. So also show you some of our experimental results, and finishing with the current state of this contribution. First of all, you're happy doing your experiments in GNU Radio, right? In the below 6 GHz band. You create your DSP chains, place your blocks, and everything works most of the time. Until like you start playing around, move your radios a little bit to the side. If you put them like 2 feet further away from each other, then it would work. You start playing around with the gain to make sure they're happy, and then you increase the gain too much, and then you saturate the receiver. But alas, no, it's still great for broadcast experiments, and it works great. But let's say you're bored, or you want to explore the millimeter wave band, right? You want to break this directional communications barrier. What do? It's very likely that you're going to end up hooking up your current setup and your current CRs and your code base to millimeter wave frontend, which is an equipment that up-converts and down-converts your signals that outputted from your SDRs, now become like any intermediate frequency, and you bring it up to the millimeter wave range. This kind of equipment usually also possesses a patch antenna array with a bunch of different elements and allows you to change and play around the code books so that you can point your signal to different directions. It's amazing and it works. And it's great for characterizing the environment, the equipment. Some people even do this for creating some sort of radar equipment, even inside of GNU Radio, and it's wonderful. But as you start playing around with this, you soon realize, okay, if I move my radios around, not only have to worry about the gain and whatnot, but now the direction that I point my signal is also important. So you need to steer your beams from both the transmitter and receiver so they can find each other. But as of now, we really only have like manual ways of doing that over this GPIO-based millimeter wave front ends, right? So that you generally have to, out of band, outside of GNU Radio flow graph, you have to manually say, yo, please move there, please move here. But okay. However, these may not be practical in some scenarios. Let's say if you are moving around, if you're a car or on a robot or if you're a handheld device, these will not cut the chase. Especially if you have multiple users going to different directions, you can't really do this in real time manually. That's why commercial millimeter wave equipment and the mobile standards that operate in a millimeter wave range, they include what is called the initial access procedure, whereby both transmitter and receiver radios, they scan sweep to different distances and find each other, right? They keep transmitting information back and forth. They find the direction that works better for both of them, and they establish a handshake, and they finally start transmitting information over the ping with the highest, ping pair that has the highest SNR. It works great. But I think this is a kind of a Mac level handshaking procedure that I couldn't really find in GNU Radio. And you're like, okay, what to do next, right? You can kind of control the pings manually, but can we do more? Yes. So we started to delve deep into the millimeter wave frontends that were under possession and realized that, okay, yes, they actually allow you to do this online runtime error configuration, usually using their commercial closed source frontends or controllers that are super expensive. But they allow you by hand to play around with the ping over their SPI or GPIO interface. Then you thought, okay, so the millimeter wave frontends, they have the GPIO control. The GNU Radio supports and allows you to play around with GPIO commands, and USRPs also have a great GPIO interface, if you remember the presentation I had from the NA guys on Monday. So we then connected the dots and created what we call Stamina, a software-defined millimeter wave initial access. Who doesn't love man-made acronyms? So with Stamina, we do two different things. First, we expose and abstract the control over the millimeter frontends over GPIO instead of GNU Radio, right? So that you only have to focus about the things you care for your millimeter wave experiments, the pings you're pointing, and so on and so forth. And we also closed the loop and created a complete initial access control loop, pun intended. So first, when we started to look into the GPIO interface and the different millimeter wave frontends, we soon realized, okay, so they basically use different pings and different ranges of pings to do the same things, right? Set a ping 5 to different directions, whatever, transmitter, receiver. The different pings in different places. So to do the same thing, we thought, well, can we parameterize that? Can we expose this in a way that users can use it and just tailor depending, with little modification, can use it with their own equipment? To do so, we created an abstracting block in GNU Radio that you can feed with information over how your particular millimeter wave frontend works using a configuration file, and then you're free to go. In addition, it allows us to reconfigure the pings you're pointing for transmitter and receiver at runtime using asynchronous messages. And then, great, with this, you can basically start controlling your millimeter wave frontends within GNU Radio. Great, but we were not happy there, right? We wanted to go a few steps after that. So we created the whole control loop structure, where at the same time we sweep over different pings, right, for transmitter and receiver, while we collect all this information in terms of the received signal strength and label that with the current pings for transmitter and receiver. And based on the highest value, we decide, okay, let's use that given ping pair for communication. And we look so that we can adapt to changes over time. Here, a little bit about our realization in GNU Radio. On the top and bottom, you can see our WebFilm transmitter and receiver. And in the center, we have the blocks for control, measurements, and decision, right? I think despite being a rat's nest of control messages being exchanged across different blocks, it's working great. And we also leverage the beauty and versatility of GNU Radio that allows us to play and change with those parameter variables during runtime. So with this, we can, almost there. Okay, there's much time left, I have to sprint. But then again, with this, we can like reconfigure and arrange how this works in terms of the pings we sweep, how long we stay there, so on and so forth. Here, a picture to illustrate our very messy deployment with both millimeter wave frontends, and in the center we have our host machine with running GNU Radio, our out-of-tree block, and USRP, and the millimeter wave controller unit that has the GPIO interface. Skip this. And here, finally, we go to like some of the results we got, right? So we start exploring how systems behave. So first we want to validate whether everything was working. So we set up the two radars pointing at each other, started playing around with the tilt and the orientation, and start to identify how we obtain higher power from different directions, and also be able to observe the benefits of running an issue access procedure over doing this manually. Because by doing that, by probing the environment, we'll even be able to leverage reflections on the walls to get higher signal power than we would if we're just pointing to whatever thought would be best. And we didn't stop there, right? We started playing around with the flexibility of the initial access procedure. For example, shortening the time we stay, transmitting control frames gives us more throughput for the payload, and vice versa, which allows you to tailor your initial access to your own needs. You may sacrifice accuracy to increase the throughput if you so want. But I know this is still not finished, it's still work in progress. A few more things we would try to accomplish in the future. For example, replace the synchronous message passing by something else. While they work, they're asynchronous, and this is a problem for this kind of strict control schemes. And we also want to include some sort of mux or selector to change between payload and control frames during runtime that we don't really know how to do. So if you have any suggestions how to accomplish that, or if you're interested, please don't hesitate reaching out to me. And if you want to use all this, is all available open source in our repository, but you probably would need a couple of millimeter wave frontends to really use it. But luckily, we also have an open testbed open for remote experimentation. So if you're interested, please reach out.
All right. While we have time for one question, next speaker may already come up and prepare. So are there questions? No? Oh, all right.
So have you looked into like any of the 802.11 protocols that are involved with beamforming?
Sorry, sir,
have
can
you
you
looked
repeat?
into any of the 802.11? I guess there's AD and AY that have.
No, we didn't really look into Wi-Fi related standards because like a whole motivation for this was actually targeting 5G and 6G systems, so we can't really talk say much about 802.11.
All right. Well, I can see we have time for one more question. Okay. In that case, thanks to the speaker again.
No, no. This is just my notes.
All right. All right, so let's move on to our next speaker, Sarah Pearson, and the stage is yours.
Thank you. I'm going to try to go a little bit quickly because I know my talk goes about 3 minutes over, so I apologize for that in advance. But hey everyone, I'm Sarah Pearson. I'm a PhD candidate at the Georgia Institute of Technology. I'm in the Planetary Habitability and Technology Lab in the Ocean Science and Engineering Department. I go by Lola on the Element chat. If you guys want to reach out or talk to me about anything after this presentation. But without further ado, I'm going to tell you guys today a little bit about wireless acoustic data transfer through ICE, facilitated through model integration with GNU Radio. So as you may have guessed by my title, my thesis work is in modeling realistic acoustic data transfer through ICE. Originally, this project began as an auxiliary communication system for future European drilling missions. For those who don't know too much about Europa or planetary science, Europa is a moon of Jupiter. This is the planet you see in the animation here. This animation is a real compilation of photos from NASA, which is kind of cool. You can see the moons going around it, but my work began focused on the one moon, Europa. You guys may have seen this image before as well. The only thing that we need to know is that Europa has a thick ice shell on the outside with a liquid water ocean underneath. The idea is that if a lander is sent to the surface of Europa with a probe that can drill through this 15-kilometer plus ice shell, then we would need a robust wireless communication system. And harsh polar environments on Earth offer a great analog for portions of Europa's ice shelf. So this leaves us with the question of why? Why study the potential of an acoustic system? And the answer is that acoustic transducers have potential to be less power hungry than electromagnetic communication systems, and they are low frequency. This means long wavelengths, which lends itself to environmental robustness. In polar regions on Earth, we see ice that has impurities, inclusions of water, salt, salt crystals, air bubbles, cracks, you name it. In these unpredictable environments, typically RF comms are attenuated to highly for long-range transmissions. So the more robust a system can be to these features, the better. And even more exciting is that an acoustic data transfer system through ice has potential for use as a positioning solution for under ice ROVs and AUVs. These are remote operated vehicles or autonomous underwater vehicles like the one you see here. This is just a little plug for my lab. This is IceFin, the ROV of the lab I work in. This robot gets put through a borehole in Antarctica and goes to swim around underneath the ice, taking all kinds of scientific data. But one issue that IceFin and all other underwater, under ice vehicles encounter is that there is no GPS signal through ice, leading to navigational or positional drift problems. So you can imagine why that would be treacherous for an expensive vehicle being sent to do cool work underneath the ice. So a low-power wireless acoustic system that could communicate through both ocean water and ice has exciting additional applications, not just outer planet ones. But before we can talk about the model, sorry, my notes here are not changing. There we go. We have to, if we want to talk about the origins of the acoustic model, we have to talk about ice characterization. Acoustic research of ice has been taking place since at least the 1950s, and some of you may be familiar with one of the first techniques used, which is still used today in many fields, impulse characterization. This is one of the easiest ways to characterize a system, simply at least with pretty robust results. This image on the right is an example of some acoustic data taken at Blue Glacier in Washington around 1965. The waveform was recorded after detonating a seismic blasting cap near the surface, with the receiving hydrophone in like a 50-meter borehole next to it at 2.5 meters away. But speaking of characterization, as time went on, it became more complex. So researchers immersed transducers in boreholes and propagated signals both vertically and horizontally in ice, recording data for frequency sweeps and sine waves and et cetera. Careful analysis of ice sections were conducted, resulting in a comprehensive understanding of ice crystal growth and how ice crystal geometry changes with respect to the environment in which it was found. And finally, at least one of the last things I'm going to talk about as far as analysis goes, analysis was also conducted on ice cores, giving us a better understanding of the structure and entrainment of impurities in ice. Here's an example of just a piece of one of the longest ice cores ever drilled, which was over 3 kilometers long. It's just wild. I thought that was pretty cool. And with all of this analysis and data, researchers were able to find empirical equations to characterize parameters of interest in ice. Things like sound speed, which is dependent on the direction of travel, as I mentioned before, longitudinal or transverse. The crystal structure, what kind of grain boundaries are we dealing with? How many air bubbles are in the ice? What kind of impurities are in it? How much salt does it have in it? Etc. So it's using these empirical equations that an acoustic model can be put together. So we know about the characteristics of ice and we've identified their acoustic effects, but how do these measurements turn into an acoustic model within the context of an entire system? A nice way to describe it all concisely, I think, is a link budget, where PR and PT, received and transmitted power, P is path loss, A is attenuation loss through the media, T is transducer loss, and C is coupling loss. I'm sure a lot of you guys are familiar with this. But attenuation loss in and through the media of sound propagation is the model backbone. This is where the empirical equations for through ice characterization come into play. Attenuation loss in ice has a few major contributors, which I mentioned in passing: absorption, grain boundary scattering, air bubble attenuation, and salt attenuation. You can think of these components almost like a channel model. Now, before I explain how I integrated this channel model of sorts with GNU Radio, I want to take a step back and reiterate that my goal in using GNU Radio with this research work is to have a customizable and easy to use test bed that would allow me to test and ultimately optimize the data transfer capability of a wireless acoustic system through specific types of ice. With that being said, this is where we finally get to talk about GNU Radio. So first I started with an out-of-tree module, and within that module, each component of attenuation was turned into a block. Each block has a few parameters that represent the environment of interest. I won't spend too much time explaining each of the parameters, but the important takeaways are that one, attenuation is usually strongly linked to frequency. So frequency is the input to the blocks in the flow graph. And two, the user-defined parameters of each block are bounded for most locations of interest on Earth. And what I mean by that is if you wanted to model a temperate glacier or sea ice or Antarctic ice, there's very likely data available to you that will give you an upper and lower limit on what those user input parameters should be. And this is one of the major features of the acoustic model. Because the blocks can be cascaded and the inputs customized, attenuation through different kinds of ice can be computed if you just input your particular ice parameters. So this is just a simple flow graph that you can use, input a source that represents frequency, have the blocks just there, and you can see the attenuation total that comes out on the right-hand side. In the time sync, it comes out in decibels per meter. Pardon me, technical difficulty. And here is an example of how you would integrate the attenuation blocks into a larger system. This is an FSK modulated flow graph modified from Barry Dugan's tutorial. Thank you, Barry. Using the acoustic attenuation blocks, which are highlighted in the yellow box. So again, the acoustic model is an aggregation of equations turned into blocks, put together into GNU Radio such that a modulation scheme can be applied. This is the novel part of my research. Very recently, a couple researchers have sent modulated data through ICE, but modeling and trying to optimize that process hasn't been done. So what this flow graph does, I'm sure a lot of you guys are already familiar, it takes a source, this could be a text file, random source, etc., and modulates the data. A PLL frequency detector is used to pass the acoustic attenuation blocks that input frequency that they need. And the blocks calculate the attenuation in dBs based on that frequency and a few input parameters. And finally, the dB reduction is calculated and applied to the amplitude of the signal using another block I made here called dB reduced received signal. And then the rest of the flow graph carries out the demodulation. And finally, we are on to the model results. So note that while I just showed you guys an example of how to use the blocks in a flow graph that includes a modulation scheme, right now the model isn't perfect. And it's going to continue to be updated and constrained, hopefully with some benchtop lab setups in the near future, until it gets to a point where it's within, until it gets to a point where within the frequency range of interest, we're getting the level of accuracy desired. So before I begin to explain these plots, it's important to point out that my model is only valid for 1 to 100 kilohertz. But the frequency ranges of interest for acoustic communications through ICE are estimated to lie in between the 5 to 35 kilohertz range. I'm comparing to acoustic attenuation through sea ice here. These values were calculated by Lang-Levin in 1969 on the left-hand side. Notice that while my data on the right has the same curve as the Lang-Levin data, we actually have a higher attenuation calculated. The acoustic model works well for 1,000 to about 50,000 hertz. But at 55 kilohertz, we get a true divergence that starts occurring. Here I plot Lang-Levin's data in gold on my own plot. We have a 4 decibel difference at this location that grows with the frequency value. I have thoughts on what this might be, but I think I'm headed a little bit over time. I'm getting close to it at least. Okay, oh, wow. Sorry, I was talking a little bit faster than I expected then. Well, I can talk about that a little bit later. It is very possibly due to the salt types or how thick the ice was that they were transmitting through. I have a couple ideas on why that might be the case, and that'll be incorporated into the model as I continue updating it. Moving on to glacier data conducted by Westphal. Notice that the simulated results in purple are actually about an order of magnitude, 2 orders of magnitude lower than the experimental result, excuse me. No, just one, pardon me. Also notice the pink line of data. This is the same as the data in purple, just multiplied by a factor of 10. Here it is just a little bit closer. So we have an anomaly in the 2 to 4 kilohertz range. and a little divergence at the tail end. But generally, the researcher Westphal hypothesized that Rayleigh scattering was the main contributor to the attenuation he calculated at Blue Glacier. And to a decent extent, we see that mirrored in the simulation data, if only it were the order of magnitude larger across the board. And I think this may actually be due to something that Westphal calls lensing in his paper. At his field site, the ice had significant and distinct layering. There was extremely coarse ice. There was very bubbly ice that was described as nearly opaque. It was described as looking like porcelain almost. And then fine, almost transparent ice. So the additional attenuation due to an interface change of that type could be around an order of magnitude based on what I've seen in the literature. But this is another area of improvement for the model moving forward. And finally, this is an example of my model compared to Antarctic ice. This data is from SPATS, the South Pole Acoustic Test Setup. If you guys haven't ever heard of that project, it's really cool. They were like the precursor to a neutrino observatory set up in Antarctica. So some really interesting work there. This team calculated attenuation for horizontal propagation through Antarctic ice with respect to depth. The ice near the surface was reported to be just slightly warmer than the ice deeper down. This is why we see the slight decrease in the pink triangles on the right-hand side. That is my data, and that's how it compares to theirs. So pretty decent in Antarctic ice. And that was the info I have to wrap up my talk. As far as future work goes, I plan to update the code in the ways I mentioned briefly when I was talking about the model results. But I also hope to be able to account for in the future TVR or OCRR and some phase change information if possible. But this information is not something I've found in the literature for through ice transmission. So it's likely that this is something I would have to document in the lab myself or in the field on a benchtop lab setup, I mean. And I also have plans to work with a low-power transducer in the frequency ranges of interest with a colleague at Georgia Tech who has developed a low-power, cheap transducer in that frequency range. So be on the lookout for some hopefully interesting results here very soon. And I just look forward to talking to everyone about this stuff. If you guys are interested, I'll be around. I would love some suggestions on how to make my model better using currently existing GNU Radio blocks. If anyone knows a little bit more about those than I do, I'm a little bit familiar, but I'm sure I could learn more. And yeah, if you guys have any suggestions or ideas, feel free to ping me on Element, because I am on that chat somewhat frequently. And that is it for my talk today. Thank you.
Thank you. I think we have time for one quick question, and the next speaker could also already prepare. Are there questions? All right.
Hello. Yeah, thanks first. I always love it when we have talks here that aren't like the classical radar comms, so that was cool. Can you say a little thing? So I missed the second. I came in a bit late, so maybe you said something about it, but like those transducers, can you very quickly say something about those? And is there would it make sense to pull them directly into GNU Radio so you could like start, I don't know, pinging, or I don't know exactly what they do. Like, are they just like microphones and loudspeakers, or is there more to that? Like,
sorry, you're talking about how it is that this data was taken. I'm having a hard time hearing.
So I don't know exactly how those sonic sonar transducers work.
The seismic blasting caps?
Yeah, maybe you could just like talk about the
Gotcha, what I was talking about at the beginning. Yeah, they are quite literally just explosive charges that were used back in the day to have this impulse sent through the ice that could be recorded very easily with a hydrophone. Yeah.
Thank you. So, thanks to the speaker once again.
Thanks.
So we can continue with the next speaker. That's you two. All right.
What's that? Matt Bezier, Elliot Olson. Okay.
All right. So the next speakers are Matt Bader, Elliot Olsen, and Ronald Lee. Guys, the stage is yours.
Hi, everybody. Title of this presentation is High-Speed Sensing of the Electromagnetic Environment for Cognitive Radio Receivers. It was a multi-group project between Aspen, Columbia Integrated Systems Laboratory, or CISL, and Peraton Labs. So just a brief outline. We'll just have an introduction, background and motivation, some that we're all familiar with, cognitive radio applications. Our proposed solution, one of the components of our hardware system, the EMEA sensor, a couple slides on that. We'll go over the hardware, then the machine learning based decision engine, and then we'll go over some future work and conclusions. So I'm sure we've heard a lot about it. It's our field. EM environment is cluttered in multiple domains. Frequency, time, angle, makes reception with an outstation increasingly difficult. The current detection methods now are not scalable if we consider all the possible places in the EM environment that we can find white space in. So we present a receiver architecture that uses compressed sensing to sense an emitter's location and also sends that result to a machine learning based decision engine to come up with the optimal decision for the transceiver to retune to. So this is just basically a graphical description of what I just described. We could see here two bottlenecks. We could see an n-dimensional resource cube of the EM environment, frequency versus time, frequency versus direction of arrival, quality of service, or Burr could be another one. We could also break it down further, modulation characteristics, other more internal characteristics of the signals. And then once we've identified the signals and where they are in the EM environment, we need to take some sort of corrective action. So there's also another bottleneck on the possible transceiver actions. So for the sensing problem, oh, I'm sorry, I'm getting ahead of myself. But the device that we propose is called the ITRN, the Intelligent Transceiver Radio Node, to sense and come up with the optimal decision to use. So this is just a broken out block diagram of it. It has a few parts. It consists of an EMEA sensor, which stands for EM Environment Aware Sensor. And then it has a transceiver that's communicating with an outstation and a machine learning based decision engine. You can see here, just in panel B, what exactly is happening, and we have some signals that are incident on the antenna. We sense them using our EMEA sensor very quickly, take the locations, send them along with a quality of service metric of the outstations to the MLBDE, which then comes up with the optimal decision for the transceiver to take. So we break, what we do is we exploit a characteristic of the RF spectrum called sparsity. So assuming that the RF spectrum is sparse in some domain, in this case the frequency domain, meaning that K signals is much less than N possible signal locations, we can use a DSP technique called compressed sensing to drastically reduce the time it takes to perform a scan. And on the back end, we use reinforcement learning to make this optimal decision once we learn the spectral locations of the signals. So we use a custom piece of hardware that we built and actually presented at RFIC 2018. We won third place. Basically, it's called the DSIC, the Direct Space to Information Converter. It breaks all the trade-offs between resolution and time and bandwidth that either an FFT-based spectrum sensor or a Sept LO or a channelized spectrum sensing technique uses. Instead of using N measurements for N possible signal locations, for instance, like an FFT or a Sept spectrum analyzer type of sensor, it uses M equals to K C0 log N over K, where K is the number of possible number of signals and N is the number of possible signal locations. So like I said, the direct space to information converter is used as our EMEA sensor. It's an 8 antenna RF ASIC built in TSMC 65 nanometer. And it's already been published and used for spectrum sensing in the spatial domain, or angle of arrival. So when it's put into spectrum sensing mode, we could take a look at a couple of PDPFA curves. So we could see here for one signal at minus 55 dBm incident signal power, we're able to get 90% probability of detection. And for up to k is equal to 3 signals, using 19 measurements and 4 iterations of orthogonal matching pursuit, which is what we use for the compressed sensing recovery engine, we're able to recover with 90% probability of detection at minus 60, minus 55 dBm. This is just a block diagram of our hardware prototype. We use an EDIS X310 with 2 basic RX daughter boards and 2 DSIC chips. For the demos that you'll see in this video, we're using only 1 DSIC chip for 1 band, but it does support 2. We need to use a sync pulse to synchronize the DSIC chip with the EDIS X310 for just data framing. And that required us to do some manipulate the FPGA a little bit more, which Elliot will talk about now.
Right, so to get this working with GNU Radio, we wanted maximum throughput, and we didn't have a very high dynamic range requirement. So what we did is we took 7 bits of IQ data from each analog channel and packed that into one 32-bit vector that includes the sync signal. So we can get, so essentially we're kind of doubling the throughput by just using less data, and also putting in that sync signal so we can do the recovery properly. So started with the UHD 3.15 release for the X310. And then most of the changes were done in what's called the knock block DDC, which contains DDC for each analog channel. So there's 2 of these for 2 analog channels. And essentially, the solution we came to was each DDC would share its IQ data with the other DDC, reformat the data, like in the previous slide, put in the sync signal, and that way we could use only a single AXI interface from just a single channel instead of using both. And this is a little more in-depth of what we added to the knock block DDC. Originally, it just has the DDC and its control signals. We added in a decimation block that decimates the sync signal and makes sure that it keeps its timing alignment with the IQ data. And then there's some buffering that will make sure that channel 1 and channel 0, their data stays in sync and is continuous. And then there's just the packager that does the bit manipulation to put everything into 32 bits. And now Ron's going to talk about the compressed sensing.
So now that we have the synchronized, the sync signal coming in through the EDIS X310, now we can take that incoming time series and actually perform the support recovery to get the signals, to see what frequency bins have signals. So we have 2 flow graphs here, one to show how we perform the signal support recovery, and the other flow graph was to show how we perform the bit error rate measurement across all the different channels, which is used by the machine learning based decision engine. So here we have the flow graph where we absorb in from the EDIS X310 And there's a number of custom out-of-tree modules, out-of-tree blocks that we built. So one of the first ones was the ability to extract this sync trigger or sync signal that was embedded by the X310 in the FPGA. So what we do is we extract that, and we take that time series and we basically limit it. At the time when we were first implementing this flow graph, we weren't sure how fast we could process the OMP algorithm. So we needed a way to basically lower the duty cycle of the system. So the two large blocks that you see, those are out-of-tree blocks. The first one on the left side performs the branch expansion. So Matt mentioned that depending on the number of signals we're trying to detect, we need M measurements. So you see M different measurements coming out of that block. So essentially that branch expansion is just a large channelizer. So all that data, as it gets channelized, gets run into the OMP block. This is running the orthogonal matching pursuit algorithm, as Matt mentioned before, to recover the supports. Ultimately, the output of that is a vector of instantaneously detected bins that have signals in them, which is output to the MLBDE. So this next flow graph is showing how we send a pseudo random bit sequence across all the different available frequency bins, and we're measuring essentially the bit error rate, which is going to be used to assist the MLBDE's determination of an optimal frequency bin. So MLBDE, there's a lot going on in this graph, but essentially it takes over a UDP socket, it takes two sets of information from the previous flow graph, which is ultimately the instantaneous vector of which frequency bins have signals, as well as the bit error rates for all the available frequency bins. So MLBDE takes this information to generate the optimal, or calculate the optimal bin to use as a transmission frequency. And so two of the goals are to basically pick a frequency bin that is robust and high performing, meaning something that doesn't have to be changed all the time, and something that has a good bit error rate. And so there were a number of different heuristics that were evaluated as part of this machine learning based decision engine. So it was cast into a multi-arm bandit problem. Ultimately we ended up with the epoch-greedy heuristic that we use for the MLBDE, but all along there was a random policy that was also evaluated. So at any given time we could evaluate how well the heuristic would be performing against a random frequency selection bin. So the MLBDE software was validated against 4 different scenarios just to see how robust it was in performance. So the epoch-greedy heuristic that was chosen was evaluated against a random policy. We also needed to verify that the MLBDE could process data fast enough that it could handle how fast it would be coming out of the OMP algorithm. And the third test was to validate the importance of the interference side information. So essentially the instantaneous vector of signals that was detected, and we noted that there was a good benefit from using that information as calculating an optimal frequency bin. And also there's a compound metric used to actually select the bin. So it's not just the pure reward metric, it's actually, we're using the bit error rate as well as the instantaneous signal, the signal interference vector.
So we simulated the whole system using basically what you see here. So we used one EDIS-X300, a B200, some custom PCBs that house the DSIC, and an environment emulator where we had 2 Keysight signal generators emulating frequency hopping radios. And here we could see a short demo. There's another demo that I could show at the end. This is just showing the whole system. If you look in the upper right corner, and I have another one. It's hard to see with this one, but you could see the green line is moving around The red is the instantaneous jammer detects. The green is the output of the MLBDE. And at the end, I have another video that it'll look a little bit more obvious. This is a description of what you'll see. So this is the system GUI. The top right is the Burr output of our Burr calculation engine. Bottom right is the instantaneous jammer count coming from our orthogonal matching pursuit compressed sensing recovery engine. The MLBDE is in green, so all the data gets sent to the MLBDE, which comes up with the optimal choice, optimal new channel to select. And the bottom left is the a waterfall detects versus time. So future sensor work. So this EMEA sensor actually builds on a family of what we call analog information converters starting back in 2015. We started with just frequency domain sensing. We built a few chips doing that. And then the DSIC was actually a dual domain sensor where it could do sensing in the direction of arrival domain, sensing in the angular domain, so finding the direction of arrival, as well as spectrum sensing. So just before we get to the short video, conclusions. So a CS-based receiver architecture can sense the RF spectrum in a fraction of a time as a current state-of-the-art techniques. So the current state-of-the-art techniques are all take about n amount of operations or n samples, whereas we only need m, where m is equal to k C0 log n over k number of compressed sensing measurements. We built a proof of concept called the ITRN, which you saw and we'll see in the demo video next. The jammer location coming from the EMEA sensor is sent to the MLBDE, and the MLBDE makes an optimal corrected decision, which is then sent to the ITRN transceiver. Currently, we're doing some benchmarking of the ITRN and comparing against other EMEA sensing architectures. So far, the results look like it is following the theory. So whereas an FFT-based or sweeping spectrum sensor-based EMEA sensor will take, requires n number of samples, we only require m. So here's our references, and then I have a short video which I'll bring up. Oh, that's not it. Right, so you can see here, this is across 500 megahertz we're scanning, and we have two frequency hopping radios centered at just offset from the center, and they're 66 megahertz wide each. And we're moving them around, and you can see that as we move them, they're being detected. So in the bottom right, you could see the EMEA sensor is detecting the frequency hopping radios. And you can see in the upper right, this is maybe not the best example, but typically every couple seconds, or maybe on the order of 30 seconds, we're doing 500 megahertz. We're calculating the Burr for each of the channels with an outstation. And you could see the green MLBDE output in the upper left jumping around trying to find the most optimal, well, it is finding the most optimal new channel to tune to. So that's it. Thank you.
Thank you. Are there questions? I have a question. How long did you measure the latency it takes between your measurement until you have your what's it called, your processing finished?
Yeah, we're still calculating that now. But yeah, do you want to talk a little bit about that? Yeah. So we're still working on that now. I mean, what about duty cycle or anything? You have those numbers off the top. I don't have the numbers off the top of our head. We're going through the characterization of things like that right now. So we don't exactly have a latency yet. So I could maybe on the order of magnitude milliseconds, maybe latency so far.
All right, thanks. Well, we have time for more questions. And if there are questions online, please tell me.
Hi, really interesting. Orthogonal matching pursuit is a pretty compute-intensive algorithm. Do you see any limits as to bandwidth or performance from that?
Yeah, so we encountered that same problem. So early on, in the video that you see, actually our duty cycle is pretty low. It's probably about a little bit less than 2%. So what we tried to do was explore using a GPU to do some processing. Problem is the pseudo inverse is very hard to parallelize. But the nice thing about it is some of the processing that we can have, we can actually store as a lookup table. So for up to a certain number of signals, because of the amount of memory bandwidth that's available, we can actually store it as a lookup table. So that's one way to actually accelerate it, but we don't have the results of the timing or the performance improvement for that as we're currently implementing that. But yes, we did see that.
All right.
Unfortunately, some of the benchmarks, we're right in the middle of calculating them right now, measuring them, calculating them. So it's still ongoing work.
Are there questions online? Can somebody help me out here? No, no questions online. Are there questions here? All right, then thanks again to the speakers.
No, I just need to plug in. But I've got 7 minutes. If you have one, yeah, that would be great. Does that work? 1, 2. Not good? Okay. Yeah, I didn't connect yet. Yeah, I still, I should wait till 4:20, right? Yeah. Oh, okay. Okay. Is it viewable? Oh, no, that's not. Have to set it for mirror display. Okay. Yeah, I think it's working now. Yeah. Okay. Okay. Okay, we'll get started.
All right. So, welcome to the lecture MIMO 102. I'd like to add everything in that lecture will be relevant for your finals, so take out your notebooks and pens. Having said that, the stage is yours, Matt.
Okay, thank you. Okay, so today I'm going to be talking about the sort of the more advanced, or a couple of the more advanced MIMO concepts that I mentioned in my talk last year. Just to show of hands, who was here last year and saw my talk? Okay, good. Good, okay. So I'll just step through a couple of a little bit of the previous stuff quickly just to give some background. Basically, I talked about MIMO and how multipath causes issues that MIMO can help solve, and how we can look at that, how we can model it in GNU Radio, and that sort of thing. So we talked about multipath and constant versus time varying, and Doppler and all that sort of stuff. And if you find yourself bored on a Saturday night, you can always go back and watch the video, which I think has been put back up after our takedown notice, which I was very proud of that last year. But in any case, the basic, this is the basic model of a communication system. Can everybody see my pointer? Yeah, okay. So there's all these things in a normal modern communication system, but most of this is going to be left out of what I'm talking about today, and I'm just talking about really the MIMO sections of it, and the rest of it is you know, assumed everything is synchronized and assumed that the channelization happens, and all of the fading that I talk about today is going to be flat fading, which in a single carrier system is maybe not that likely in the real world, but the reality is in a modern communication system you'll typically use OFDM, and thus will give you a set of flat fading channels. So everything we're going to be doing here today is flat fading, but it applies to non-flat fading as long as you use OFDM or something like that. Yeah, but it will be dynamic fading, right? There will be time varying fading. It will just be flat across frequency. So we talked about MIMO last time, how it increases reliability and throughput, but there's some overhead in terms of hardware complexity and stuff like that. And I went through these MIMO techniques last time, but we stopped after space-time coding and didn't do this sort of true MIMO stuff here, which is in this case spatial multiplexing and pre-coding, and that's what I'm going to cover today. Massive MIMO will still be a future exercise, so won't be covered today. So we did receive diversity, which is, I guess, MISO, right? But I use the blanket term MIMO even if there's only one transmitter or one receiver, as long as there's multiple on at least one side. And of course, somebody's calling me in the middle of this. So good. So we had transmit diversity we talked about, and space-time coding, and that's where we left off. And then we got to the advanced MIMO. So that's what I'm going to talk about today. And there's two basic categories that I'm going to talk about. The first is, I'm actually going to reverse this slide, but first talk about spatial multiplexing, and then about pre-coding. So, but before we do that, let's just review MIMO propagation. And really, it's all matrix math. For some, that's, oh, good, and for some people, that's, oh, no, it's matrix math. But really, it's pretty straightforward. You have some collection of transmit antennas and some collection of receive antennas, and all the transmit antennas have paths to all of the receive antennas, and H is typically used for a transfer function, so we use H11 to mean go from first transmitter to first receiver, H21 first transmitter to second receiver, and the like. Those H's you can collect into a matrix, and you can multiply, use matrix multiplication rather than individually doing all of the elements. Very often when we see H as a transfer function, like for a filter, it has many taps for the same channel, and that's because it is a frequency selective channel, right? Because it has width in time. But as I said earlier, everything we're doing is frequency flat today. So these are all single taps. So H21 is one value. If H21 had many values in time and it thus became a filter, we would fix that with OFDM so that we had single taps. So all of these you can look at as a single complex number. All these numbers should be assumed to be complex unless we say otherwise. So you have this N by M or NR by NT matrix that is called H. And X is the transmit signal, and Y is the receive signal, and N is noise. And so I give the size of the matrices here, just so you can follow. Right? So Y is NR, Y is N, and Y NR by 1. It's because there's an NR receivers, and the noise it happens at the receiver. Y is H. NR by NT, well, when you multiply an NT by 1 vector, the number of transmit elements, by that matrix, you get number of received signals, right? So this is just the propagation expressed as matrix math. So let's say we have this system, we want to do something more interesting than just send one signal on one antenna to one receiving antenna. Well, how do we do that? Well, we modulate the X, and we look at the Y, and then we have to look at the Y and figure out what X was sent. And that's the ultimate goal of communications, is to sort of reverse the channel. So we could invert the channel. If we have H, right, we've sensed H using some sort of pilot tones or something. So the receiver does have a picture, an estimate of what the channel looks like. So you could invert it, right? Well, and that would result in your X tilde, your estimate of the signal as being equal to sorry, I wrote that wrong there. So X plus H. That's what I get for putting too much math in these. It's X plus H inverse of N. So that seems pretty straightforward. So why don't we just invert the matrix of the channel? Well, there's a number of reasons. One is, first, sometimes it's not square. You may have more transmit antennas than receive antennas. But even more important is it could be ill-conditioned. And what that means is there may not be an inverse, or the inverse may be numerically unstable. And so what you would see here from this minor last equation with a small error in it, you would get the received value plus inverse of the noise. But if the channel was very weak and you invert it, your noise explodes. And so, and we see that in normal frequency domain equalizers or in normal equalizers of frequency selective channels, you get noise amplification where the channel was weak. Well, this is the same thing just applied to multiple antennas instead of multiple time samples. So just simply inverting the channel is not trivial. But there are ways that we can effectively accomplish the same thing, and so then the question becomes, well, do we sort of do this inversion just at the receiver, or do we do it at the transmitter, or do we kind of split it? And so the first option would be what we call spatial multiplexing, and in spatial multiplexing, what you do is you allow the receiver to do all the inversion of the channel or the detection of the channel, and you just let the transmitter, you say, okay, I've got 3 antennas, I'm going to send 3 different signals on, a different signal on each antenna, and we'll leave it to the receiver to figure that out. And so I'll show you what that actually sort of looks like here. If unfortunately that's not popping up properly. Oh, there we go. Okay. There we go. Okay, so I'll quickly show the spatial multiplexing demo, and I'll go back and I'll show what's in it in a moment. So what we have here is I have 2 antennas. We're simulating 2 antennas. Actually, maybe I should show the flow graph first. So we have 2 signal sources. One is generating QAM16, the other is generating QPSK. I just use 2 different ones so it's easy to tell them apart in the diagram. We throttle one of them, and we send it through this apply MIMO taps block. So what that is, that's just the channel. So that would be, here it is. So what it does is it takes in your input signal, which is 2 signals, right? 1 for each antenna. We're doing all 2 by 2 in the demonstrations today. And that goes, each input signal goes to 2 multipliers, and then you have these, your channel taps, H00, H10, H01, H11. And what that means is that each input signal is multiplied by these complex factors and then added into each of the output signals. So both outputs are linear combinations of the inputs, which is what you would expect from matrix math. So this is just a very quick module to do that addition, and then I have a separate module in the main flow graph that actually generates those taps. So we have 4 independent fading channels here, and then to simulate correlation between them, because correlation is the enemy of MIMO, we use these matrix multiplies just to correlate them together, and then we output those in this pad sync. And so that's what we get here, right? We have our 4 channels, our 4 channel taps, and they go into this MIMO channel, and then we have the 2 input signals in the MIMO channel here, and then we of course add noise at the receivers, and that comes out into the constellation sync. So let's run that. And so here I have manual control of the taps. This is not automatic. So on the left we have the 2 constellations. One is the QAM16 in blue. One is the PSK in red. And all the channel taps are set to 0, so you see just random noise on both receivers. Well, the first receiver is blue and the second receiver is red. So if we start playing with the channel taps, right? So this says H00 says the first transmitter is connected to the first receiver by this gain. So I made it non-zero, and you can see it comes through. And then if we set H11, you could see that the second transmitter goes into the second receiver. Now this would be like fiber optics, right? They're not crossing each other at all here. So in practice, you would also have this cross signals, right? The H10, the H01, and that makes some cool pictures in the display, but that's actually pretty hard for the receiver to decode. But what you're seeing is, so if you look at the blue on the right, for example, you've got the dominant signal is the QAM16 is coming in and causing 16 different constellation points, but added on top of it, you have the other signal, the cross signal, coming in, and it's adding the circle on top of it. Now, if I just did QAM16 for both of these, it would just look like, a grid. So and you're unlikely to see this sort of pretty a picture in a real receiver, but this is what's happening, right? And you know, I've got noise, but if we take the noise down, you can see what it looks like, right? Now I just have real channel taps here because I can so I can use sliders, and actually if Hakan is here, but my request is the equivalent of a QT slider GUI, but 2 dimensions, so you can do complex numbers with it. That's my feature request of the year. But in any case, so this is what happens. Now, how does the receiver decode this? Well, the receiver could multiply this by the inverse of the channel, but that could be that's messy. So there's other algorithms, but here I'm going to show that was sort of manually setting all of the taps. I'm going to now put this is the automatic setting of the tap. So we'll turn on some Doppler so the channel is varying, and this is no correlation, right? Actually, here, let's slow down the Doppler. So this is a hypothetical channel with no correlation, but as it correlates, you can see that the 2 constellations that are received approach each other. And when you have perfect correlation, now you no longer have 2 independent estimates of what's going on, and so in this situation, the second receiver is useless, and you would only have the information from one receiver to do this decoding, right? So again, that's why correlation is the enemy of MIMO, and that's why you sort of have to space your antennas apart sufficiently in order to get independent multipath. But now, let's say you have this system and you are attempting to decode that. Well, how would you do that? Well, the most common methods for doing this are what's called the maximum likelihood method, where you're effectively trying all the possible combinations of points and seeing which is the most likely based on your estimates of the channel and the actual received symbols. Maximum likelihood grows, exponentially in complexity, and so there are other methods that have been developed to do that more efficiently. The most commonly used is sphere decoding, which is also very complex computationally, but not nearly as much as maximum likelihood when you have a lot of antennas. But it's also it's quite complex conceptually. But this is the best picture I was able to find of it, where you have a received signal here, and you say, okay, the truth is somewhere within this sphere, and what is the most likely element within this sphere? It's a relatively complex algorithm, but it's used in things like Wi-Fi. So Wi-Fi uses multiple layer spatial multiplexing in the more modern versions. And one of the advantages of spatial multiplexing is if you have decently uncorrelated multipath, your channels will separate, and you can significantly increase your data rate because you have these parallel channels. And it works with broadcast because you're not, in a broadcast channel, you have different paths to each receiver, and you can't, pre-compensate for each of them separately. You sort of leave it to the receivers. So the advantage of spatial multiplexing is there's no need to send channel information back to the transmitter. So that reduces overhead, and it can be used in a broadcast system. The downside is because you're not doing anything transmit signal, each antenna is radiating omnidirectionally in this case, and so you're not getting any antenna gain, right? The signals are spread, and you're sending energy everywhere and not necessarily optimizing that transmission. So that's spatial multiplexing. Next we have precoding. And you can imagine two varieties of precoding. Well, the most obvious precoding was we have, right, if we go back to spatial multiplexing, we have inverting this H, you're inverting it at the receiver. Precoding would be inverting it at the transmitter, right? And so what does that mean? That means the transmitter needs to know the channel state information. And of course, this again means it's only, only to one user at a time. But it also means that you are sending the energy in the direction of the dominant channel modes. So you actually get antenna gain when you do precoding, because you have now have a correlated signal between your multiple antennas, and they are constructively interfering at the receiver. And so you actually get antenna gain from pre-coding. The one issue, and so the other issue is we saw here, you get this noise enhancement, right? Because you have h to the minus 1 of n. This is because the receiver has to do this multiply by the inverse after reception, so it's already gotten noise. If you do it at the transmitter doesn't have that noise, so it can do that inversion there, and so there's no noise enhancement. But you could have an ill-conditioned channel, which would still result in instead of noise enhancement, it results in very strong signals. It sort of amplifies what you need to send, and you end up with disparate amplitude between the different channels. And so pre-coding is actually used quite a bit in cellular systems. It's basically in a multi-user MIMO system. Pre-coding sort of implies that, okay, if this user has a good channel on these frequency bins of the FFT, we'll send to them on those frequency bins, and if this other user has a better channel on these other bins, we'll send to them on those bins, and that's effectively pre-coding. You're choosing the frequencies to send to each user based on which channels are good, and so. There are many forms of pre-coding, and you'll see a variety in modern cellular systems, certainly. The one I found the most interesting is actually where we split the channel, and we do part of the inversion at the transmitter, and you do part of the inversion at the receiver. And the tool we use to do that is called the singular value decomposition. And the singular value decomposition really comes from a result in linear algebra that says that any linear transformation can be represented as a rotation, a scale, and a second rotation. And rotation could be reflection as well. But so essentially, it takes your H, your channel matrix, and it separates it into U, sigma, and V. And U and V are rotations, and they're unitary. And so this is actually key to why this is so useful. Unitary means that, first it means that the inverse is the same as the conjugate transpose. But the more important thing is it means that when you multiply by a unitary matrix, you don't change the amplitudes. And that's critical. And it's just rotating only. And then you have this sigma, and sigma it essentially tells you how strong the different channel modes are. So we'll get into how that works. But so you take your channel, and for this to work, both sides need to know what the H is. So the receiver needs to send channel information back to the transmitter. So we have CSIT, channel state information, at the transmitter. And then both apply this pre-coding and decoding in order to productively transmit. Now, what's key for this is that this works first for non-square matrices, but it also works for ill-conditioned matrices. If there's if you don't have as many paths through the system as you have antennas, it's okay. It doesn't explode. It doesn't multiply your noise. It doesn't multiply the signal by too much. It produces useful, safe results for all situations. U and V will always be magnitude 1, and sigma will just tell you how strong your channel is. So this is a little hand wavy so far. So let's look at what the steps are. So first, we choose our number of spatial streams, and if we remember, if you have some number of transmit antennas and some number of receive antennas, you can send up to the minimum of those two. So if you have, let's say, 3 transmits and 2 receives, you can send up to 2 different spatial streams. But you don't have to choose 2. You could, or in this case, you can send just 1. And the nice thing about this SVD is sigma will tell you if there's any point in using the second spatial mode or not, because or the third or the fourth, because it tells you how strong they all are. So the first step is you pre-code at the transmit. So you multiply your input symbols by V, which you've gotten from the singular value decomposition, and V is an NT by NT matrix. So obviously this requires CSI at the transmitter, but it rotates the signal into the dominant eigenmode. Now that's sort of fancy way of saying it sends the signal in the direction where there's good paths to the receiver. And so that's where you get gain on the transmit side. You're directing the signal towards the receiver, over the known paths. At the receive side, we multiply by the conjugate of U, which is also a rotation, but this time it's if there's NR receive antennas, then it's an NR by NR matrix. And so now all of so we'll look at the math a little directly. This is the most math I've ever put in slides in my life. So if we go back to the singular value decomposition, we have H, right? That's our channel matrix. And it is decomposed by, and this is a common function in every linear algebra library, into a U, a sigma, and a V, shown either as an inverse or a conjugate transpose. And remember, being unitary, inverse and conjugate transpose are the same thing. So, and then we say, okay, what we really wanted to send is X hat. And so at the transmitter, we pre-code. We take our X hat and we multiply it by V. Not the V inverse, but V. And that becomes X, what we actually transmit. So that's our pre-coding operations. Very simple matrix multiply. And you didn't actually even have to do the inverse. The inverse was already done in the SVD. And you could just do a conjugate transpose to get the V properly. Then we send it over the channel. So we take that X, and it gets multiplied by H, the channel transfer function. And then, unfortunately, noise gets added onto it at the receiver side. And that's Y. That's what the receive antenna receives. And if we expand the H in that, we see we have U sigma V, which is the H. So U sigma V inverse, right? At times X, but X is V X hat, right? And then plus noise. Now, the V inverse times V, of course, cancels, right? And we end up with U sigma times X hat and plus noise. And then at the receiver, you pre-multiply by the U inverse, right, or U conjugate transpose, and that is the post-coding. So we have pre-coding and post-coding, or decoding, and that gives you your Y hat, which is your estimate of X hat. And so if we expand that out, now the U inverse cancels the U, and we end up with sigma X and plus U inverse times the noise. Now, U inverse, we said, is unitary, so then there's no noise gain, right? We've rotated the noise, but noise is random anyway, so it's effectively the same thing, right? So we end up with the same noise, but our signal, our S, our X, our values in the vector X have been multiplied by sigma. Now, sigma is a diagonal matrix, so it means there's an individual gain applied to each element. Now, so what does that mean? That means that the individual channels are now preserved. X hat has been transferred over, and the only change has been a gain to each. Each one has its own individual gain. And so let's look at that. I actually have using Octave actually here, and we'll just show a little plot of what happened. So this is set up to do. I'm not sure why it's not zooming. This is set up for 4 transmit antennas, 4 receive antennas, but only using 2 spatial streams, right? You can see that's why I have 442 in there. 4 transmit, 4 receive, 2 spatial streams. And you can see in the dominant eigenmode, the first spatial stream, it's red, and you can see it's a big QAM16. In the second one, it's weaker, right? The SVD implementations all sort these so that you get the strongest one first, the next one, right? And then we put nothing into the next 2 modes, and so those just the blue and the pink show up as single points because we put no energy into those. But we put energy into the red and into the green, and the green came through not as strong because it was the weaker mode. Does that make sense there? Okay, so now let's say we had the same system, but the same 2 eigenmodes that we wanted to, same 2 spatial streams, but now we only had 3 antennas on transmit and 3 antennas on receive. And so that's gonna pop up hopefully. And you can see similar, right? But now what happens if we only had 2 of each? And what tends to happen is that your second, right, if you have n transmit, the n transmit and n receive, your last one, your fourth, your last spatial stream is going to be weaker than the others. And in this case, you can see it's pretty noisy, right? It hasn't come through as strongly, and that's pretty common. So now I've got this n in a GNU Radio flow graph with the SVD, and so we can get a little more dynamic view of this. So again, what we have here is we have our channel taps, an SVD precoder. We apply the MIMO taps and then postcoder. Now the precoder and the postcoder both receive the taps on their inputs. In a practical implementation, you're going to have to feed that back from the receiver, but for demonstration purposes, we just feed it in both of them. And so here again, we have our QAM16 and our QPSK, and you can see we have our input signal on the upper left. Then we have the output of the precoder on the right, and then we have what's received by the receiver in the lower left, and post decoding on the lower right. So if we again had this magical fiber optic-like channel, you can see the precoder and the receive channel, it looks exactly the same, and our output is decoded correctly. But now what happens if, let's say, the first channel goes into the second channel? Well, again, you have to add these you have a superposition in the channel, but here we've adapted, right? So we have pre-coded, based on the superposition coming from the channel matrix, we have put some of that into the pre-coding, or the opposite of part of it into the pre-coding, so that when it's received on the other end of the channel, the decoding can remove the rest of it and get us back to the two separate signals in the output. But you can see now, as I created what I'm doing here, remember we're going from a matrix that's basically an identity matrix right now in this setting, or this is close, there's the identity matrix. We're going from an identity matrix to now in a matrix that's 1, 1, 0, 1. And so it has it's invertible, and it's not ill-conditioned, but it does have correlation. And what happens is the correlation actually adds to the energy of the first mode, and so the blue actually gets bigger, right? But it reduces the energy in the second mode, which is the red, and you can see that gets smaller as I do that. Now, if I then make it perfectly correlated, now this is an ill-conditioned matrix, and we get nothing of the second signal through, and right, you see that's why this red is in the center. There's no circular constellation, but all that energy is used productively by the dominant mode, and that grows even bigger. So in this case, because we have a perfect correlation, we still get the first dominant mode through. We just don't get the second one through. So I'm gonna switch this over to a dynamic channel and see. We can just watch what that looks like. In practice, where this is a dynamic and complex channel, I was just doing the real coefficients there. So we'll turn on the Doppler, and you can see all sorts of cool patterns, right? You can see these circles on top of the squares, and you can watch as on the receive side, on the post decoding side in the lower right, you'll see that the circle will change size relative to the square, and that's again because of a shift in the relative energy in the two modes. Now again, as I increase the correlation, right here I just have a slider for correlation, you can see a perfectly correlated channel, our second mode goes away, right? Now the cool thing about the SVD is it will choose the right way to get your dominant channel through. So even if your channel was just the first antenna getting through to the first antenna on the receive side and nothing on the second, it would send the QAM16. But if you switch it to the second one on both sides, it would still send the QAM16 because we've put that as the input to the dominant channel input on the precoder, right? If we swap those, it would prefer the circular the QPSK the PSK constellation. So now, what does this look like in practice? So here I have. This we're just going to look at the amplitudes of the signal. So I just send basically a 1 into all channels here, But again, we have the same MIMO taps, we have this SVD precoder and stuff, and we view the individual taps as well as the output signal. Can I have a couple minutes? Okay. So here, let me turn down the correlation, and this shows us the signal versus time. And so on the top plot, you can see the blue, red, green, and cyan, which may or may not be visible, are the individual channel taps. And you can see that they have big dips and stuff, but that the dominant mode of the SVD is black, and you can see it's always above all of them. And then the second mode is the purple, and you can see sometimes that actually does pretty well, but sometimes it drops low when there tends to be correlation. Now, if I increase the correlation, you'll see that purple drops significantly, and if I increase it enough, the purple will drop off the screen, off the display. And the others match. But if we turn the correlation back off and you look at the bottom, here we have our histogram, and you can see that the purple is somewhat lower than the average of the others, but the gray, which is the dominant mode, is always stronger. So what this is showing is that with this SVD precoding, you're always getting this gain in the system, at least for that dominant mode, and you're able to communicate even in the presence of the correlated multipath and pretty deep fades. So just going back to the slide, so again, that's what we showed here, and we actually have the code. The code to do this is surprisingly simple. I did this in Python blocks, and really this line here, this is all you really need to do. I mean, you have your matrix. You do your H matrix, you do your SVD of it, and then you do a multiplication, and that's all. That's the postcoder, and then the precoder does the same thing, except it multiplies by VH instead of UH. So the code is incredibly simple. Obviously, getting the channel state information back to the transmitter is more the problem there. But anyway, that's let's call it intermediate MIMO and SVD precoding. So thank you, and does anybody have any questions?
Thanks, Matt.
Oh, and while I do that, this is how you can contact me if you have any questions, and I am, like apparently everyone else here for every year, forever, I am recruiting. I work at Apple, and I can finally say this as of a few weeks ago. I am part of the satellite connectivity group, so if you are interested in working on that sort of thing at Apple, let me know. Our group actually uses GNU Radio and does a lot of cool communication stuff. So let me know if you are looking for a job.
Thanks, Matt. That's really interesting. I come from a radio astronomy background, but I love seeing the sort of the interchange of linear algebra and communication. That really fascinates me. Again, coming from a radio astronomy background, we do have the interstellar medium being a sort of a medium that applies a transfer function on whatever signals comes through. The problem is we cannot always estimate the transfer function. In your precoder, I'm interested to know how do you actually know that transfer function to apply it on your transmitters, and does that only affect receivers in one particular direction, and can you do it for multiple receivers, I guess?
Yeah. So good question. So how you actually get that channel state information back to the transmitter, or it's two aspects: is getting it back to the transmitter, but also how does the receiver figure it out? So this is a more complex flow graph that I didn't show. But what we do here is we have the precoder, SVD precoder, but also we add in some known symbols, and this is essentially what all comm systems will do these days. Is they add in pilot symbols, and sometimes those pilot symbols are modulated or whatever, but they're known to both the transmitter and the receiver. So in this particular flow graph, what we have is for every 8 symbols of symbols of useful data, we also send 2 pilots. And one pilot is, in this case, the way I did it, it was one transmitter sends a pilot while the other sends nothing, and then we switch. And then the other transmitter sends nothing, and the second one sends the pilot. And that way, in 2 time periods, both receive antennas can compute what their transfer function was to the first transmitter, and then what their transfer function was to the second transmitter. And so that's very similar to what's done in like LTE and 5G. They have these tones and Wi-Fi where you have these known symbols. Usually it's not that simple, and they'll put like an array of them all through the OFDM matrix or something. But essentially, it always comes back to I sent a 1 and I got a 0.707 plus 0.707i. That means there was a 45-degree rotation. And that's essentially what it is. So now that's not a perfect measure, right? It'll have its own noise, and so that's typically you either want to add more energy to it, or you want to send it a couple times, or average over several of them, so that you can get a good estimate. Because none of this, if the estimate's noisy, that noise is going to add into your system. So usually it's the pilot tone. Sometimes you may just use decision-directed equalizing and sort of you guess at what a signal was and sort of compensate. But in most MIMO systems, you just send independent pilots. Anybody else?
All right, so let's close that.
Or do you have a?
Okay, one more question.
Foreseeable. Can you put these online? The flow graphs? And
Yeah, I'll get the flow graphs. I have the blocks are all on GitHub, but I need to get the flow graphs up as well. I should say these are for pedagogical purposes only. They're not set up to be efficient or that practical in a real situation, but it shows you the algorithms.
All right. Thank you, Matt.
Thank you.
That was our last speaker for today. And now Martin's going to close.
Really, really, really briefly. Can I get the CTF scoreboard? It's on this computer. Can I have it on there? All right. So just to give you a sense of what's going on. Yeah, Dr. Esteves is pretty consistent. He had like 400 and something points on the first day. Now he's like 1,300. Yeah, but we've got a lot more teams. I think that's the real news. That's pretty cool. So I remember, first day I was looking at the bottom, and we had a couple of 5-point teams, and those are probably the teams that just signed up, today. So yeah, good luck, Gruff and Erdo Spy, and then M7 TWS, etc. Yeah, so very cool. I'm happy that so many people are participating. In particular, looking at the names, a lot of these are actually participating from home. They're not here, and that's something I think is really cool. Okay, so tonight is the social, 6 p.m. Penn Social. It's not far. Just PENN Social. If you put in your phone, you'll find it. It's not far from here. I just wanna apologize if I was unclear earlier. So if you are registered for the conference, then obviously you are invited to the social event, and that everything is covered, etc. Just like the people who were not planned, like the plus ones, like we also want them to come. We just have to pay for their food. So that's what the virtual ticket is for. So you just get a virtual ticket for your plus ones or plus twos. It's fine. The more the merrier. We're looking forward to having all of you there. If you show your badge, you will get free drink tickets, and then at some point you will run out of tickets, and then you'll just have to pay at the bar. But it's a social event, and we're really looking forward to seeing everyone there. And yeah, that's pretty much it for today. Tomorrow, last day of talks. I'm just gonna have one round of applause for all the speakers from today, and I'm looking forward to seeing you all at Penn Social. Later.